Senior Vice President, Urs Hölzle.
Hi. Good morning, everyone, and welcome to Google Cloud Platform Live here in San Francisco. But I also want to welcome every one of you who's watching from our offices in Seattle, New York, and London, and also from the many viewing parties, online viewing parties all around the world. So I'm Urs Hölzle, and I'm responsible for the technical infrastructure at Google. My team, which includes thousands of engineers, builds and runs the infrastructure that all of Google, and now the Google platform, cloud platform, is built on. So the data centers, the networks, the servers, and the software systems on top of that. Now, I started in 1999 to work with Google, and it's really gratifying for me to see that this platform, this super efficient and scalable and fast worldwide platform, is now available for everyone to use to deploy applications to pretty much any device, any user, pretty much anywhere in the world. Now, the Google Cloud Platform is a central part of our infrastructure development. And we're investing heavily in it to make it as great a platform for external users as it has been for internal users at Google. So we're laying the groundwork for years and years of improvements and innovation. And while we already have a strong platform, these are the early days, so you can expect a lot more. There's many things that are still hard in a platform, but we see a clear path to making developers phenomenally more productive. And build applications that really take advantage of our platform and all the services that it has to use, be that storage, compute, or higher level things like maps or speech recognition or translation. And Google is really committed to the Google Cloud Platform. And as you'll see today, we'll be introducing new features at a pretty rapid pace. So today, I want to spend my time with you on three particular themes or topics. First, a quick look back at what we've done in the last 12 months or so. But then second, while we've already accomplished a lot, I want to talk about the challenges that people still face in the cloud. There's a lot of ways in which the promise of the cloud isn't fully met yet, and we see that as a major opportunity. So we want to make developers much more productive. And so in the third part, I'll talk about how we are going to do that. Today, we're announcing new functionality, new pricing that will help you developers be more productive, more economical, and hopefully have more fun while you do it. So first, let's look at a few highlights from last year. 12 months ago, it's actually hard to think back 12 months ago because our world was so much popular features of all time, feature requests of all time. Then in August, we showed you layer 3 load balancing, and you might remember in November when we demoed it that it can reach 1 million requests per second from a cold start in 5 seconds with no need to pre-provision or warm up anything. Right? So even a 1.0 product like load balancing is actually pretty mature and pretty stable. And the reason for that is that it's based on the same code base that powers load balancing for Google.com. You're going to see that a lot from our infrastructure. Then in December, we put Compute Engine into GA, general availability, and introduced a few more new features there that I'll talk about in a minute. On the data side, we also did a lot. We introduced Cloud Data Store, our fully managed NoSQL data store that scales to pretty much anything you can throw at it, based on our very own Bigtable, the system that actually started the NoSQL revolution. We have offline disk import, encryption at rest, native connections for Cloud SQL. So one example where we're following open APIs so that you can use all the tools that come with the ecosystem that's been built up around these APIs. So something we're really committed to in the Google Cloud. Many improvements to persistent disks. And then SQL went GA general availability just last month with 99.95% SLA, larger instance types, and encryption of all data at rest. But we didn't stop there. We also introduced many improvements to BigQuery. So for example, now you can join huge tables with ease and really do big data computing at scale. We have dedicated memcache that, again, scales to pretty much arbitrary size and load. Lots of other updates. A mobile backend starter for iOS. So now on both Android and iOS, you can build the backend for your application with very little effort. And cloud endpoints let you do RESTful APIs for your own applications with little programming. And just last month, we announced HIPAA support, adding to the long list of certifications that our cloud already has. So that's great. And I want to spend a little bit more time on one feature, just one of these, and we couldn't really mention all of them, but one of them is live migration that we announced. So when Compute Engine went GA last December, it came with a unique feature called live migration. Now, why is that important? Well, as a cloud provider, you're faced with a dilemma, because you can either have an up-to-date infrastructure, patch your operating systems, upgrade, introduce new features, and so on at a rapid pace. Or you can provide long-running VMs to your users. Right? But you can't really do both, because if you apply a security patch to the OS, the underlying host OS, and then have to reboot the machine, the VM can't really survive that. But live migration solves this dilemma and lets us provide both. And to show you how it works, I'd like to introduce Chris Elliott to give you a demo. Here you are, Chris, of live migration.
So in order to demonstrate how seamless live migration is for our customers, we built this sample application here, which is going to live stream an HD video from an instance that is undergoing live migration. This instance is physically moving around in our data centers while we're live streaming this video. And this happens blazingly fast, so I'm going to walk you through what you can expect to see here. This instance down here, VOD1, is the instance that will be streaming the video. And once we start live migration, you'll see a spinning wheel appear on that instance. Then it'll briefly flash yellow, and that is when the switch happens to the new physical host. So without further delay here, I have a terminal window into my instance, and I'm going to start a script that is keeping an eye out for a signal we send to the VM when we're running live migration. This script is then going to fire off to the App Engine app you saw earlier and update that UI. So we're good there. Let's jump back over to the UI. And I have an engineer waiting by in Seattle to simulate a physical hardware failure, such as a power supply overheating on this current hardware where it's hosted. And that will then trigger live migration. So let's get this started. And so we should see very shortly that this VOD1 instance will start live migrating once she runs the tool. And we'll wait for it to start live migrating until we start streaming the video. And here we go, 1080p video streaming while this instance is undergoing live migration. And so this is currently syncing the two states of those physical machines, getting ready to make that switch over to the new machine. And it should happen any second now, because it's amazing how quickly, there it is. And now we're on a new physical machine. That is live migration. That is how quickly we can migrate. Thanks. And there's 2 points I wanted to highlight here. One is it's amazing. It fundamentally changes how developers build on virtual machines. We have added intelligence to that layer, so we can now proactively live migrate you around hardware issues. So you're always going to have a high-performant, consistent system. Similarly, it allows us to upgrade under the covers so that you always have the safest and most secure environment to run your workloads on. And the other aspect here is this is completely transparent. That is the real magic. We built this demo on signals that are available, but you shouldn't even really care about this when you're running. During development and testing, we had a test cluster with customers running large production workloads, and they were trying to find any performance hiccups to find when live migration happened. We ended up getting an email at the end of the day asking, hey, are you not doing live migration? What's happening? When in reality, we moved them back and forth 10 times that day. It really is seamless, fast. The instance is exactly the same IP, same configuration, and you really don't need to know about it live migrating at all. And at the end of the day, the only thing that actually tells you it migrated is a little note in your operations log. That's it. And this is how we can, one of the ways we can provide high performance computing with Compute Engine and give developers the consistency they expect from Google. Thanks.
Thank you, Chris. So you can see, even though our VMs may look similar to other VMs, there's really a lot of innovation under the cover that make it a unique platform. Now, let's take a look at what kind of adoption we've been seeing. We now have over 4.75 active applications running in a Google Cloud Platform, continuing the strong trend seen
and focused much less on maintaining infrastructure and much more on building new infrastructure to support the features and the product developments that we need. In fact, actually, Tim, one of our VPs of engineering, just last week told me one of his biggest surprises at joining Snapchat was at not having to deal with the operational headache and complexity that he was expecting and you would expect from a company at our growth rate and our current scale. So yeah, the biggest benefit is just the fact that we can focus less on maintaining infrastructure and much more on building new stuff.
And so as far as I understand, you still don't have an operations team, really? Like an SRE team
No,
or
not really. We're at about 25 engineers now, and a little bit of operational work here and there, but for the most part, everyone's focused on new feature development.
Cool. So if you had a piece of advice for anyone out there who wants to build the next Snapchat on a Google Cloud platform, how should they go about it?
Yeah, I would just say it's a super easy platform to use. We got started on the App Engine, which is amazingly simple to use and has scaled tremendously well. I've been absolutely impressed and very surprised that it's scaled as well as it has. Certainly thought early on that the kind of traditional notion of you build on a hosted solution and you reach a certain size at which you have to move off, I think is fading, and Google's kind of paving the way there. And so what's great about App Engine and Cloud Platform in general is that you get that kind of upfront ease of use with the added comfort of knowing that whatever you're building, if it needs to, will eventually scale, ad infinitum. So
great. Let's
so.
Let's go to infinity and beyond. So
right.
Thanks, Bobby.
Yep.
Thank you very much. So people like you make it look easy. Just a small team building an insanely popular application and just scaling just like that. Now, even though there are success stories like this, as I mentioned a little bit earlier, building an app in the cloud is still harder than it should be, because you have to spend a lot of times worrying about things that you shouldn't really have to worry about. So too many things to think about, too many trade-offs to make, and too much work that's not really related to building your app. Let's look at a few of them. Consider pricing. Right? Pricing is still way too complex. It may seem cheap by comparison with your on-premise alternatives, but there's still a lot of room for it to go down. And moreover, it seems like you need a PhD to figure out the best options. Should you use on-demand instances that are flexible or cheaper reserved instances? And should you prepay? And if so, how much? And for how long are you going to use them? And how much are you going to use them over the next year, et cetera? How do you optimize your cost versus your performance? Way too much complexity there. And often, developers also are forced to make design trade-offs, right? Like Bobby just mentioned, right? Should you get started really quickly, but then risk having to rewrite everything down the road? Or should you build something scalable, but be less productive? Now, we want cloud to be easier, and so we want to solve both of these problems. And today, in the next 10 minutes or so, I'll talk about that. So first, let's start with pricing. The chart here illustrates the typical VM in sort of the average industry cloud over the last 5 years or so. So prices have been falling by about 6 to 8% per year, which is pretty nice. But hardware prices during the same 5 years have been falling by about 20 to 30% a year. Right? So the cost of the underlying components, CPUs, RAM, flash, disk, has been falling much faster. Because they've been following Moore's law, and cloud prices haven't. And so over time, that's opened quite a gap, right? Over several years, easily a factor of 2 between the two curves. And we don't think that this gap should really exist. Because while the two curves can't be identical, because the VM price also includes not just the capital expenditures, but also the cost of running the VM, power, space, maintenance, administration, and so on. But the gap should be nowhere this large. Right? We think the two curves should be much closer together. And today we're taking a big step to bringing them much closer. And we think over the next 2 or 3 years that they will be even closer still. So I'll now describe how we do this. First, we'll have on-demand price reductions that make our on-demand pricing incredibly attractive. So Moore's law at work, basically. And then second, I'll show you how you get additional discounts that traditionally come with reserved instances, but with no upfront payment, no commitment, and no lock-in. And together, these two changes bring you industry-leading performance, price performance, really by far, without the complexity that's common in the industry. Good. Well, just wait for the details. So let's get started with the on-demand price reductions. So we start with immediate price reductions that bring our on-demand pricing to where it really should be, given Moore's law. On Compute Engine, we're reducing prices by 32% across the board and in all regions. So now our on-demand price is lower than the 3-year reserved price of most other providers. But that's not all. In storage, we price all storage now at a consistent 2.6 cents per gigabyte, no matter whether you use it for App Engine or for Compute Engine, and no matter whether you store a gigabyte or a petabyte. So for most users, that's a 68% decrease in storage cost. And our lower cost DRA alternative that gives you the same durability with a little bit less availability is 2 cents, so another more than 20% cheaper than that. But that's not all. On BigQuery, we're also reducing the on-demand prices by 85%. So now BigQuery is really accessible to everyone. And in BigQuery, we're going one step further because our largest customers have told us that they want predictable throughput for their applications. And so now you can analyze any amount of data with a chosen level of throughput in 5 gigabyte per second increments at a fixed price. So you can, you just tell us how much performance you want, right? What throughput you want, and we just provision everything for you, so you don't have to worry about what hardware resources you need to pick and how many of them and where, et cetera. So with other cloud providers or on-premise solutions, if you wanted 5 gigabytes per second of query throughput, so gigabytes per second, not megabytes per second, you'd pay about $80,000 per month. And you'd have to worry about picking the right configuration and everything. So with Compute Engine and BigQuery, this is just $20,000 a month. So 75% reduction. And on top of the predictable performance, you also get on-demand elasticity so that when your needs really spike, you can go even higher. So together, we are really resetting the price curve in a cloud to where it should be. And this isn't a one-time step. This is a philosophy. The price trend of virtualized hardware should follow the price trend of real hardware. So it should follow Moore's law. And with the Google Cloud Platform, you're going to see exactly that. Now, one more problem with pricing is really that it's, as I mentioned, it's too complicated. So now we've lowered the prices. But the original dream of the cloud and the original promise was that you could get elastic capacity. So on-demand capacity. You only pay for what you use. You don't have to pre-provision, right? You don't have to commit. And it's cheaper than anything you could do yourself. Now, the industry hasn't really evolved towards that simple concept. In fact, along the way, things have gotten more complicated, like much more complicated. Here's a graph that shows the total cost of a typical VM over 3 years, given different pricing choices. And so you can see that there's a huge difference, a factor of 10 difference between the lowest and the highest price, depending on what price plan you choose. And it's the same resource, right? So for the same resource, you can pay 10 times more if you don't pay attention. So the question is, should you use on-demand instances, or should you prepay to get a reserved instance? And if so, how much do you prepay, and for how long do you want to reserve this instance? And you have to guess, how much am I going to actually use this VM for the next year or the next 3 years? Right? This is not simple on-demand elastic computing. Right? This requires a PhD in finance to kind of get right. And so either you have someone on your team who spends a lot of time worrying about it, or you're probably paying too much, or both. So this isn't completely crazy, right? Reserved instances actually have a purpose because they try to reward you for having a predictable, sustained workload. And of course, you should get a discount for having a sustained workload. But we think that you should get that discount with no upfront price, with no upfront expenditure, with no contract, no lock-in, and just no complexity. So how do we do that? I'll show you how. Today we're introducing sustained use discounts. We want you to be rewarded automatically for having sustained usage without you requiring to pre-plan. So we're moving the burden of planning from you to us. How does this work? Well, here's an example. We start with the low rates that we just announced, so rates that are lower than anywhere else. But once you use a VM for more than 25% of the month, your price starts dropping. So every additional minute becomes cheaper. So that means that if you have a 24/7 workload that you use for an entire month, like a database instance, then in effect, you get a 53% discount over today's prices. And what's even better, you don't, this discount applies to all instances of a certain type in a region. So even if you have a VM that you restart frequently, as long as that VM in aggregate is used more than 25% of the month, you get that discount. Right? So simple, easy pricing that gives you a discount based on your actual usage with no commitment up front. And remember that our pricing already has simplicity built in all kinds of other places. So you have per minute billing, where you only pay for the minutes that you actually use. And you have linear scaling of prices across VM types. So if you need a VM that has 4 times more CPU and 4 times more RAM than your current VM, you're going to pay a rate that is 4 times higher. Right? There's no penalty for using a larger machines, things just scale as they should. So with these price principles, we've really taken the guesswork out of pricing. Your developers no longer have to double as finance planners. We do that for you. You automatically get discounts based on your actual sustained usage without any commitments. And that really was the original dream of the cloud that I talked about. You have on-demand capacity. You pay for just what you need, but you get a great price. That is a world that you can live in, right, as long as you use the Google Cloud, because that's the experience you'll have with us. So now let's turn to the other part that makes cloud computing harder than it could be. And mostly it's that you have to work around certain limitations that are in the cloud that cause you to do extra work. Let's look at a few of them. First, just the basic problem of time to market versus scalability, right? Should you build something that is quick and works, or should you make it scalable, right? There's too many examples of startups that had to go rewrite their backend just as they were getting really popular, the success failure, essentially. Second, flexibility versus automation, right? Do you want the flexibility and the openness of VMs, or do you want the automatic management of App Engine? And then third, big data scalability versus real-time analytics, right? Do you want to analyze really, really large data sets, or can you deal with the special demands of ingesting large amounts of data and analyzing them in real time? And now fundamentally, these are all hard problems, but we want to make the cloud easier, and so we believe that you should not have to choose between those apparent opposites. We'd like to turn this or into and we'd like for you to be able to do all of the above in the same infrastructure. And how we do that, to show you how we do that, I'd like to call up Greg DeMicheli. Sorry, Greg. So he can't pronounce my last name. I can't pronounce his last name. So I think we're about even. So Greg, come up, and Greg will explain to you how we do all of this. So Greg, all yours.
Thanks, Urs. Thanks, Urs. It's really no exaggeration to say that cloud is one of the biggest trends that's changing the way that developers operate. And with the new pricing that Urs announced, we really think that this will be opened up to even more developers to take advantage of the promise of the cloud. Now, before I deep dive into those hard trade-offs that Urs talked about, I want to spend just a minute and update you on a couple of very common requests I've heard from customers since we met at I/O. The first one's around operating systems. We know there's customers out there who want to run specific operating systems because they have workloads that depend upon those operating systems. So today we're announcing the GA availability of both SUSE and Red Hat Enterprise Linux on the Google Cloud Platform. So if you have workloads that require either of those products, with one click you can deploy virtual machines using those two operating systems. But of course, it's not just a Linux world. And one of the things we hear a lot is, hey, Google, are you really ever going to support Windows? And the answer to that's easy. Our customers tell us they want Windows, so of course we're supporting Windows. So starting today, we have preview support for the most popular version of Windows Server out there, available on the cloud platform. So if you're an enterprise and you have workloads that depend upon Windows, those are now open for business on the cloud platform. That's not the only common request that I've heard in the months since we were at I/O. Another one is around network management. We've heard from customers that having to manage their DNS infrastructure in one place and managing their virtual network configuration in another is a pain to keep those up to date and keep those in sync. So today we're announcing Google Cloud DNS, an authoritative DNS as a service, built, operated, managed by Google, Google scale, Google reliability, with a simple API and integrated into the Google console. So as a developer now, you can manage your network infrastructure for your applications and your DNS all in one place and get very high performance, easy to use DNS. So those are a few of the just common requests that we've had. Let me turn now to those hard trade-offs that Urs talked about. Now, the first one we want to dive into is around time to market versus scalability. So let's start at the beginning. You're a developer. Maybe you're at a startup. Maybe you're at an enterprise, and you're building an application. Right away, you know that you are going to be successful. So, of course, you want to build for scalability so that when you go viral, your application supports it. But you've got a manager, whether that's your manager or your board of directors or your stakeholder. Somebody is telling you, get the application out and get it out yesterday. So at some point, you feel this pressure to maybe not spend as much time on scalability and really just go with whatever's the most productive thing to build. And then you pay the price. The app goes viral, suddenly your app is down, and now you're frantically trying to rewrite the back end while your customers are not getting served. We think that's a false trade-off. We think you should be able to take advantage of the Google scalability that we've built the cloud platform around from the beginning, but you should also have a very productive developer experience to do it. You shouldn't have to choose between developer productivity and scalability. So to do that, we've been focusing on a couple key areas. One is making sure that when you come to the cloud platform, you can continue to use the existing tools and services that you know and love. Whether that's Git for your source code repository, whether that's Maven and Jenkins for build and continuous integration, you should be able to continue to use those tools and services and have them integrate into the cloud platform really nicely. Second, when you do a deployment, you should have the confidence to know that the deployment is successful and that you didn't have a bad deployment that resulted in your app not working. And third, when problems come up in production, and they will come up in production, because they never come up in testing servers, right? It's only production. You should have the ability to easily spot those problems in production, and with one click, make fixes so that your app is back on track running like you want without having to do a bunch of context switching from the console into a bunch of other tools. So to give us a look at exactly these things, I want to bring up Brad Abrams. He leads the product management team for our developer experiences group, and he's going to give us a demo of 0 to 60 on the cloud platform showing these productivity features.
Awesome.
Brad?
Thanks, Greg.
Do you need that? No, I need that.
So in his copious spare time, Greg's been building out this Cloud Event 2014 application. But he ran into a little snag, and he asked me to use my programming prowess to help him out. So what we're looking at here is the Google Developer Console for Greg's application. But before we drill into the console, how many people are command line fans? How many people are more productive on the command line? Let's hear it. OK?
Yep.
Great. Yes, me too. So we're going to start there. I'm going to show you our new G-Cloud command line tool. The reason I'm more productive on the command line is because of keyboard shortcuts like tab completion. So I can just say G-Cloud tab, tab, and that shows me the list of options that are available there. And then if I can type, a tab again completes that. Oh yeah, and then what were the options for components? I can't remember. Oh right, list is the one I want. Tab finishes that out. So pretty cool, huh? Okay. Fine. Okay. So we have a set of components that are available. I can add and remove those, but I have what I think I need there. So we'll clear that, and I'll do another G-Cloud command, and we'll go ahead. Cloud Event 2014. We'll go ahead and bring down code that Greg's already started onto our local workspace so that we can start getting started with this. So let's take a look at what Greg's already got. I'm going to use my second favorite editor here to check out Greg's code. And there, Greg, I think I see your problem. You forgot to give it a title. So let's see if we can do that. So GCP live. OK, just save that. Now we're going to use Git to commit that to our local repository. How many big Git fans are you? Use Git? Yes? Awesome. So I'll do a git commit, and I'll say add a title or whatever.
Or a tidy.
And then I'm going to go ahead and do a git push. So when I did the gcloud init, I initialized my local workspace with a remote repository that's hosted for us in the Google Cloud. And now I've gone and pushed that up. So if we switch over here to the console, you'll see when I refresh this that our new source code viewer in the console has that change that we looked at. There it is, GCP Live. And now if I switch over to releases, we see this is the Git URL that we offer as part of every developer console project. You get a free private Git repository that's accessible to all the members of your development team on this project.
Now that's really cool, and a lot of people do use Git, but a lot of people also use GitHub, whether it's for public open source projects or even for private repos. So is there support for that too?
Absolutely, Greg. At Google, we are big fans of GitHub. And so we've gone ahead and added a Connect to GitHub button. So all the features I'm going to show you work great if you're using a GitHub repository or one of ours. So regardless of which you use, as a post-commit action, you have your choice as to what happens. We can do a build, run a set of unit tests before we deploy that into production. In this case, we've set it to build with Maven, run unit tests, and then deploy to our cloud platform. To give you a peek inside a little bit about what's really happening, when we configured that build, what we did is we spin up a compute engine instance. And we installed on your behalf Jenkins, Maven, JDK, everything we needed to do reliable builds. And then when that git push happened, we pulled down all the code and did a clean build. And then when that build passed, we ran all your unit tests and then pushed it to production. So you can be more sure you get a safe, reliable deployment. And you can see as I've practiced this demo, the spikes in the build machine. So if we switch back over to cloud deployment, you can see our release history. And what you see here is that we added that title, we did a build, test, and we deployed that into production all in the time we've been talking here. So if we switch over and see Greg's app, Greg, it looks like a little meme application. That's kind of cool. And it's going to refresh with, and we see these, here are the memes you have. Yes, that's cute, petabytes of data. But let's, and there's the title that we added. That's great. I'm interested in what our top memes are here at the cloud event. So let's check those out. Oh, Greg, you have a server error here, a 500 server error. That's not good. These kind of issues are hard enough to debug when it's on your local machine, but when you have an issue like this in production, it's even harder. So to give you a sense about debugging this in production, I'm going to switch over and give some simulated load. So just going to throw a lot of traffic at that site. I saw some of you copying down the URL, so you might be throwing some traffic at it as well. So we'll go over and look at how we debug that issue. So I'm going to bring up the new unified logs viewer, and we're getting a log entry for every request that comes in. And you saw I just threw a bunch of requests at this thing. And we're aggregating all those logs across every front-end instance that we're spinning up into a single unified view. And so now I can just scroll through here, and notice as I'm scrolling, it's loading new logs. So it's easy for me to kind of find the logs that I'm interested in. I can also filter these, in this particular case, though, I want to look for a status 500, because that's what we saw, the 500 server error. I can also come in and filter by date and time. So if I get a bug report at a certain time, I can narrow that down pretty easily. These filters can be chained together with and or, so you can get exactly what you want. Okay, so here are the errors that we're hitting. And I can see, Greg, the problem here is this in this ominously named method, get memes buggy. That must be
I had
the
to make
problem.
it easy for you to find, Brad.
Yes, I appreciate that. So speaking of finding that, you'll notice the next thing we want to do as a developer is jump into the source, because that's where we're going to be able to fix this problem. But I have all this context loaded in my head. I need to get to the source quick so I can start bringing that to bear. So what I'm going to do is notice that right here, this is actually a hyperlink. So if I click right on this hyperlink, it brings me into the console, into our source code view with exactly the version of the source code that was deployed into production and that line of code highlighted. Pretty useful? So at this point, we could drop back to the Git command line. We could pull that file down and start operating on it. I can click on this Open an IDE button and use a variety of third-party or Google-provided IDEs. Or, because this is a very quick change, I can just click on Edit. Make this change right in the browser and go ahead and do a commit. And we'll just say fixed Greg's buggy code. And we'll deploy that into production. Now, how many of you have been debugging a production issue and you ended up SSHing into a production machine and twiddling some config file or messing with some PHP code? Who's done that? Yes, who's done that this morning? Okay, a couple of you. Okay, and that's maybe not the best idea, and that is not what we're doing here. We're actually committing this change back to the production Git repository. That change is attributed to me. It's repeatable. All future deployments will have that code as well. And we're running that full release pipeline. We're building the code on a clean machine. We're running all our unit tests, and we're deploying it only if all those things pass. Now, that takes a minute or so for those things to happen. So let's see if we can view that deployment in progress. So let's open that in a new tab. And we should see our new release. There it is. We fixed Greg's buggy code. Notice it's already built and tested that in just this short time, and we've deployed that out into production. So if we switch over now and refresh this, we should see the top cloud memes. And of course, they're all Jeff Dean memes. Guess that's how it goes. So what you've seen today is it's very easy to use tools you already know and love, like Maven, Jenkins, and Gradle to be able to target our platform. You've seen how easy it is to get reliable and quick deployments with our new continuous integration system. And finally, you saw how easy it was to find and debug an issue in production and get that fixed quickly. Thanks, Greg.
Thanks, Brad. That's really cool. I think that'll help a lot of developers make the jump to the cloud knowing that they can keep using the tools that they're comfortable with. So let's turn to the second of the big trade-offs, and it's a big one. You know, back in 2008, we introduced App Engine, which really became the first widely used platform as a service, allowing developers to focus only on the code that make their application unique and let us at Google handle all of the stuff like scaling and management and configuration and let us carry a pager so you don't have to. But today you face a tough choice. Do I use products like Compute Engine, infrastructure as a service, that give me total flexibility on open source packages I use and operating systems and programming languages, but at the cost of me having to carry my own pager, scale my own infrastructure, build out my own management? Or do I use products like App Engine, which free me from all that, but impose certain restrictions on me, like they only let me use certain languages or certain environments? This is another case of what we think is a false dichotomy, and it's one that we want to address. We think you should have access to the languages and runtimes you want and still get the auto management, auto capabilities of products like App Engine. So today we're introducing managed virtual machines. And managed VMs are just what it says. They are virtual machines that run on Compute Engine, but they are managed on your behalf with all of the goodness of App Engine. So this gives you a new way to think about building services, combining the freedom and control of App Engine, of Compute Engine, with the capabilities of App Engine. So you can start with an App Engine application, and if you ever hit a point where there's a language you want to use or an open source package you want to use that we don't support, with just a few configuration line changes, you can take part of that application and replace it with an equivalent virtual machine. And now you have control. You can do whatever you want without giving up all the benefits to begin that you chose App Engine for to begin with. So to see this in action, I've asked Chris Ramsdale to come up. Chris is going to give us a demo of managed virtual machines. He's going to take an application like Brad used, but he's going to add in now C++ code and some open source packages while still keeping the capabilities that he thought App Engine was great for to begin with. So Chris, why don't you show us managed virtual machines?
Cool. Thanks, Greg. Appreciate it. So what I want to show today is how we use managed VMs to take and add real-time image collaboration in the cloud and add that to Brad's demo. All right? So what we're going to do is we're going to have clients that are running inside of Chrome that are communicating back with a fleet of managed VMs via WebSockets for low latency communications. Right? And on those managed VMs, we're going to rely on ImageMagick, a third-party open source library that's an optimized C library for doing image processing and image rendering. Then we're going to use local disk to cache the renderings to make it super snappy. Then we're going to use App Engine's Java runtime as a serving stack to get data flowing from the front ends to the back ends. Now, as Greg alluded to, that kind of technology is not typically supported on platforms as a service, and not what App Engine is today. But with managed VMs, this is totally possible. Furthermore, we make it very easy to get up and started with this. So let me show you. Here, we're going to pop over to my terminal here. And what we see is a typical App Engine configuration file with a few parameters. So we have an application, we have a version, we have what module is running. And with a few more lines of configuration, we're actually going to turn this into a managed VM. So let me walk through these settings here. So the first thing is we're setting VM true. That's telling the system I want to run this on a managed VM so I have access to native resources and the ability to run native code. Furthermore, we get into a new section called VM settings. Here we specify machine type, for example. And since we're doing image rendering and image processing, we're going to crank up the horsepower on these VMs and deploy 8-core machines.
Now this could be any of the compute engine virtual machine types, 1, 2, 4, 8 or more cores, high mem, high CPU standard, whatever's available in GCE you can use with App Engine as well.
Absolutely, Greg. And furthermore, as we innovate here, those innovations will flow back through this configuration as well. The next line is the settings for deploying the third-party code that I want on those managed VMs. In this case, we're using ImageMagick and just doing apt-get install to those managed VMs.
And again, anything installable via apt-get, I can specify here, and it becomes available to me in a managed VM.
Absolutely. This is how we're opening up App Engine so you can use third-party libraries like that and get them onto those VMs, those managed VMs, in a super simple way. The next line is we're opening up a port. In this case, it's an arbitrary port, 65080, and that's how we're going to do the WebSocket communication from the clients that are running in Chrome back to those fleet of managed VMs. And then for the sake of this demo, we're going to specify 2 instances because that's more than enough for this demo, especially since we're running 8-core machines. So we're going to escape from this, save it. And now since this is since we're running on the Java runtime and it's a Java application, we can use Maven to deploy this. Okay, so while that's running, I'm going to talk about what's happening under the hood. So if we can cut back to the slides, please. All right, the first thing that's happening is that we're relying on our G-Cloud tools to parse and to validate the configuration file that I just showed you. Assuming that's valid, which it is, it's going to communicate to our deployment endpoints and say, okay, I want to deploy this application. Those deployment endpoints are going to store some metadata about the application, the version, the template, the number of instances that are running. And then from there, we're going to go off and we're going to create the actual containers. In this case, we're creating 8-core compute engine VMs, and we're installing our Debian OS on top of that. After that, we're going to carve out the managed services and make sure that everything's lined up correctly for you. So in this case, we're going to do monitoring and health checking, task queues, memcache, and data store. We're also going to create secure namespaces so that everything is secure within those multi-tenant systems, and we're going to set up smart defaults, so it's very easy to access the APIs and get data flowing back and forth. From there, it's onto the serving stack. And since we're running on a Java runtime, we're going to install a web server, an application server, and a JVM. And then it's on to the interesting parts, the parts that you provide. So in this case, the third-party code that we specified, so ImageMagick on those managed VMs, and then most importantly, your code. We're going to bring all that up, we're going to do some health checking, make sure everything's running correctly, and assuming it is, we're going to install a load balancer, and then we're going to wire everything up for you. And the final step is we're going to take all of that and make sure it's co-located with the other pieces of compute that you're running. So in this case, Brad had showed you some front ends that we're running. We're going to take your managed VMs and co-locate those with your front ends so you get low latency and improved overall performance. All right, so if we can jump back to the demo. All right, so our build has succeeded. Let's go check that out in Chrome. So we'll pull this up. We'll navigate to the URL that's provisioned for us. All right, and there we see our new front end, Cloud Collabo, collaboration in the cloud. This is pretty straightforward. We're going to be able to upload an image. We're going to do some edits to that image. Those edits are going to be shared with the people that are collaborating, and then we can do some real-time conversation back and forth. So let's pick an image. All right, meme 2 looks good. All right, man of the hour, Urs. We're going to use his meme to actually get going. So that's uploading to cloud storage right now. All right, there it is. So it's uploaded. We see that I am the only collaborator, so let's change that. I'm going to share this with Greg. Now, demo note where I'm going to use Chrome profiles to simulate Greg and myself communicating back and forth. So we're going to bump over to Greg's profile. Oh, yes, looks just like you, Greg. Oh, you're a Despicable Me fan as well. I love it. It's great. That is like the craziest theme I've ever seen in my life. All right, back to business. OK, so I'm sharing this with Greg right now. It's going out. It's going to log him in. Wait for it. OK, there he is. All right. And you see now that Greg and I are collaborating on this image. Now, to show you happening in real time, I'm going to try to move this over here. OK, so I'm going to pretend that Greg is actually doing the editing, and you're going to see things happening if everything works correctly in my browser as well. So we'll dress it up with a frame first. Nothing goes with green like magenta. Grab that. Say add border. All right, good. We've got a border. Now we're going to add some high-end doodling. Now, somebody had mentioned that doodling on Urs's image is probably a career-limiting move. But I said, hey, why not?
Only if the demo doesn't work.
Exactly. All right, so we're going to give Urs a big smile. Good prices in cloud. His famous earring, a little more bling. Oh, there we go. And now we see that it's happening in real time back to my browser. And so again, what's happening is that these two clients are connecting over WebSockets back to the managed VMs. We're doing the rendering, we're caching in local disk, then we're sending the updates back to the Chrome clients. Now I want to take a second and say to all the App Engine developers and users that are in the crowd that this typically wasn't and was not supported on App Engine, but yet it's been a top feature request consistently year over year. So I'm happy to announce that those feature requests are now fixed and available to you. OK, so it's not just about, thank you, all the App Engine developers in the crowd. So while the ability to access native resources and run native code on these managed VMs is fantastic, it's not just about that. It's about great developer experiences and great developer integration. So to show you that, I'm going to bump back out to the developer's console here. So here. OK, it's the same UI that Brad had shown previously. It's our developer's console. And I'm going to show how we've integrated App Engine and Compute Engine by drilling down into the App Engine tab. OK, we see our dashboard. We see our modules. I'm going to select our backend module. That's the one that's handling all the real-time collaboration and communication. We'll drill into the instances. And here we'll see the instances that are running from my application. So remember back in the configuration file, we specified that we want 2 managed VMs. Here we see those. And if we drill into this VM over here, give it a second. OK, and so there's the dashboard for the underlying VM. And if we move down on the page, we can see that it is, in fact, an 8-core machine. We've automatically configured an external IP for it. And there's some metadata here that allows us to manage the VM, quite a bit of it, actually. So that's drilling down into the VM. Now let's bubble back up and see how we've integrated all the managed services. If we come back to the App Engine tab, we'll go to our unified logs viewer. Now what's nice about this is it's not just unifying the logs on all my managed VMs. It's actually unifying the logs across all the compute that I'm doing, be it a front end running on App Engine or managed VMs that are running on top of Compute Engine VMs. So here we see that there's a fair number of servlets that are being hit for my backend. Got one for serving up an image, one for creating the WebSockets connection. And while you could do all of this on an unmanaged VM, you could do it on a raw Compute Engine VM. You could deploy syslog or rsyslog. We think there's a more productive way. We think that by offering a managed and centralized service like this, you can become a more productive developer. And furthermore, if you apply that philosophy out to things like authentication, deployment management, configuration management, developer tools, developer console, that you can be a more productive and happier developer for the cloud. Now let's take a look at how, speaking of developer productivity, let's take a look at what we do with the underlying VMs. Now, we had mentioned that these VMs are locked down by default. So they're not, you don't have root access, you don't have SSH access into them. And that's for good reason. We don't want people going out into production making changes to one of those VMs that are running inside of a large fleet. It makes it hard to manage in a high availability manner. But we recognize the fact that there are times when you need to get to those VMs to do things like do some kind of debugging or check on a configuration file that you have or make some configuration change just to see what happens to the underlying VM. We make that super simple as well. So if we come back here to the terminal, we're going to do a gcloud instances, gcloud compute, instances list. Okay, and there's our 2 VMs that are actually running. And now we're going to enable debugging for one of those. So we're going to do gcloud debug. Excuse me, compute. Debug. Use the local directory, which has the configuration for these managed VMs. And what that's going to do is it's going to go through that deployment endpoint and put those 2 managed VMs into debug mode, which is what you're seeing here. I'll clear that up. And if we do gcloud compute instances, list again, so I can grab the name. Let's grab the first one. We'll SSH into that. Let's grab that guy. Instead of list, we'll do SSH. Okay. And now that'll SSH us into the underlying VM, which you see here, Cramsdale at AE-backend 1-0. Clear that up. Now, once we're on this VM, you have access to common tools that you would normally use on a virtual machine. In this case, we can do things like run netstat. Right? And we see all the activity that's running through the various connections on the VM. In this case, we can actually see up there at 65080 with the port we're listening on for the WebSockets communication. And then we can do things like interact with the Debian package manager and see that the package that we specified inside the configuration file is actually on the VM. So in this case, we'll do dpkg, and we'll do a grep for, let's say, magic. All right, and sure enough, there you see that, in the bottom there, you see that our package is actually installed on the VM. And so all we need to do is we exit, we'll seal that VM back up, and things are good to go. So what we've seen here is that with managed VMs, we can take advantage of the auto management that App Engine provides with the control and flexibility of underlying Compute Engine VMs. We can make it super simple to get started with easy configuration, easy deployments, integration back with managed services, as well as integration with our developer console and our developer tools, right? So that you don't have to make a choice between, oh, I want platform as a service and auto management, or I want to choose flexibility with Compute Engine. Managed VMs brings both of those together, giving you the best of both worlds. And so with that, I'm going to turn it back over to Greg.
Thanks, Chris. So there you really saw the ability to blend auto management and flexibility in one offering. We think that's going to be a great way for developers to be more productive. So the last hard problem we want to talk about today is a big one. It's all about data. Big data is really revolutionizing the way people deal with analytics. And companies are able to get insights from data that was never before possible. It was previously just sort of a mass of data they couldn't make sense of. But if you take a look at most big data deployments, there's a lot of work in those that has nothing to do with analytics. It's about moving data from A to B, or sharding it so it's efficient, or transforming it from one format to another. None of which is actually about analyzing. It's all about setting up so you can analyze. What you really want to be able to do is take data as it's generated in its raw form, ingest it in real time as it's being generated, and start analyzing it the minute it's in your system without having to go through intermediate warehousing and transformation steps. And that's really why we first built BigQuery. BigQuery, you probably know, builds on a tool that we developed internally at Google. Early on at Google, we realized that we had to find a way to look at the log files of massive numbers of front-end web servers to see what's going on. And we knew that none of the existing data tools out there would be anywhere close enough. So we built an internal tool for that, and BigQuery is built on top of that. So it uses the same technology we use to do massive data analytics of front-end web servers, but with a very friendly SQL-like syntax. So back in September, we introduced in BigQuery a streaming API. And BigQuery streaming allowed you to take data as you're generating it, whether that's from applications or from physical devices, send it into BigQuery, and as soon as you send it to BigQuery, it shows up and is available for analysis. Well, we started out allowing you to ingest 1,000 rows per second into BigQuery. Today, we're taking that to the next level. We're announcing BigQuery streaming supporting 100,000 rows per second of ingestion. So what that means is you can take massive amounts of data that you generate, and as fast as you can generate them and send it to BigQuery, you can start analyzing it and drawing business conclusions from it without setting up data warehouses, without building sharding, without doing ETL, without doing copying. So to give you a demo of exactly that, of real-time large amounts of data being analyzed in BigQuery, I have a special guest we want to bring up. I want to bring up Eric Schmidt. Not the chairman of the board of directors, Eric Schmidt. The Eric Schmidt from the Cloud Platform team. Eric?
Thanks, Greg. I'm a solutions architect in the cloud platform team, not the chairman of the board. So, in this demo, I want to demonstrate how you can leverage BigQuery to do near real-time interactive analysis over rapidly changing massive data sets. As Greg just talked about, we now have the ability to ingest 100,000 rows per second per table into BigQuery. For this demo, I'm modeling some use cases from a company called Glen Canyon. Glen Canyon is a pioneer in smart meter and intelligent network technology for electric power utilities. They have millions of meters in market today. This is an example of one of them. They communicate over Wi-Fi and 3G. For our demo, we're going to have these meters report out once a minute, 60 events an hour, and I'm going to virtualize these meters over the city of Seattle, which roughly has 400,000 meters in its network. At the end of the day, we're going to be processing around 17 billion events per month. You can flip over to the demo machine. All right. So the first thing I want to do is just dive into a couple very, very simple queries to give you some context about what's happening with the system. On my other machine over here, this is my meter system. I'm generating load to create hundreds of thousands of meter requests. This query here, I'm just going to do a quick count from my single table that I'm doing raw ingestion of records. I apologize to all my DBA friends out there for doing a select star with no where clause. So there you go. We have over 4.6 billion rows in this table. We're doing around a billion per day, so this is roughly a little over a week's worth of data. So what does this data look like? I'm going to go and look at my raw data table. I'll scroll down. Oh, first get details. Scroll down. And you can see down at the bottom, I have individual meter ID, the read time from the meter, its status. The status is very important. How many of you had to call the electric company to tell them that your power's off? Wouldn't it be great whenever you call them, they tell you? You have active energy. This is how much kilowatts per hour the home or business is drawing. And if I scroll all the way out, I have things like the actual temperature of the meter. So temperature increases of a meter typically indicates some type of mechanical failure. And finally, you have the insertion time, the time that the record was actually inserted into BigQuery. This record on a case-by-case basis is 128 bytes. So roughly, we're building around 2 terabytes per month just for the simulation of Seattle. But if you want to put this into perspective, you start multiplying the number of cities on the planet, you're talking about hundreds and hundreds of terabytes into petabytes. So what can we do with this data? I'm going to flip over. I'm going to re-render this. This is a real-time visualization of all the meters in Seattle, all 400,000. This visualization is powered by a standing query that I'm running. That will calculate all of the average power for the entire grid. So you can kind of see this mean energy that's being drawn across the screen. It's a sliding window of approximately 10 minutes. So every second, I'm streaming on average around 8,000 to 10,000 records into the system because I have it completely distributed. And BigQuery is constantly ingesting and enabling me to query that data in real time. Now, let's go ahead and zoom in and try to find a location because it's kind of hard to see what's going on this map with so many points. So I'm going to find my local coffee shop on 19th, Fuel Coffee. If you're ever in Seattle, they have great coffee. I'm going to go ahead and re-render this map, and in the background, I have run another query that is doing geographic analysis just on the lat and long boundary for all the points that are in this view. So if I start clicking on them, I can go ahead and get some details specifically about just this meter. The interesting thing here to point out is I have one table, one single table for me to do my aggregations that I just showed you in the previous graph, or these graphs that are looking at specific atomic records, the active energy as well as the temperature. So I can go ahead and click around.
And this also shows, right, how BigQuery is not only for interactive analysis, but you can actually build applications that sit on top of BigQuery to do visualizations at the API level as well.
Exactly. So some of the queries that I'm about to show you that I was using in the console, those are running inside of a set of Python application as well as a Java application to power this visualization. All right, let's get back and look at some queries. This query is the average power by time. And I am going to go ahead and run this. This is fundamentally the same query that was powering the overall averaging of that entire system. Now, you'll note here up top where in my from statement, I'm using a relatively new feature inside of BigQuery called table decorators. What this enables you to do is basically filter down the rows that you would like to see that have been written into a particular table in a given time window. So fundamentally, I've taken 4 plus 4 billion rows and narrowed it down to roughly 800,000. This helps with query performance as well as reduce query cost. So you can kind of view table decorators as a simplified where with some benefits. So there you go. There's the average of the entire system right now, around 5.7 kilowatts an hour. This is interesting. I can do real-time, near real-time interactive analysis over lots of data, but let's write a bigger query, because after all, this is BigQuery. This query is the basis for the query that I was running whenever I was zooming in on my geo coordinates. And one of the things I want to point out here, Urs talked about this morning, released a feature last fall called join, or big join. In this case, what I'm doing is I am joining my raw meter table, those 4 billion rows, to a metadata table that contains all of my lat and long information for my meters. This is a great way to maintain normalization in your database. I'm a big NoSQL fan as well, but one of the challenges is you end up muddying your tables with lots of redundant data. Well, with the power of join, I can go ahead and just filter out, given lat and long, the meter IDs that I would like to address in my query. So I'm roughly filtering down to a couple hundred inside of that view. And I am averaging and also looking at their status to see if they're off and on. It's fundamentally the same query I was running before, except I'm using joins to filter out on lat and long. Now, I can average, so I have roughly, probably 200 to 300 in this view, and I'm averaging so I can see who is the highest user. I do a sort at the bottom of this query. I want to see who's the highest user of power on average. But the other thing that I did in this query is leveraged cross joins and a statistical function called quantiles to look at the entire 400,000 meters that are in this system and look at the quantile distribution. I have 100 steps in this distribution so that I could compare an individual meter to the entire population. So I'm fundamentally taking 4 billion rows, narrowing it down to around 800, doing a join, and then doing a quantile back on the entire grid system. It's a big query. But you'll notice I only processed around 200 megabytes of data. I didn't process gigs of data. And I did this in roughly 15 seconds. So there you go. Meter number 163236. They are the highest average user in that GeoGrid. And ironically, they're also in the 99th quantile, because my data is all completely randomized, but it's randomized with the same patterns. Now, this same type of query, you might not even been able to run this if you were running in a NoSQL environment, or if you didn't have the processing power, you may have gone to lunch and then came back, right? So I have one more query to show you. While I've been running this demo on my machine over here, just making sure that our system is still up. Instead of running the system to report every 60 seconds or every minute, I've asked the system to report out roughly every 7 seconds. Functionally, I've taken 400,000 meters and turned them into 2.8 million meters. This equates to roughly around 45,000 rows per second being ingested into my table. Not doing any sharding. I have one table to do all of my analysis off of. Now, if you needed to do further RPS, you could shard, and you could use something like wildcards, and you could get hundreds of thousands or millions of rows per second into BigQuery. So there you have it. All of your data in one common environment. You have a friendly SQL-like syntax. You have high throughput, low latency ingestion to do near real-time interactive analysis at democratized pricing. So thanks for your time. I hope you enjoy the rest of the show. Please turn off your lights and go big data.
Thanks, Eric. It just blows my mind that while Eric was doing that demo, that we were putting in 45,000 new rows per second while he's doing the demo live. He gets like the gutsy onstage demo award for the day, I think. You know, when you look at everything we're doing, this is a great time to be a developer. We're going to have drill down sessions on all of these technologies throughout the day, as well as product managers and engineers to help you answer your questions. So with that, I'm going to turn things back over to Urs to sort of wrap up, and thank you very much for your time.
Thank you, Greg.
Thanks, Urs.
All right. Well, as Greg said, this truly is an exciting time to be an engineer, because you can build an application for a global audience, and you have to do very little to do that other than focus on your problem. That is our goal. The amount of change and innovation around us that's happening right now is really incredible. And that creates a huge opportunity. And what we want to do is build the cloud platform that you want to use to take advantage of that opportunity. So really, a lot of what we focused on today was productivity. Right? How do we make you more productive in developing in the cloud, make it easier to build and test and deploy in the cloud using the tools that you already know. And then with managed VMs, you can have the flexibility of App Engine, the auto management of App Engine with the flexibility of VMs. You don't have to choose between the two. And then as we just saw, BigQuery allows you to make big data analysis really just work at any scale. You don't have to choose between really high scale, interactive querying, or real-time data. Right? All these three things you get on one tool, one single tool on the Google Cloud platform. And on top of that, of course, we have made this all more affordable than it's ever been before by following Moore's Law. Because we believe that the price of virtualized hardware should follow the same trends that the price of real hardware followed. Really, Moore's Law is here to stay, and you will see that in our cloud. Now, on top of that, I have shown you how you can get additional discounts for sustained usage, but without upfront payments, without lock-in, without long-term commitments, and really without the planning hassle that you have to go into with other providers just to get a good price. So this is really a new way of thinking about pricing, I think. A way where we move the planning hassle from you to us so that you can focus on the things that you actually want to focus on. So everything we're doing with the platform really is about making you more productive and helping you, the developer, to do the things you love and let us do the rest. So we introduced a lot of things today, but it's just March. So you can look forward to a lot more later this year. And I'll certainly see many of you at Google I/O here in San Francisco in June, when we will have a lot more to say about the Google Cloud. But before we get there, we're going to go on a tour, a developer roadshow, starting 2 weeks from now, going through 27 cities worldwide. So look for that at cloud.google.com/roadshow, and I hope to see some of you there as well. So with that, enjoy the rest of the day, all the detailed sessions. Thank you for putting your applications in the Google Cloud. Thank you for attending Cloud Platform Live. Thanks.
Great job.
Yeah, this worked well. Yes.
Okay. All right. Good morning. Good morning. Welcome. We're going to start. We have a long series of sessions to give a lot more detail about the announcement from the keynote today. So this is one of the 2 big data sessions for today. We're starting now. I'm William Vabanep. I'm a product manager on Google Cloud Platform. More specifically, I'm responsible for big data services on the platform. And with me today is Jim Caputo. He's the engineering manager for BigQuery. So speaking of big data, when you talk with industry analysts about big data, there's 2 factors which are most often listed as explaining the growth of big data. We believe there's a third one, which is just as important and becoming more important every day, and we'd like to talk about that. So the 2 which are usually agreed are first, the increase in the availability of data. That takes many forms. One, of course, being the fact that most business transactions now go through computers and program and generate data, and not just business transactions, a huge number of interactions of all kinds, including non-financial interactions, go through computers and programs, and a lot of data is generated that can be kept and help document what happens. At the same time, there's an ever-increasing number of devices, from cell phones to cars and things like sensors, objects whose only goal in life is to produce data. That's the only thing they do, is just pump out data all the time, and there's more and more of them every day, every month, every year. Fortunately, the cost of collecting and storing all this data is coming down dramatically as well. So all those 3 factors together, that explains the much larger availability of data. The second widely recognized reason and factor explaining the growth of big data is the increase in the ability to process data at this scale. And these 2 comes in 3 main aspects. One of them is the invention of new programming models, more famously MapReduce, and now some newer large-scale data processing programming models, which were built specifically to allow people to process data at very large scale in parallel easily. The flip side of that is, in addition to inventing new programming models, we've taken existing, well-known, familiar, popular methods, SQL chiefly, and created services that allow those to allow SQL to work at much larger scale and much faster than it was designed to do originally. And then finally, there's been a huge explosion in the availability of open source software in general, but specifically for big data. And that has really given everybody a wide portfolio of products they can use, high quality portfolio, something that, with a constant innovation, very, very dynamic environment with products like Hadoop and Spark and others, and that has really democratized and brought down the cost of big data. So all those together, that has really improved the ability to process data at large scale. Combining that with the availability of data, these are the 2 well understood reasons why big data is really picking up. The third one, and the one which I would submit is just as important and becoming even more important, and 2 days in general and the keynote this morning, I think, helps make that very clear, is the emergence of the cloud consumption model for big data. One aspect of that is how easily it lets you get started. You can wake up one morning with an idea, and by the end of the day, even if the idea involves processing terabytes of data, you've tried it, you've iterated, you've tested it, maybe you've abandoned it or you've refined it. Like you've already been able to do work with it and make progress without having to start by thinking about, can I do it? What do I need? How do I get the infrastructure? You just go do it. Whether it's a 1-day personal project or a 1-week, 2-week proof of concept, you can right away start using systems and do that at a very, very low cost. And then for those ideas and projects that actually prove to be useful that you want to take forward, where you are already in the cloud, you can scale those pretty much infinitely and keep doing that at a very, very, very low cost of ownership. I think those, hopefully you were all here early in the morning when Urs talked about the price drops, and he made it clear, this is not a one-time price drop. This is a continuous effort to really bring the cost on cloud as low as allowed by the declining cost of hardware. So cloud is the cheapest place for big data, and it will remain the cheapest place and most effective place for big data processing. And finally, the third aspect of the cloud consumption model for big data is that on a platform like Google, you have a chance of using a mix of platform-provided services, fully hosted, fully managed, as well as open source software. And you use them, it's not one or the other. You use them together. They share the same data. They share the same authentication system. It's one environment where you can seamlessly make use of one or the other, use them together, transition between them. And that's one aspect that we're going to illustrate today. So we have 2 sessions on big data. In this session, we'll focus on BigQuery. And Jim is going to describe new features, new scalability achievements, new, more detail about a new pricing model. And as he describes all that, keep in mind, everything he's describing, you get that with no installation, no configuration, no monitoring. You just come, send your query, get your result. That's it. This is the best of a fully hosted, the easiest to use, most productive services. And then, at the same time, we'll have at 3:30 here in the same room another session all dedicated to running open source big data processing software on Google Cloud Platform. And there we're going to show how the quality of the infrastructure, the compute, the storage, the network, give you excellent performance and excellent cost performance running open source data software. We'll talk about some work that we've done to implement open source APIs to natively connect to data sources. We'll talk about some tooling that we've put in place. We'll describe in detail how much value you can get from running open source software for big data at Google. And keep in mind, between these 2 sessions, hopefully you'll be able to attend both. This is really one platform. We've broken that in 2 sessions, but it's one data set, one environment for you to bring your big data processing. So for now, I'll yield to Jim, and he's going to give us all the goodies about BigQuery.
Thanks. Thanks, William, and thanks everybody for coming this morning. I'm really excited to be here to tell you about the latest innovations we've got going on in BigQuery. So we launched BigQuery a little under 2 years ago, May of 2012. And what we brought to market for the first time was the ability to scan multi-terabyte data sets in just seconds. This capability was previously unheard of, right? This unlocked a whole new set of use cases, the ability to finally do interactive analysis over huge data sets. We combined that with tremendous ease of use. No provisioning, as William was talking about. No figuring out how many machines do I need to do this? How many cores would it take to process a terabyte of data in seconds? And we make it convenient, right? The convenience of SQL and open interfaces like our REST API, web user experience, a SQL 92 compatible ODBC driver. And finally, we introduced this notion of big data storage. We wanted to improve the experience around how you actually interact and manage your data. Most of the large data processing, big data processing is done on large files, large quantities of files. We felt like a familiar database structure is what people really wanted there. They wanted easier data management. They wanted to be able to ACL and share their data. After all, you're moving all this data into the cloud. Shouldn't it be easier to collaborate with your coworkers, right? And we made it easy and fast to get your data into the system. So we've been hard at work over the last 2 years, and we've added quite a few pieces of new functionality along the way. Shortly after launch, we introduced batch processing. So you had the ability to queue up all of your jobs, and then we would just run them when idle resources were available. Clearly, not every use case requires interactive performance. The Excel connector made it easy to use Excel as your primary front end if you desired, and then use BigQuery as your primary big data back end. I've got a lot more in terms of partners to talk about in a moment. Next, we added JSON import in addition to sort of standard CSV imports. JSON's obviously valuable, pretty ubiquitous standard in terms of moving data around, but more importantly, it unlocked nested and repeated fields for us, which is a pretty powerful, although admittedly a little bit complex data structure to make use of. We also made it possible to bring data stores. If you have a cloud data store instance, you can back that up and then bring it right into BigQuery for analysis. Or as mentioned earlier, at the beginning of last year, Big Join, the ability to join 2 arbitrarily large data sets together, regardless of join key that you're operating on. Big aggregates, the ability to group on something that has potentially millions of distinct values. So, for instance, if you're grouping on something like user ID, that's going to scale with the size of your system. And then timestamps. So we're furthering that goal of making this more database-like. A standard timestamp data type and the accompanying functions that would go with that. After that, large query results. So not only were you able to query data of unlimited size, you can now generate data of unlimited size. So all of a sudden, we started seeing more and more use cases emerging. We started with that interactive analysis. We started seeing people doing more ETL processing, for instance, on top of BigQuery. Query caching, just to help out application development, reduce costs, speed things along. Analytic functions, we continue to invest in our SQL engine. Near the end of last year, the streaming API. It actually launched with 100 rows per second initially, combined with that feature you saw that Eric demonstrated with table decorators. So the ability to just slice into, I only want to see the last 2 hours of data, for instance. Right at the end of last year, Google Analytics integration. I'll talk more about this in a moment. And finally today, a bunch of new features coming out. We've dramatically increased the streaming rate, as Eric showed you, up to 100,000 rows per table now. Table views, again, extending on that goal of advanced big data storage. We want this easy to use. We want you to be able to reuse this stuff and share large queries across your organization more easily. Table wildcards. So also mentioned this morning, the ability to very easily shard your data across many tables. We want to make that easy to use from a query perspective. So for instance, if you've chosen to shard your data across days, you may want to use a wildcard that says, give me that table, and here's the date range I want to apply. It automatically just works for you. JSON functions. So if you've loaded up a bunch of JSON in a given field, you can use a JSON function to extract out values automatically. And finally, a whole bunch of other SQL improvements, trying to make us much more closely aligned with the standard SQL 92 spec, as well as a whole bunch of additional improvements like some of those analytical functions. So it's not just us. The ecosystem around us has been going at incredible speed. We've really been impressed by this. We've got a great partnership, for instance, with Tableau. We've spent quite a bit of time working on the technical integration there. We've been able to see whole new use cases emerging in that space as well. Actually bringing interactive performance to a visualization and data analysis tool like that has been tremendous. I saw a great example of pandas, so Python and analytical functions done there in the open source community. As you can see, a whole bunch of other providers all working around us. So thanks for all your efforts out in the open source and partner community. We're sort of excited to see where this can go next, building on top of the BigQuery platform. So BigQuery streaming, let's dive into this a little bit further. As demoed this morning, we can do 100,000 rows per table at a low cost of just 1 penny per 100,000 rows, and real-time availability of that data. This dramatically simplifies the amount of infrastructure that you have to build and maintain on your side. No longer do you need to batch up records and figure out when you want to submit those and at what latency or frequency they're going to come into the system. And the use cases are endless here. So for starters, you can see an example like that distributed application that Eric built. But we're starting to see other examples emerging. And working with a customer, Streak, one of our early adopters, they were impressed by this. They were able to use streaming to reduce the amount of infrastructure, of course, to simplify the infrastructure to bring their data into the system. And so great, they were able to continue using their standard reporting. What they found were new use cases emerging. All of a sudden, they had user support scenarios that would come in, and rather than have to go to one system and to figure out the debug logs, they could go to a single system, look at the debug logs, right alongside what was the historical behavior for this customer, what was their user experience over the last month or so. So we think this is the best of both worlds. It gives you the flexibility to do that real-time processing that you desire when you need it, that low latency processing, while also bringing that data into a storage system that's capable of doing your full historical analysis. So there's nothing disjoint here. Everything is all done in one location. Moving on next, I'd like to deep dive for sure into Google Analytics. For the first time, Google Analytics customers are now capable of bringing in completely unsampled row-by-row detail of their analytics data. This was previously unavailable, and the volume of data here is tremendous. Bringing this data into the system is done completely for you automatically via managed pipeline behind the scenes. Bringing this data in couldn't be any easier for you. All you need to do is sign up for Google Analytics Premium. The data automatically arrives on a daily basis. So we've already seen quick adoption here. The number of use cases are essentially endless. In talking with some of our early customers and website owners, the first thing they were amazed by is the volume of data that they could actually analyze inside of BigQuery. No longer were they looking at month-over-month changes. They were looking at year-over-year changes over many years, something just previously they couldn't actually endeavor to do. Secondarily, we've seen quickly customers are actually uploading their transactional information, which is pretty exciting because now they can do those big joins, those data mashups. They can actually look at, in this case, the customer was interested in trying to figure out why are some users spending a fair amount of money on their site. They come back, but they're not repeating their purchases. What changed? And then there's another example as well. So the value here is incredibly high. We've seen tremendous adoption. In just a few months, a whole bunch of huge customers have been coming online, huge data volumes and interesting use cases. So I wanted to look at a few other use cases I found interesting. Interactions marketing. Interactions does on-site retail marketing. So they're actually out at storefronts doing marketing campaigns. So actually maybe a sample of some sort that they're distributing. And they wanted to understand the answer to what I thought was a pretty straightforward question. They wanted to understand what's the impact of weather and weather events on these retail marketing campaigns. As it turns out, their analysts had struggled to do this for quite some time. The data volumes were just too large. They couldn't perform that data mashup. But I love this quote here from Giovanni. He says, analyses would require hours or days to complete. With Google, it took just minutes. This time to insight was previously impossible. So using the power of Tableau as their front end and BigQuery as their big data back end, deriving insights that were previously not possible to generate in the past. This next one came from Shine Technologies. I was really interested to learn more about this. In fact, they're here today, so I'm excited to have them in the audience here. So Graham actually posted a tweet a couple of months ago and said, hey, we've been really successful with this BigQuery product. What it turned out was they were actually struggling in the past to do the data analysis they needed to do on running on just a small sample of the data set that they had in question. They're using ad serving logs, so huge numbers of impressions and counts that they were trying to push through the system. And they were amazed in a 2-hour proof of concept effort. They went from getting the data loaded to immediately being able to answer questions that were previously impossible. I love the last line here. He says, the SQL-like query language is an easy transition to make for any engineer and much quicker and easier than using a MapReduce model. Again, simplicity along with scale. We're trying to drive both of these at the same time. So I mentioned we started with this arguably relatively narrow offering. It was high performance, really fast. But it wasn't really intended to solve for something as big as data warehousing. Well, that's definitely changed over the last 2 years. Our friends over at Motorola have made huge use of the system and are using it as their primary data warehouse for some of their most important data. So to walk through this, their most important data is their telemetry data that they're collecting off all of their devices out there, obviously hundreds of millions of Motorola phones. They ship this data up through App Engine multiple times per day. App Engine does some lightweight pre-processing and then drops it into cloud storage for archival purposes, which is fine, but it's not particularly actionable sitting there. They instead, as quickly as possible, move that data over to BigQuery storage where they can begin to take action on it. Well, Motorola was running the majority of their data processing in-house previously. They had a rather large Hadoop instance on their own private cluster. And they came to us less than a year ago and really started investing in the cloud platform. As it turns out, they went from basically 0 bytes in BigQuery a little over a year ago to now having many petabytes of data in storage. And they actually are still using those same Hadoop MapReduces. So they're running those MapReduces now on top of the logs that have been brought into BigQuery storage and generating the downstream tables they need for analysts to consume. On top of that, we've seen them actually migrating a decent number of their workflows over to BigQuery. So MapReduce is great in some instances. SQL solves for other cases. Might be simpler to use in some circumstances. And then finally, once that data is all processed and ready for use, it's moved downstream in general for all of their analysts to take advantage of. Hundreds of analysts around the company running queries all day long, building applications, visualizations, dashboards. So whereas previously we assumed that BigQuery was primarily intended as an analytics engine, now we're seeing it expanding, seeing it going into this data warehousing role. So I've harped on this quite a bit now. BigQuery storage, it's more than just file storage. We've invested in it quite a bit, and we continue to make improvements. It's, of course, everything you would expect from cloud-based storage, right? It's highly available, highly durable. It uses an optimized columnar format underneath, something that we've built proprietary inside Google specifically for this kind of workload. And we take those files that have been imported, and we actually do quite a bit of management on top of those for you on your behalf. So for instance, if you have happened to import a whole bunch of small files, we'll actually automatically coalesce those over time to ensure that we get the highest possible query throughput. And we offer fast table reads, the ability to read data out of that storage layer without running a query. It's rich metadata, as I said, a familiar database-like structure, data sets, tables, full fields and schemas, as well as descriptions we just added in this latest release for each one of those. A time to live on tables. Maybe you only want to store 90 days worth of data. You can just expire tables after 90 days. Project and data set level ACLs, so very fine-grained controls. And table decorators. Maybe another interesting use case with table decorators to highlight. Imagine over the last 2 days you discover that your imports were bringing in corrupted data. you could actually reference the table as it was 2 days ago, make a copy of it, rerun the imports with your corrected data, and off you go. Very easy to interact with. And finally, data imports. We've invested heavily in the standard high-frequency bulk imports. We've obviously got this new improvement now with the streaming API, and we couldn't make it any easier with respect to data feeds like Google Analytics. So BigQuery storage, it's of course optimized for SQL. That's the primary interface that we've exposed to you all, and we continue to make investments in terms of new functions. JSON extract is an interesting example here. So this might open up a whole new set of use cases. You have your JSON data somewhere, you just bring it directly into BigQuery, you can pre-process it and then generate downstream tables that you want to run your analytics on. So it's a structured data repository, but a very flexible one. With this JSON processing, you can add a lot of value to the data right there. You can do these large arbitrary joins. And you have nested and repeated fields. Complex, as I said earlier, but very powerful. So let's take a closer look at that. I'm going to use the analytics data here to look at nested and repeated fields. So analytics applies quite a bit of business logic to all of the hits that are uploaded throughout the day. It's collecting every single hit, of course, that somebody has on a given website, with the general goal being they want to generate this notion of a visit or a session. So all of these hits encapsulated for a given visitor that's arrived at the system. So their schema looks something like this. They have at the top level of a row or a record this notion of a visit ID and a visit start time and a couple of other fields. And then embedded within that, an array of hits. And within each one of those is a hit's time, so the offset from the start time. And the path, the actual URL that they hit, and a whole bunch of other fields as well. And then just thought I'd note here yet another repeated field embedded in there for custom variables if the website owner set those up. And those would hang off of the hits array. So what does this actually look like here? So we actually run Google Analytics right on top of that BigQuery user experience that you're able to use. So I pulled out a single visit here from early February. Looking at a few here, I noticed the user went from GitHub nested, one of our public data samples, and then moved to the timeline version of that, and then kind of proceeded around to various different tables there. So they were sort of exploring clearly and trying to get a sense of what are those different tables, what can they do with those. So I started thinking about an interesting use case. I was kind of wondering, how many people have done this same thing? Or how many people have transitioned, for instance, from GitHub nested to GitHub timeline? How would I go about solving that question? And maybe that's a bit contrived, but you could imagine this in a given e-commerce site, maybe a travel website. You're looking at a hotel details page, and you want to see how long does it take for people to transition from the details page over to the purchase page. Okay, that might be a little more interesting in that scenario. Maybe something's changed, or maybe it varies by region or by hotel, and maybe you need to change your marketing on those pages. So I set out to write this. I wanted to find the average duration spent transitioning from page A to page B, in this case, those two GitHub tables. And as it turns out, the SQL for this was significantly more complicated than I was actually expecting. So I apologize, this is a bit of an eye chart, I realize that, but I want to go through the specifics here and explain how this actually works. So in the innermost query here, we need to pull out the visit ID, the hit time, and the actual path that was navigated to. The next bit of syntax is omit record if. It's actually something I wasn't even familiar with prior to trying to work on this example. What it does is, rather than just apply a standard where clause, omit if allows me to find rows in which, embedded in that repeated field of hits, both of those conditions have been met. In this case, the user had navigated to both GitHub nested and GitHub timeline. So now that I have at least the rows that I'm interested in processing, I need to find those cases where they actually did transition between those two specific tables. So I come here and I use one of those analytic functions, a combination of partition by, ordering on hit time, and this notion of lead. And what it's essentially doing is it's transposing. It's taking hit number 1 and it's transposing hit number 2 alongside of it, and so on and so forth. Once I have that created using path and now path lead as the two fields as I've named them, I can now apply this final outer select. First, it's filtering, of course, and it's looking for where path is GitHub nested and path lead is GitHub timeline. And then I can do the count and the average. So this works. This definitely works. There's no doubt about it. And you can construct all sorts of amazing things, especially if you've been using SQL for years. But I would argue clearly SQL has some challenges. I mean, these limits, if not nearly impossible, in some cases are truly impossible. And so I don't think this is anything new. I mean, other databases have solved for this, right? There's PL SQL, there's T-SQL. This is pretty standard in the industry. People have accepted that sometimes a procedural language makes life 1,000 times easier. Even if you can express it in SQL, it might be that much easier to express your business logic in a procedural language. So what would this one look like? If I just want to find those hits, let's isolate in on that most important part. It's super straightforward. For each row here, I have an array of hits. I just need to check if hits sub I is equal to GitHub nested and hits sub I plus 1 is equal to GitHub timeline, then do something. In this case, I'm adding it to an array and emitting it. So it's clearly a lot easier, right? I need this escape hatch. I need this ability to be able to go operate in more arbitrary ways than I can express in SQL in some cases. And I mentioned earlier that we make this possible. You can do reads directly from BigQuery storage without running a query. In fact, I noted that Motorola was actually doing MapReduces over BigQuery storage. So what we're announcing as well today is not only can you do those reads, but you can now do them at incredibly high throughput. We're making it possible to read in parallel across a huge BigQuery table via Hadoop, via whatever parallel processing tool you have of your choosing. The pseudocode here I've included, it's trivial to set this up. You first need to instruct BigQuery via an API call that you want to read in parallel across a given table. You tell us the number of workers you're going to have. Maybe you're going to run 100 MapReduce workers. You then wait for that job to start. Should take no more than a few seconds. And then you would iterate. Each partition can be consumed in parallel across that table. So this unlocks a whole new set of use cases. But maybe there's an even easier way. And if you could switch to the demo, please. Apologies, it's pulling up the wrong desktop. Question is, which one? No. Little help. I'm on desktop 4. How do I get to desktop 4? Ah, much better. Okay. Hopefully you all can read that from the back row. It might be a little bit small. Okay, so what you're looking at here, I mentioned we have the GitHub nested table alongside the GitHub timeline table. So here I just induced this behavior. I've navigated between the two. And I've pulled in all of our analytics data into this test data set here. So we can take a quick look there as well. So we have visit ID and visit start time like I was talking about, a whole bunch of other fields here, totals, traffic source, the device that you've navigated from, as well as that repeated field of hits, so hits and the hit time and the page path. And this table isn't particularly large here. It's about 18 gigs, about 11 million rows. So I mentioned there might be an easier way. Well, indeed there is. We are combining the power of that procedural language right inside the power of BigQuery, the full scalability of BigQuery, allowing you to merge right together both SQL and JavaScript at the same time. And like that, I've run that exact same query now directly inside BigQuery without any effort in terms of spinning up resources, provisioning hardware, doing any kind of software provisioning as well. So taking a closer look here, it's pretty straightforward. We've got a standard SQL select at the top here, pulling from that given table. The next row, I'm instructing BigQuery what is going to be the input schema I'm interested in, so which fields do I want to pull out of that table. The following row is what's the schema that's going to be emitted from the function, and then as you can see, the function itself. And I would argue, going back to that, can you push the limits with SQL, what are the boundaries there? Let's take a slightly different example. Maybe I don't want to look specifically at that transition from GitHub nested to timeline immediately, but I'd like to see if they skipped a page or two in between. So changing that is as simple as coming through here, making a quick update. It's very easy, at least for me, to understand this relative to the challenge I think I would endure in trying to figure out how to do this in SQL. So off it runs. This is coming soon. We're going to make it available to you. Excuse me, please contact a sales rep to get started. Hopefully this one will finish here in a moment. And indeed it does. Please, let's switch back to the slides. So with BigQuery and the combination of both SQL and now JavaScript UDFs, we think we're unlocking a whole set of new use cases. We're very excited to see what you guys can come up with next on this. So BigQuery storage, in summary, it's optimized for SQL, of course, and we're going to continue to invest there. We have a whole bunch of new improvements coming down the road. Fast table reads, the new ability to do huge scale MapReduce directly against a BigQuery table, not having to necessarily do any operations in between. And finally, coming soon, JavaScript UDFs on top of BigQuery data directly. So the last area I wanted to cover are those pricing announcements. We talked about those this morning in the keynote. We're definitely excited about opening this up more broadly to more users. So why are we doing this? Well, of course, to reduce price, lower barrier to entry. We want more people. We want everyone to have access to big data processing. We've also heard from the larger customers we have that really wanted predictability in terms of costs. Additionally, we've seen these new usage models emerging since we started. So data warehousing, now streaming ingestion, doing real-time capabilities, and UDFs coming along the way soon. So lower across the board, everything is coming down. So lower query pricing, $5 per terabyte, an 85% reduction off of our current $35 price point. Lower storage pricing, $26 per terabyte per month, 65% reduction. And what's really important to note here is that your storage pricing is completely independent from your query pricing. So you can park as much data as you want with us at bare bones pricing and not necessarily have to pay a dime in query costs. Use it as much or as little as you want in terms of query. It's immediately available. Only Google has the infrastructure in terms of storage, network, and query capability to give you these things independently. And finally, lower streaming costs. 1 penny per 100,000 rows. We've actually deferred pricing on this until July to let you get started now. So on-demand query pricing, a closer look at this. This is essentially our existing usage model. It's ideal for interactive ad hoc analysis. It leverages a very large shared pool of resources. Because it is a shared pool, we do impose these limits in terms of how much a single user can use, making sure everybody gets their fair share of those resources. Pricing is simple, $5 per terabyte processed, no contracts, pay as you go. Doesn't get any easier. But Urs also mentioned this morning, we have a whole new pricing model coming online. It's reserved capacity. It gives predictable costs for those larger workloads, consistent performance, and we remove those concurrent query quotas. You choose how much capacity you need to send as many queries as you like. So capacity reservations, they're purchased in increments of 5 gigabytes per second. Something that's relatively easy to get your head wrapped around. How much do I want in terms of throughput? Not how many machines do I need to buy, how many cores do I need SSD versus regular disks? What do I need to do? Larger, more consistent workloads is what this is after, obviously, with a monthly commitment attached to it. Each 5 gigabyte per second increment costs $20,000 per month. It enables 13,000 terabytes of processing per month. If you were to fully utilize that, that's actually a 95% price reduction off our current $35 price point. So what is 13,000 terabytes, though? That sounds big, but I'm not really sure what it means in reality. So I put together a quick example customer scenario here. Let's imagine you have 50 terabytes of data stored, and your average query size is about 2.5 terabytes. Right off the gate, you might question, why just 5% of my data? Why is it so small? Well, I mentioned earlier, columnar data format. It's very highly optimized. We reduce the amount of data scanned simply based on the columns referenced. So if you had 50 columns in the table and you're only referencing 5 of those, probably about 10% of your data is actually going to be scanned in that query. But there's other places you can save. So table partitioning and using table wildcards. If you have daily tables and you only need to query over 7 days, then only reference 7 days worth of data. You don't need to reference the whole year. Or additionally, table decorators if you're doing more recent information that you want to pull out via the streaming API. So there's many ways in which you can get there. In fact, a lot of our customers see a lot lower than 5% in some of their use cases. So I'm also going to imagine that this company has 2 analysts that they want to have operating on this particular data set, and those analysts are going to run about 75 queries per day. So in total, that's 2.5 terabytes times 150 queries, about 375 terabytes of processing per day. As it turns out, our smallest reservation can accommodate a 50 terabyte data set, because a single reservation of 5 gigabytes per second enables you to do 432 terabytes of processing per day. So quite a bit of capability just from the smallest reservation increment. The other thing that we enable, because of BigQuery's multi-tenant architecture, is the ability to not only use your reserved capacity, but optionally burst into our on-demand resource pool. This is something nobody else is capable of doing. The scenarios here are endless, right? So it might be just during the course of a given day, there's volatility in your workloads, right? And you want to have the ability to spike and not necessarily have all of your users backed up and waiting. Or maybe the finance team is struggling to get financials done at the end, or end of the quarter. Or maybe literally you're just increasing your volumes that dramatically, and you haven't figured out how much more you want to provision, but you need the capability to run more queries. So it offers that predictability and costs with guaranteed capacity and additional resources when you need them. So what does this actually look like in practice? This is going to get a little in-depth with some charts here, but this should be fun. So here's a given day's worth of volume. And you can imagine it wouldn't be a perfect bell curve, but as you might guess, the volume's going to increase during the middle of the day for a given workday, right? And so this curve is measuring query throughput, essentially the number of queries you're pushing into the system at any given time for your reservation. In this case, using that customer example, the total query processing during that day was 375 terabytes. So that customer reserved 5 gigabytes per second, and they'd chosen not to actually burst. That's where they started out. They felt like that was the appropriate approach. And this is what you would get if you were provisioning your own hardware or buying or reserving n number of instances. You would get something that looks like this. Rather than the smooth bell curve, you would end up capping your capacity. All of your queries would start slowing down. Your users would get a worse experience. And then hopefully at some point near the end of the day, the system catches up and recovers in the middle of the night, and eventually you come back and the same experience again. We've all experienced this. Oh, the SQL server is running slow today because there's a lot of workload going on, right? But with BigQuery, you don't need to run into this problem. In our case, we're able to actually burst that additional need above and beyond your reserved instance. Ironically, the query capacity required is the same. We still have 375 terabytes of processing to do in that day. The difference is your users didn't have to bump into those painful slowdowns. So this is burst with cap. There was no change, and I'll explain cap in a moment. In the next example, they've also chosen burst with cap, but over time, their data volumes have grown. The number of queries they're running is higher. So they're spending the vast majority of their time above their reservation, more than they've reserved in terms of query throughput. So what happens in this case, because they've told us, they said, we can't go beyond our $20,000 per month budget, we're actually going to stop them at some point. We're going to stop them technically at 432 terabytes in that given day. They could, of course, go outside the reservation and still run on-demand queries. I want to be clear about that. But they have told us, they've instructed us, they don't want to go beyond that cap. And then finally, the last example, this case, they've chosen, they haven't figured out exactly how much more they want to reserve, but the last thing they want is their queries to get blocked. So they're allowing this to go through. They're going to process, in this example, 510 terabytes. So a number of scenarios there, and I realize that might be a bit complicated, but I'm trying to highlight the tremendous amount of flexibility we're bringing. The first scenario is perhaps the most obvious one, because this is what most people face on a given day. They buy a fixed amount of capacity. They're capped at that capacity. Perhaps there's some benefit here. You would avoid, if you were truly capped in terms of budget, you would avoid consuming too many resources too early on in the day. The second scenario, they ran over the top of the reservation, but they still consumed the exact same number of terabytes of processing. So there was no additional cost. Third scenario, they did a burst, and they actually bursted too far along, but they got more. They actually got 430 terabytes. They told us the cap, so the additional cost, again, is zero. And then finally, in the last scenario, they ran a total of 510 terabytes, roughly 80 terabytes more. We multiply that by the standard on-demand rate for an extra $400 that day. So we believe that BigQuery is finally realizing the true benefits of cloud here. Simplicity, the performance you desire, and the scalability you need whenever you need it. So in conclusion, you've seen a lot today, both in the keynote this morning and some of these examples here. We're trying to make it simpler for you in terms of storage. We're trying to unlock all the use cases, whether it be something you want to power with SQL or something you want to power with a MapReduce, or coming soon, SQL UDFs, all merged right inside of BigQuery. And we've made it tremendously easier in terms of both cost and provisioning, simplifying the overall use case. With that, thank you so much for your time. We look forward to seeing more of your use cases and working with you guys on new business problems. Come visit us, cloud.google.com. Thanks.
30 seconds.
Okay.
As soon as he walks on stage, you can bring this music down and he's going to be straight into his presentation. Okay, let's do it.
Hi and welcome. Thank you for joining us today. My name is Navneet Juneja. I lead product management for App Engine and Compute Engine at Google. And today, we're here to share how Google builds applications, what that means in terms of the capabilities we provide to our customers in the cloud platform, and finally, what that means in terms of the benefits you can get from our platform as a user. So what you see on the screen right now is literally a page from our history. It's the first infrastructure bill we received as Google. Now, back in the day, building applications started with buying what was back then very expensive hardware and deploying it and managing it. And quite frankly, the tools available to do that were quite terrible. And we didn't think we could build the company we wanted to build with the technology that existed back in the day. For example, the conventional wisdom back then was that in order to build a very highly reliable application, you started with the most reliable hardware you could find. So let's say you start with a piece of hardware which has a mean time between failure of 10 years. That means you expect on average that device will fail once every 10 years. Now you take 100,000 of those devices and you put them in a data center. The system you've just built actually has a mean time between failure of 1 hour. In other words, you can expect that on average, every hour, something in that system is failing. So no matter how reliable your hardware is not the path to reliable applications. It's really software. But that was only half of the picture. It turns out that even though hardware and infrastructure was really expensive back then and has gotten a lot cheaper over time, even then, the scarce resource was not actually compute resources. It was our people, and specifically the time and energy of our engineers who were building and operating and keeping Google reliable. And so the more time they had to spend on deploying applications, on building servers, and keeping them up and running, the less time they had to spend on building Google. And so in order to maximize Google's growth, we had to maximize the growth and the productivity of our engineers. And so we had to make the most of that scarce resource. So what was our solution? Well, really 3 things. The first thing was, instead of reacting to failure, we knew we had to plan for failure. We knew we had to expect that things would fail, and we had to build systems that could handle failure transparently. The second thing was to take everything we learned, and we learned a lot because we made mistakes a lot, and encode that into everything we built. So build software and platforms that took the best that we'd learned in building and operating Google at scale, and make that available to all our engineers as a force multiplier. Because every time they used this proven technology, they were benefiting from all the accumulated learning of the engineers who'd come before them. And then finally, to make all this happen, we had to make investments at all layers of the stack, starting with the design of our data centers and all the way up to the high-level platforms and software that many engineers use to build their applications. Now, we had to do all this ourselves because back then, these tools didn't exist, right? We had to just build them from scratch. We had to figure out what worked and build these platforms for our own use. And along the way, we wrote white papers about many of these subjects. We talked about MapReduce, we talked about the Google file system, we talked about Dremel. Many pieces of core technology we were building in terms of software and the platforms we were building, we actually talked about very publicly in terms of the white papers we wrote. But that is only half the picture, right? Half of what we learned wasn't just the patterns, the software, the technology that was going to work for us. It was also how we operate those things at scale, how we make sure that those things work really well when they're serving large amounts of traffic. And if you want to get the most of the benefit of our experience, the best way to do that is to use the Google Cloud Platform. So to talk more about specifically what we learned, some of the patterns we think work really well, and how we really build applications at Google, I'd like to invite Joe Beda, one of our architects at the Cloud Platform. Joe?
Thanks, Navneet. And that was actually me up there. Navneet stole that picture and kind of surprised me with that. So I want to give you a little bit of an idea of of what it's like to be a Google engineer, what your first week at Google looks like as you start learning about what has sort of evolved as the internal Google platform. And one of the things to realize here is that the Google Cloud Platform really is the internal Google Cloud Platform. We're exposing the exact same tools that we use internally to you to use. And we're continuing to expose more and more of those tools. So you're going to see more coming from the Cloud Platform in the months to come. So when we, we view these things as a toolbox of sort of flexible tools that you can bring to bear, and we're breaking those things down along for the purposes of this talk around compute, storage, networking, and then sort of services and glue that really bind all of this stuff together. And one of the things to keep in mind is that you can use these tools in these building blocks in a whole bunch of different ways. So you can use them in well-understood patterns, like we do at Google, things like MapReduce, or the way that we'll build a tree of services to actually do a query, where you start at a root, and it distributes the query, collects the results, and then distills that back up. Very common architectural pattern at Google. But if those things don't work for you, if those well-understood and proven patterns, you can go off and build your own solutions using your own architecture. And so this flexibility of building blocks, which has really made our platform stand the test of time as Google has grown and moved from doing things like search to doing things like Gmail and apps. Now let's dive into compute a little bit. When we look at compute, one of the things that Google tries very hard and sort of is necessary for us to do is to really avoid snowflakes. And so the idea of a snowflake is you want to deploy a service, so you get a server, you log in, you install some stuff, you install your application, you're done, woohoo, invoice your customer, you're done, right? But now let's say that you have to do 100 of those, or now let's say that it's a big application, you need to scale that thing out. Well, that's where things get complicated. And if you do that all by hand, you'll find, oh, server number 2 is always a little bit flaky. Let me go in and fix that guy. So that's a snowflake. That's a unique server that has its own unique problems that you have to deal with. We've built a ton of tools and techniques to be able to manage things at scale, automation, so that we actually avoid this situation where you have these special cases. And this applies not only at the infrastructure level, at making sure that the individual servers are managed and as identical as we can make them, but also works up the stack in terms of the software that we're deploying onto these things and at the application level. So concretely, what does this mean? Well, it breaks down to two things. So the first is declarative management. The idea here is that you tell the system what you want, and then you let the system take care of that for you. And when you deploy an app-to-app engine, that's exactly what you're getting. So that's an embodiment of that technique. This builds on top of this idea of idempotency, which means that if you do the same thing over and over again, you get the same result and you're actually not moving the system forward. It's a key principle for being able to deal with failures, because if something fails, well, you just try it again and then things will work. Or you won't make the system any worse, at least. And then building on top of this, you have reproducible deployment. So this is the idea that if you're deploying an application into your infrastructure, you want to make sure that you can repeat that again and again and again. And this is important because if, not only for your production systems, but also when you look at your test, dev, staging, however you want to actually call your pre-production systems, you want to make sure that those mirror your production systems as closely as possible. One of the hard-won lessons, if you've done this stuff over time, is that any issue or any place where your production infrastructure and your dev and test infrastructure differs, eventually you're going to find a bug there. So the closer you can make those things, the more you can protect yourself from having issues make their way out into production. So moving from compute to networking, Google has made enormous investments in networking. And we've done it both at the cluster level, how one machine in one data center, in a data center talks to another machine in that same data center, but also across the world. In terms of wide area networking, how one machine on one side of the world talks to another machine on the other side of the world, or how your phone or your laptop talks to Google server. And speaking specifically about that wide area network, we've done a lot of really interesting work about managing the quality of service across our worldwide network. A little while ago, Urs presented a paper at a conference describing the system called B4, that's B as in boy, It's a global software-defined WAN, and it's built on top of this technology called OpenFlow that we've pioneered, and we have the largest implementation of it. So we're really pioneers in this way in terms of doing software-defined networking. The last piece of the networking puzzle is high-capacity load balancing. And we look at this from, how do you actually, when something hits a data center, how do you actually disperse that traffic to the right servers in that particular data center, to how do you actually make sure that it gets to the right data center if you have a lot of them around the world, and how do you actually manage capacity and actually overflow from one place to another. And a great example of this is the 1 million QPS test that we ran and wrote a blog post about. I think that was mentioned in the keynote. So if you want to learn more about that, I highly recommend you read that blog post. So moving from networking to storage, at Google, pretty much all of our storage is done over the network, and we've built our networks to be able to handle that load. And this really achieves two things. So the first thing that this achieves is it gives us the opportunity to implement reliable, durable systems. Once you have that interface where you're actually getting an API between you and your storage system, you have the opportunity to build distributed, reliable, durable systems there. Great examples of this are at the blob storage level. So our product, Google Cloud Storage, is built on top of Colossus, which is the successor for GFS, which again, we have another paper out there for that if you want to read about how GFS works. But having that distance over the network gives us the opportunity to actually be smart about replication, about directing you to the most performant replica when you're doing a read, things like that. And we use that same technology both in our virtual VM block solution, so this is persistent disk as part of GCE, to Google Cloud Storage, to our structured storage and analytics systems, including Google Cloud Data Store, Google Cloud SQL, and our analytics systems like BigQuery. Back on that slide. So one of the other things I wanted to mention is because of this networking, we can actually integrate not just with Google systems, but with other systems. So there's also another great blog post detailing running Hadoop, accessing Google Cloud Storage directly using the Hadoop adapter for Google Cloud Storage. Okay, so now services and glue, bringing all this stuff together. So the first thing I want to talk about here is common data formats and API mechanisms. And so with common data formats, we use pretty much universally internally this system called protocol buffers. This is a way to actually encode, persist, and read back data in a way that's tolerant to versioning and changes and moving this stuff forward. We use this pretty much, anytime you write something to disk, anytime one server connects to another, we use protobufs inside of Google. Configuration files, protobufs. You name it, protobufs. Now there are, we've open sourced this, so this is available on code.google.com. You can use this stuff directly if you want to, but there's also a whole set of similar systems out there that give you a lot of the same advantages that you should check out. And then we have API mechanisms. How do you actually expose services so that one part of your infrastructure can talk to another part of the infrastructure? And an interesting thing there is that we built a set of API middleware that we use internally to expose all of our applications. Things like the GCE API, for example. But we also make this available to you through this product called Google Cloud Endpoints. And so you can benefit from the same rate limiting and, client libraries and all the services that we've built, that infrastructure for our APIs. You can leverage those for your APIs as well. Monitoring and alerting. If you don't monitor what's going on with your application, you don't know when things are broken. And Google has enormous investments around monitoring and alerting, and we're working hard to bring some of that to you. I think you've seen some of this today with the integrated logging, another sort of piece of this puzzle, but there's a lot more to come there. Configuration brings back to that declarative management, but you really need to take a holistic view of configuration, not only configuring which resources you're running, but also what's happening inside of those resources. And so a piece of the puzzle here is things like we're going to talk about later with managed VMs and deployment manager, but you can also leverage open systems like Puppet Chef or SaltStack to manage what's going on inside of a virtual machine. And then finally, there's automated build, testing, and lifecycle management. This is making sure that you know what you're building, you know that it's well tested, and you know that it's actually deployed when and how you want it to be deployed. There's a lot more detail with that in the session that was co-scheduled with this one that's going on in the other room. So I recommend that you check out the video once it's posted on the Cloud Platform Live site. So bringing all this stuff together, I want to talk about a couple of systems that are uniquely Google. And the first one is Google Cloud Data Store. So this is started life as the Google App Engine data store, but now it's available as a separate RESTful API so that you can access it outside of the context of an App Engine app. This is built on top of a couple of technologies that, again, we've released papers about, including Megastore and Bigtable. These are really interesting papers that I recommend you take a look at. But one of the most interesting things here is that these things take advantage of Google's entire data center. So when you buy some space in Google's Cloud Data Center, you're just putting items there and you let us take care of the scaling. You're not buying a discrete set of resources. Instead, you're actually buying more of a horizontal slice of the entire data center, which means that as you scale from the small to the very big, if you structure your schema correctly, you're not going to hit any cliffs along the way. And you won't have to make discrete decisions that, oh, I'm going to buy another chunk of capacity. And so this really is bringing the elasticity that is promised in the cloud to life. Another similar system here is BigQuery. There was a session earlier that went into a lot more detail here, but I just want to put some numbers, sort of some hypothetical numbers, in to actually drive home this point of actually using the entire sort of horizontal slice of the data center. And by the way, there's a paper on BigQuery also. It's Dremel. This is a screenshot of one of the pages there. So let's say that internally, hypothetically, Dremel uses, or BigQuery uses 1,200 spindles to actually execute your query. 1,200 spinning disks. I actually don't know how many there are, so don't quote me on that. So hypothetically, and let's say that it takes half a second to actually run a query. You're essentially buying half a second of spindle time across 1,200 spindles. That's the same as buying a single spindle for 10 minutes. As far as Google's concerned, that's the same cost. When you have enough customers actually accessing that, it's actually the same amount of spindle time. It's just unevenly distributed. But it's a game changer when you're looking at the service in terms of getting wall time results. Running a query that takes 10 minutes is not very interesting. Running a query that takes half a second is very, very interesting. So hopefully this gives you a taste of what it's like to be an engineer at Google, what our internal platform looks like, and a little bit of a hint of some of the stuff that you're going to be seeing over the next coming months. So back to you, Navneet.
Thanks, Joe. Thanks, Joe. So if you've been watching us over the past few months, you've seen several of these pieces in action in the cloud platform. We've talked about, for example, how our internal Dremel system is BigQuery that you have access to. But I wanted to just spend a few minutes recapping some of the more interesting highlights of the capabilities we've launched recently. So Compute Engine went GA in December, and we launched several enhancements. How many of you were here at the keynote? So, okay, good number of you. So if you were there, and if you weren't, I'd encourage you to watch the video later. We did a demonstration of this technology, which we call transparent maintenance. Let me go into a bit more background about transparent maintenance. So it turns out that the best way to keep any system functioning, frankly, not just computing systems, is preventive maintenance. You want to make sure that all the components of the system are functioning as well as possible. Transferring that over into the compute plane, you want to make sure that, for example, your data center power infrastructure works well. You want to make sure that your hardware is maintained properly. You want to make sure that your software, your host software, is patched whenever there's a security update. You want to make sure everything is running, frankly, as smoothly as possible, so you get the most reliable, most secure environment for all of it, or for everyone, right? Now, it turns out that many of these things I talked about, like patching host software or doing power maintenance, are actually disruptive events, right? If you have something running on a machine and you need to upgrade the host OS, it's going to affect the VM. If you want to do power maintenance and make sure your generators work by flipping the switch, it's going to affect the VM. So you could have a choice. I mean, that's one way to go about it. You could have a choice between delaying those maintenances and hoping that things don't go wrong, and so having sort of fewer disruptions to running VMs. Or you could potentially go the other way and just say, we're going to do preventive maintenance, which means you will have planned downtime, and that's just how things work. We actually didn't want to go either of those routes. We wanted to effectively let you have your cake and eat it too. We wanted to give you a minimal number of disruptions on your VMs while simultaneously keeping our infrastructure as secure and as efficient and as reliably running as possible. And so we launched this technology called transparent maintenance, which really was us going back to the drawing board and saying, how do you actually design data center operations from the ground up so that the applications running over there can survive a maintenance event? So what we're doing really, and just to peel back the covers a bit, is we're actually taking running VMs and moving them out of the way of a maintenance event. So if we know a particular rack is about to be maintained, we'll take all the VMs on that rack, move them somewhere else, perform the maintenance in the rack, and now you have an up-to-date rack. And we do this very quickly throughout the whole data center, which means that actually we can keep our software and hardware running really efficiently without impacting you. So like I said, there was a great demo in the keynote. If you didn't catch that, I really encourage you watching that, because it really drives the point home about how little the impact to a VM is when we're doing this stuff. Okay, let me talk about pricing a bit more. Now, Urs spent a lot of time about this in the keynote, so I don't want to reiterate the points he talked about. I do want to share some more color. So let me talk about virtual machine pricing. So one of the things which is basically a truism is that when you run a sustained workload, it costs less, whether you're doing that on your own hardware or you're doing it in the cloud, right? It costs the provider less because provisioning for spikes costs money. There's hardware which is not being used for large amounts of time. And some of that evens out when you're talking about cloud scale because different customers kind of spike at different times, but it's still fundamentally a problem. And so you want to make sure that customers who are doing sustained workloads actually get the best possible price. Now, one of the traditional ways that many cloud providers have looked to solve this is through commitments. So they kind of know, because you've committed to them, what you're going to be doing on that platform. And they kind of structure pricing in a way that incentivizes kind of sustained use. And that's a perfectly fine way to solve the problem, but it creates a few other problems that we wanted to avoid. Specifically, it forces you to make a commitment, right? You have to choose the kind of machine you're going to run and probably commit to it for a year or 3. And so if you decide that suddenly, actually, I kind of think this is okay, but I want a bit more RAM on this, I want to use something else, well, you've already committed to the other thing, and now you can't get the best price on that other thing. And so we wanted to make sure that you could get the best possible price without any upfront payments, without having to wade through a large menu of options, just get the best price for your workload. And so what we did was we introduced sustained use pricing. And we talk about how that works. So I'm going to use a real-world example for that. So let's say, and this is a very small-scale application, but you have one VM running your application today, right? You start at the beginning of April. You run that VM for about 10 days, during which you're doing some analysis using BigQuery on your logs, and you find out that there's probably some optimization you could do to make sure your pages load faster, right? So you do that on a second VM. You send some traffic to that VM, sort of canary it, right? And make sure that you haven't actually changed anything for the worse, everything works well. After about 4 or 5 days of testing, you find that actually, yes, you have found a meaningful optimization. This is how you want to run your application. You shut down the first VM, you keep the second VM running. Your users love this. 5 days later, you have tons more traffic, and you need to spin up a second VM to serve all that additional traffic. And you keep that second VM running the whole month. So that's kind of what this looks like, the 3 VMs running through the month. Right? So how does that look like from a sustained use discount perspective? How do we actually kind of treat that in terms of the prices we offer you? Well, so what we basically do is we kind of play a little game of Tetris here, right? We look at how you used VMs during the month. So if you look at the chart on the screen, for the first 10 days you had 1 VM running. The second 5 days, 5 days after that you had 2 VMs running. Then you had a short period when you had just the new updated VM running for 5 days. And then for the rest of the month you have 2 VMs running, serving all your traffic. So that's basically what we do. We say, as far as we're concerned, this is 2 logical VMs. You had 1 logical VM running the entire month, and so you used it for 100% and you get a 30% discount on that VM. You had a second VM which ran, although disjointedly, for half the month, and so you get a discount on that too. You get a 10% discount on that. And so we are automatically taking care of all the complexity so that you build and operate your service in a way that makes sense to you. So you don't have to do anything artificial to make sure you get the best price. We take care of that for you. And that's really what we believe is at the heart of the cloud, right? The provider should handle the complexity so you get a simple experience. And that's what we're all about. Okay, so let's talk about disk. Joe talked a bit about how at Google we build all of our storage over the network, right? So we believe that there's tons of benefits to that. For example, you can scale your compute and storage independently. You shouldn't have to buy a really beefy compute machine to get a lot of storage. You shouldn't necessarily buy a ton of storage and not be able to use it because you bought a beefy compute machine. You should use what you need. At the same time, you get benefits like network-attached storage lets you do things like snapshot your storage. So you can go back to a previous point in time if something breaks. Or you can basically look at tuning how you move your storage from one VM to another. So let's say you have a SQL database, it's running on a 2-core machine, you want to run a 4-core machine, shut down the 2-core machine, spin up the same disk on a 4-core machine, you're good to go, right? So it makes your operation a lot simpler, it makes everything more reliable, more easy to run and administer. And so we wanted to make sure that you got all those benefits, but at a good price. And so what we did was we actually launched persistent disk, which is our network attached disk, at the same price as scratch disk. So basically you get all the benefits of network disk with a single per gigabyte price that includes all the I/O, which scales with size. So if you want to scale your performance, you just know how to do it, just scale the size. It's very predictable, you don't have any 2 independent dimensions to think about, and it's very cheap. And so that's really, again, going back to the heart of offering you a simple, powerful mechanism to build your applications. That's what we're about. Okay, so let's talk about App Engine briefly. We've done a lot in App Engine pricing, and really to get the full flavor for it, you should just visit the site. But I wanted to highlight some of the changes we made there. We've drastically simplified pricing across the board. We've cut the price for instance hours by 37.5%. We've cut the price for dedicated memcache by 50%. And for data store rights, which was one of our most frequently received requests, by 33%. We've also taken a number of services that were previously charged for independently, and we've bundled them into the price of App Engine. And so overall, you'll see a much simpler, much shorter price sheet with lower prices across the board. Okay, so let's talk about networking quickly. We've launched several advances in the area of networking, starting with low-level things like giving you access to the software-defined router that underlies the network through our capabilities in advanced routing. We also launched higher-level capabilities like Layer 3 load balancing and protocol forwarding. And today we're also announcing a new service, Google Cloud DNS, which gives you access to the same DNS infrastructure that we use to serve all of our own DNS queries, to serve your own domains. And so you get access to the same low latency worldwide serving, you have command line and API access to it, and it's priced at a very simple low price. Okay, moving on, let's talk about operating systems. We've worked with commercial software providers like Red Hat and SUSE to provide their operating systems on Compute Engine. We also work with the community to provide Debian and CentOS, and recently FreeBSD, which was our first non-Linux OS, to you. Now, we didn't stop there though. We actually made the underlying virtualization technology available to you so that if you wanted to use a different distribution, you can bring your own distribution to Compute Engine. And today we're also announcing the limited preview of Windows support in Compute Engine. So if you are one of those developers who has a portion of your, or frankly all, of your infrastructure running on Windows, you can now get that on Compute Engine as well. So App Engine, we haven't taken our foot off the gas there either. So let's talk about some of the changes we've made. We recently launched the modules capability in App Engine, which lets you take your App Engine app and build it in terms of a number of different modules, components. And you can have each of these components scale independently. You can have them perform differently, have different performance characteristics. You can even use different programming languages. So let's say you're in a company where you have the people who build the back-end parts of your application really like coding in Java, and the people who build the front ends are all about Python. They can do that. You can build the 2 different modules independently and have them talk to each other, so you can actually really get the benefits of componentization and modularization for your application. Since we launched PHP, which is the 4th officially supported language on App Engine, we've seen great traction. For example, Sony Music used PHP on App Engine to serve the backend for One Direction Day, which was actually the largest streaming event on YouTube. Memcache is something a lot of developers use to build scalability and performance and acceleration into their applications. And one of the things App Engine has offered for a while is access to a shared memcache pool where you can actually get all those benefits without having to do any advanced planning. So you just show up and use the memcache API and you have memcache. But it turns out that for some specific applications, you actually benefit from the ability to do some of that planning and get a dedicated pool so you can control the performance parameters for your application. And so for those developers, we launched dedicated memcache, which as of today is now 6 cents per gigabyte per hour. And we've seen great traction there too. We now have over 10 terabytes of dedicated memcache being served to our developers. Now again, we showed you a demo of this in the in the keynote today, Git push to deploy. But I wanted to kind of talk about the philosophy behind it. So really, we believe that using tools that you're familiar with and being able to integrate those tightly with the platform gives you much faster innovation cycles. It makes it much easier to build your applications on the platform. And so the Git push to deploy capability effectively lets you connect any Git repository to your App Engine application and have a Git push become a deploy. And so you can iterate much faster on App Engine using Git push to deploy. OK. So today, when you come and try to build an application in the cloud, you're often faced with a choice. Do you want to build your application on infrastructure as a service and get all the benefits of a very flexible platform, but have to do a lot of the plumbing yourself, right? You have to build a bunch of the management pieces yourself. Or you could choose to build on a platform as a service and get a lot of agility because you don't have to build all that plumbing. You don't have to tweak it, fine-tune it, learn how to make it work better for yourself. You just focus on your own code. But to do that, you have to fit within a framework that the platform provider defines so that they can do all that management for you, right? Now, it turns out that we think that this is actually a false dichotomy. It shouldn't have to be a trade-off. If what you want to be able to do is focus on your code and not worry about the mundane details that it takes to maintain and run your application, you can do that with a combination of several new technologies we're launching today. Specifically, we think that these technologies are the foundation of the next generation cloud, where you get all the productivity, all the auto management of platform as a service, but you get that with the open and flexible environment that VMs provide. So to talk about some new technology in that area, managed virtual machines, deployment manager, and replica pools, I'd like to invite Chris Ransdale.
Thanks, Navneet. As Navin mentioned, I'm a product manager for the Google Cloud Platform. I was up at the keynote demoing managed VMs today. And so what I want to talk about is that technology plus two others that we believe will not only end this false dichotomy where you have to select as a customer, as a developer, between platform as a service or infrastructure as a service, but also how we're going to enhance developer productivity when building cloud-based applications. So first of all, how many App Engine developers do we have in the crowd right now? OK, all right. How many of you are actually building on virtual machines as well, be it Amazon or Azure or GC? OK, we've got a good blend. This is great. This is great. OK, so let me jump right in. One of the first technologies that we had alluded to in the keynote today is managed VMs. With managed VMs, you get the control and the power and flexibility of compute engine VMs mixed with and combined with the proven auto management capabilities of App Engine. For example, say you're an App Engine developer, you're building an application, and suddenly you want to have access to a language or a library or some native resource that you don't have access to, that a typical platform as a service offering doesn't support. Now, typically what happens is you're pushed off a cliff into the infrastructure as a service world, and you're left managing it all by yourself, managing the entire deployment. With managed VMs, that's not the case. We can handle that management for you. Alternatively, say you start with a vanilla VM, an unmanaged compute engine VM, for example, and you build out your solution and it's running, and at some point in time, you want us to manage it. You can flip that unmanaged VM to being a managed VM, and Google Cloud Platform takes over for you. And for more on that, I encourage you, there's a session at 2:30 called Runtime Yours that our friend Andrew Jessup is giving with the help of a few others that you should definitely check out. But it's not just about the openness there. It's not just about access to the native resources or being able to run native code. There's much more to it as well. With managed VMs, you get Google SREs. You get a team of site reliability engineers that are monitoring your deployments, co-locating them, and making sure everything is running smoothly. Managed VMs have access to all of our managed services, so data store, task queues, and memcache. And furthermore, it's not just about communication between your compute and our managed services. It's about communication between all the compute units inside your application, inside your project. For example, say you're running a bit of your front ends on App Engine today. Maybe it's built in Python, maybe it's built in PHP, who knows, pick your runtime. But you also got some back-end processing that's running on managed VMs. Because we're managing those VMs, our services and our SRE team can make sure that everything is co-located so you get low latency and improved overall performance. And finally, it's about developer productivity. And because of that, we've brought all this technology and managed VMs through our Cloud SDK so you can get at it via the command line or the developer console, as I've shown today. OK, the second technology is replica pools. Replica pools are an addition to our core compute API. As Joe had mentioned earlier on, one of the interesting problems that we had to solve at Google was how do you have declarative management and reproducible deployments? How do you build a system that optimizes so that you don't have special snowflakes? Turns out with managed VMs, we needed that as well, right? When we looked at it, we said, how can we take what we've learned at Google and bring that through to external developers so that our customers could use it in the same way we have? Replica pools is just that, a consistent, easy-to-use mechanism for getting a homogeneous fleet of VMs running in production. All you have to do as a developer is specify a template. That template specifies a base image, a set of commands that should be run in startup, a network configuration, and the initial number of instances that you want up and running. And with replica pools, much like the rest of Google Cloud Platform, what we're trying to do is take on some of the complexity and sometimes the mundane tasks of running cloud-based applications so that you can focus on applications and awesome end-user experiences. And finally, because developer productivity is near and dear to our heart, we're bringing all this great technology through to our SDK via a new component called Deployment Manager. With Deployment Manager, you can take and specify n number of VMs to be managed as a single unit. And with that single unit, you can apply a health model. So our system can then take and do health checking against that health model and healing when there's an issue that arises. We also can specify an auto-scaling policy so that our system can go and stamp out new VMs as traffic increases or as utilization across CPU or memory increases as well. So we not only think that it's an actual, not only do we think that Development Manager, or Deployment Manager, excuse me, is a way for developers to interact with complex environments, we also think it's a very great way to get started with some of these new capabilities that we're introducing to our platform. So those are the 3 new technologies that we're announcing today and talking about in terms of building cloud-based applications. But what I want to do is I want to take a step back and I want to look at how we're transitioning from a binary decision where you have to choose up front how much management you want, platform as a service or infrastructure as a service, and change that into a spectrum of management options that you can choose from as your application evolves. Okay, so if we take a look at the stack with this new technology, we see that we actually have a collection of tiered services that layer on top of each other. Okay? At the lowest level, you've got best-of-breed VMs with Compute Engine VMs, where you're managing the rest of the stack. Maybe it's you, maybe you're using open source technologies like Chef, Puppet, or SaltStack, but you're managing that portion. Or you decide that you want, you know what, I want Google to manage my deployments, so via replica pools. So we're managing the deployments, and you're managing things like the OS updates, security patches, and maybe you're deploying some kind of centralized logging and monitoring. But let's say you went out of that business as well, moving up the stack. You can have Google manage your VMs. At this point in time, we're managing everything underneath that, and you're really focusing on is managing the software that's running inside of there. So maybe it's your serving stack, maybe it's Nginx, whatever you may want. But then for some workloads, you really just want to focus on the application and the end user experience, and you want to let Google manage pretty much the entire stack below you. And it's at this level you're really taking advantage of the benefits of platform as a service. You get auto-updated software, integrated APIs, and smart defaults, right? But because these are running on managed VMs, you're not losing that control and that power of the underlying infrastructure. You can always get at the native network stack, or the file system, or run native code. So what we do is, in looking at this holistically, we believe that we're shifting away from having developers have to choose up front how much management they want, and really as their application evolves, they can switch the amount of management that they have, moving between these various tiers so that it evolves with your application without you having to do a huge code rewrite or refactoring. So that's a bunch of me talking and a bunch of slides. So to see this in action, I'm going to bring up one of our amazing developer advocates, Brian Dorsey.
Thank you, sir. Hello, everybody. It's almost demo time. OK, so after all these really big ideas, we need a really big demo, right? So Sudoku. How do you get bigger than that? It's this international world sensation. It's big in Japan. OK, if you haven't seen Sudoku, it's actually a fill-in-the-blank puzzle game. You've got numbers. You just don't repeat them horizontally, vertically, or in the same square, right? So let's use Google Cloud to play some Sudoku. So first off, we need to teach the computer to actually solve Sudoku. And we're lucky there because Peter Norvig, the gentleman who actually wrote the book on AI, wrote this fantastic essay that I highly recommend you take a look at. And it walks through all the permutations and how to write a Sudoku solver in Python, including code. So we've got that. Awesome. But what I'd like to do is actually solve like real physical puzzles, right? Like, I want to take this puzzle and solve it. So we got to get this into the computer somehow. And that means computer vision. So we're lucky there as well. There's a fantastic library called OpenCV that is a collection of computer vision algorithms written in C and C++. So I should be good to go, right? I'll just mash those together and I'm done. And this hits that like classic dilemma that we've talked about like in the keynote and stage here, and like as a developer I run into all the time. I want it to be really easy to get my stuff out. I want it to be really reliable, automatically maintained. But at some point, you run into a wall with whatever system you're using. And in this case, the wall is that I need this C and C++ library. So even if I had the whole thing written on App Engine, I still need a place to run this computer vision code. And so I can run that on Compute Engine. It's going to run great. But then I've kind of signed back up for all of the maintenance and automation. So that's why I'm just super excited about managed VMs. So here's what this looks like, the Sudoku solver in the cloud. We've got App Engine. It's a web app. So App Engine is handling all of the regular app serving, HTTP, and that sort of thing. We've got a special URL that accepts an image as a form post. And that ends up going back into task queues. And then we run the actual computer vision on Compute Engine. So awesome. From the developer perspective, what that looks like is the front end part is regular App Engine. So we've got an app.yaml here, standard normal thing. On this side, we have what managed VMs looks like. And there's very few changes. We're using modules, this same bit that lets you use different programming languages or different performance characteristics. And this extra line, VM equals true, which tells the infrastructure, by the way, deploy this code to VMs and run it for me. And there's another file that lets you say which URLs go to which module. So then this is the actual script where my code is. And down at the bottom is the key and most important parts. You might need the side monitors. But that's where we specify which Compute Engine machines we use. So we can choose any kind of Compute Engine instance, 1, 2, 4, 8 CPUs or more. You can say, I need a high CPU or high memory to do this workload. And at the bottom, you can actually just say, you list your dependencies as apt-get install lines. So in this case, I want to have the Python bindings for OpenCV and everything it needs. And I just put one line there, Python OpenCV, and it brings in like the 30+ shared libraries and everything it needs. So, OK. And then it's deployment time. So you've got one command, and that deploys your whole app to a given version. You've got all the App Engine goodness where you can say, OK, this version's good enough. Let's make that the production one. And let's go to the slides. Or sorry, let's go to the demo. OK. So on demo, and here we've got a web app. This is a real web app. This is our Sudoku solver. I've got a webcam hooked up. Hello, everyone. And right here, if we pull the cord out of the way, we will try to get an actual image that we're going to try to solve. So we've got this image, and it's saved there. And when I hit solve here, it's going to send that off to App Engine, goes through this architecture that we talked about, hits the task queue, hits the Compute Engine, saves it in cloud storage, and goes online. So moment of truth, we hit the button, send it on out, and solved. So this is a problem in my life solved forever. I never have to solve another Sudoku puzzle. We're good. So that's pretty cool. But I just wanted to kind of poke around behind the scenes a little bit and show you what this looks like. So this is our developer's console. And we're down in the Compute Engine section here. And so we can actually see we have a couple of running instances. And that's this demo actually running. We can take a look in at a particular instance, see different things about it, get its name that we're going to need here in a moment. And let's dive to the command line. And we're still connected. Awesome. They talked earlier about how, so these are managed VMs, right? The Google infrastructure runs these VMs for you, so you don't really want them to be different. We don't want snowflakes here. But sometimes you want to go take a look under the covers and see what things actually look like. So there's a command for that, gcloud compute debug, and then give it the current directory that you're working in. And it'll go out and say, OK, these guys are ready for debugging. And we can SSH into this instance that we got there, connects off, and just to prove it, look at that. We're in this instance, and it's ready to go. So now, being a developer, right, I like to have environments look a certain way. So I might go apt get install like tmux, or maybe vim. Go ahead and kind of get things in there a little bit. It's also a real virtual machine with and a Google compute engine virtual machine with all of our security set up the way it works, easy for you. So I can use gsutil and pull a file down from cloud storage that contains my tmux config. Because I like things this way, and I have to type the command correctly, software. I bring that down, run tmux. I'm all in, ready to do some looking around this machine. OK, so let's, first off, we'll go into var log app engine. We can look around there. We can use Vim and go and take a look at the request log, see a bunch of health checks coming through. That looks pretty OK. Maybe we want to see how the network looks. So what's going on the network? So sudo apt get install, and we'll look at iftop, for example. Bring that down, kind of run, I need to be root to do that. Run iftop, kind of see how things are going in the back end. You can see a little bit of activity there, but nothing unusual. I keep debugging, and I run top, and we'll just assume that I look through here and notice it's really my code, as it usually is, eating all the CPU. So I'm going to go back and fix my code, and that pretty much wraps this up.
Wait, you just created a snowflake. You installed a bunch of stuff on a machine, and that might break something.
Oh, I did. But I think this will be OK. I didn't do that much.
That's how this happens. That's how you get yourself in trouble.
OK, point taken. I've made that mistake before. So how do we fix this? Basically, here's this instance we have again. And so I can go down to the bottom and just click delete and really delete this and trust that the managed VM's infrastructure will start up new ones to run the right number of instances. So it's all good to go. So back to the slides. And so here is what that looked like. So we take things in. App Engine handles all of the main web requests. So this is regular App Engine auto-scaling, scaling up to all the things you've seen before. We've created a buffer in task queues so that if we get a sudden load spike and then it goes right back down, we can kind of have a few more things there. And then we're using application-specific scaling on the Sudoku solver side of things. And what that looks like in code, it's really easy. I basically just make one call and say I want this many instances running. So what I can do is I can watch the stats on that task queue, for example, and say, oh, it's gotten behind. Let's start some more instances. Or it's all cut up. We can shut some more down. So there we go. Thank you very much. Back to Navdeep.
Thanks, Brian. So let me just quickly wrap this up. What did we learn today? So Joe talked about how we build applications at Google. Pardon me. He talked about a number of the patterns that we found to work really well, like, for example, storing your data on the network, like making sure you avoid snowflakes. Thanks, Brian and Joe. Making sure that, fundamentally, that you try to leverage as much as possible the learning of the people who came before you by leveraging platforms that embody what they've learned. And we've continued to share details about that software. We will continue to do so. We also talked about how we believe that the choice between infrastructure as a service and flexibility and PaaS and sort of time to market and developer productivity is actually a false choice. And we're going to keep making that something that you don't have to worry about in the days to come. We talked about several products that make this vision of ours a reality. Managed VMs, we talked about deployment manager, and replica pools that at different levels of abstraction and different levels of sort of detail let you employ some of the patterns that Joe talked about. And then I just want to leave you with one thought, which is that we're just getting started. What you've seen today is just the beginning. There's lots more to come from us in the days and months to come. We'd love to have you come and sign up and try managed VMs. The URL for that is on the screen. And we also pulled together some resources that go into more detail about the subjects that Joe talked about, as well as some of the products we announced today. That URL is on the screen right now. Thank you very much.
Of management for VMs, is the pricing per hour the same on all those?
Yes, it is.
Thank you.
So there's a couple questions up front here.
Yeah. We got two up here.
Yeah. Thanks for waiting for the mic, guys.
Makes it easier for everybody who's listening remotely.
Is there a story for Git to deploy for Compute Engine and or managed VMs?
Yes, so that's something that we're working on. So what you've seen today was Git push to deploy going to App Engine. But clearly the next path we're going to go down, since a lot of this is running through the same deployment architecture, this is the whole idea of convergence, right? When we converge, then it actually works for any compute unit that we have at Google. So the next steps from the roadmap is to work with unmanaged compute engine VMs and managed VMs that we were talking about today.
Yeah, just a quick question about the endpoints, the RESTful API. Is that only at the App Engine level, or does the VM also include that? It was a little bit unclear.
Well, currently Cloud Endpoints is something that's only available through App Engine, through the App Engine sort of front door. But that's the type of thing that we'd be looking at expanding.
And they definitely complement each other
Nothing ready
well.
to announce. What?
You can use the same technique that we did in the Sudoku solver to have the endpoints cooperate with workloads that are also running on managed VMs.
But then you're stuck with those languages that you have.
For that actual part of it.
For the front end, correct, yes.
Yeah. Let's see, maybe blocked by a pillar. There we go, a couple over there.
We have over here in blue.
Just a clarification on that question they said. So when you do on VMs, any changes like packages and installs and things like that, how do you manage that today? Do you have, like, let's say if you did something on the VMs and you now have to deploy a new VM, how do you save it back and then you launch a new VM?
Right, so it's a really good question. So the typical life cycle that we're encouraging here is that you start with declarative management that I've shown a couple of times, that Brian showed as well, to say this is what I want running on those VMs. And assuming there's no problems, that's great. We're looking into ways that we can turn that into a static binary that we can easily scale up and scale down and things like that. In the case that when you do want to debug those VMs in SSH in, and you do something like Brian did where you got various open source technologies running on there, we expect that you'll either, for example, if you're debugging, you figure out what's going on and you make that change locally, or doing in your Git repository, for example. And then once that's done, you do a push. And because these managed VMs are funneling through the same deployment architecture that App Engine has, you get things like versioning out of the box, rolling deployments, the ability to canary traffic, shift it, do a slow rollout, and things like that. But the idea is that you go into those machines, you figure out what's going on, you figure there's a problem with one of them, and say one of a fleet of just say 10 or 20, whatever it may be. And say, okay, I've got it, this is probably systemic across my entire fleet, I'm going to change it locally, store it wherever you need to, do a push that revs your version, test it out, do a slow deployment over, and then you're good to go. And then you can get rid of V-1 of the VMs.
Right, so let me just kind of take a step back and talk about that conceptually. I mean, the goal here with both Deployment Manager and Managed VMs is to make it very easy to build with patterns that will scale with you and that will lead you to a place where you have a well-running application, right? So you want to declare everything declaratively so that, want to specify everything declaratively, so that when you spin up more VMs, when the system spins up more VMs, they look like all the others. There's no weird cases where one VM is faster than the rest, you don't know why, or vice versa, right? So the tools are designed to do that, but in the Managed VMs demo, I don't know if you caught this, but I'll just reiterate this again. The stuff that Brian installed with apt-get, he could have also specified in the app.yaml file, right? So once you figure out, so let's say there's a version of, I don't know, OpenSSH that you want to install on the VM, and the version you have is not working. You debugged, you found a version that works. You just go back, update your app.yaml file, right? And you say, I want to use this version. The next time around, you have the right version on all your VMs. So if you manage it declaratively rather than configuring on the fly, you'll have a much better running application, and that's kind of the goal here. Does that help? Thanks.
I was wondering if you could talk a little bit about dependency version management. Like if the Python OpenCV library were to have a new version, it seems like you'd be creating snowflakes if one of them gets rebooted and gets the new version of the library versus the other VMs. And maybe it breaks some dependency tree that you have, that some library call that you make, and so only that instance is broken. I'm wondering if you can talk about that a little bit.
So in that case, though, you would actually be installing the version of OpenCV. So you would say, I want to have OpenCV, and you could pass in, I want to have OpenCV 3.1 or 3.2 or 3.3.
So you can pass in a version number and pin it. Okay.
But then there's actually another good point. Actually, I don't know if you meant this, but I'm going to kind of tease it out of there. That, again, because you're running on the deployment infrastructure that we have, and you can do things like versioning very easily, you can say, you know what, I want to test out version 3.2 or 3.x of OpenCV. And I want to do that with a new version that's not my default version, right? So all my live traffic here is running back to what I know is good. I want to canary a new one. I'll do some QA, do some integration testing. Things look good. Flip the bit, and now you've got all of your traffic running to the new updated OpenCV or insert open source technology there.
Yeah, and I just want one more fine point on that. I mean, this is when leveraging something like the container technology that was mentioned earlier can really come into play, because now you have essentially an artifact, which is that container image that really encapsulates everything about your application that you're interested in. And so those things work really well together in terms of trying to actually specify all the versions down to the umpteenth degree that you're actually working with.
We have a question in the back there? While he's making his way back, I want to highlight another fine point there too, that while you can specify the technology you want to run on these managed VMs, you can also take advantage of App Engine's managed runtimes. So Java, Python, PHP, et cetera, et cetera. And in that case, we actually will do the updating for you, right? So if we realize that there's a security patch that we need to update for that runtime, we can do it for you just like we've done in the past. So I don't know if everybody knows, but if you're a Java developer on App Engine, back over this last summer, we did an update from Java 6 to Java 7 on the behalf of developers. We upgraded millions of applications in situ, like in real time. And we did that because we could actually do a clone of it, do some canarying, run some tests, run some anonymized traffic back at those things to make sure everything was working. And then when we felt comfortable, roll that deployment out. And we're going to make that available as well within managed VMs.
So this is a quick follow-up to the question about version packages. What's the default behavior if you don't specify a version? Are they upgraded, and are some machines, some VMs?
So we don't do anything special there. It's like it's the same. It's whatever the repository that you're fetching the libraries from, however it behaves. So it's probably going to get the latest in that case.
So as new VMs are spun up, they may have newer versions, so you'll have differences.
So for full circle, we should update the demo to include the version.
Yes.
Could you comment on what the experience is going to be for the developer in terms of dev server and managed VMs?
Yes. So again, I could go into it. I would suggest that you check out the 2:30 session, Runtime Yours. They're going to talk about ways that we can make that happen, because it is a very intrinsic issue and how you want to handle it, because you've got dependencies and things like that. Containers actually play into that as well. And some of the technologies that are evolving in the market today, we're looking at how we can leverage those. And again, we kind of do some foreshadowing in that session. I don't want to just punt, but it's a pretty deep answer. We had somebody in the back, I think.
I think this might be the last question.
So on performance, so great, perfect last question. Performance related, do you envision any future extensions or APIs for doing things for high performance computing? For instance, pinning threads to cores to optimize L3 cache management, just understanding what's happening at the lower levels, mechanical sympathy kind of programming.
So I don't have any sort of specific details to share, but I just want to say that HPC is a very interesting workload to us. We're definitely looking at what we can do to make it work as well as possible on Compute Engine.
Awesome. Anybody else? We have 50 seconds. 49, 48, 47.
One more.
Oh, one more right here.
I know there's like a big emphasis on Git. Is there any support in the future for Subversion?
Okay, so the question was, Git and GitHub are great. What about Subversion? I don't know the answer to
We
that.
don't have anything to share.
Sorry.
I think I see a guy in the back that I can connect you with that might have an answer.
All right, I think
Thank
we're
you so much for your time.
Thanks for coming. Thanks for watching online.
Thanks for running around.
Thanks.
You're running a compliant.
updated one?
Yes.
Great, okay. So, we're ready to go?
I guess they need the title slide.
Back to slides. First slide. This is it.
No. Slide 4? There you go. Okay. I'm on. Hi, everybody. My name is Eric Johnson. I'm a technical program manager. I work on Google's Compute Engine team up in Seattle. And I thought I'd take 25 minutes of your time today to talk a little bit about Google Compute Engine and open source technologies. Over this last year, as you saw previous session and probably heard earlier in the keynote this morning, Compute Engine last year in 2013, we went all the way from invite only, and then in I/O we went to open signups, and then in December we went to general availability. So during that last year also, I and several of my colleagues worked on contributing code and documentation to some popular open source packages out there, so that if you're already using those technologies, you'd be able to go ahead and use those with Compute Engine as well. But before I get into the specifics of what we've done there and some of the projects we've contributed to, I wanted to talk just a little bit in general about how Google uses open source and how we're effectively built on top of open source. It would be incredibly challenging for Google to exist as you know it today without the foundations of open source technology and open standards. We serve hundreds of millions of users across Gmail and YouTube and Maps, and none of that would be possible without the ability to be able to get in, kind of roll up our sleeves and take a look at the source code of some of the technologies that we use, make modifications to that stuff, and try and squeeze out every ounce of performance and scalability that we can. So, there's other alternatives, obviously, right, besides open source. There's other closed source binary distributions or binary packages out there that you can use. And so I guess as I think about sort of maybe the differences between the two, a good analogy to me is painting, right? So if you're a painter and you start off with a blank canvas, you have a couple of options, right? You can choose what your subject is going to be. If you want to do a portrait or a landscape, you can choose between different styles like abstract or expressionism, impressionist. And kind of sort of the sky's the limit, right? And as you go through, maybe and you're working on your masterpiece, I think one of the things that's great about open source software, which fits in well with this analogy, is the ability to be able to sort of make your own modifications to it. So I kind of, as I was going through looking for pictures, this one kind of struck out at me. And I was thinking, as Rembrandt's sitting here painting this, he's looking at this and he's like, you know what, I've just finished this great big masterpiece. And with the exception that I think is a little bit too formal. He originally had a hat on everybody. And he thought, all right, well, it's the 1600s. I'm going to make it a little bit more casual, kind of laid back. So he just painted over the hat on one of the drapers pictured here. So that's an example of being able to take and start off with whatever you want and be able to make modifications to it. If I were to contrast that with sort of the closed source world and binary packages, you can still create a painting, right? But maybe your options are a little bit more limited. So you don't, maybe the paint by numbers is a good way to think about that, right? You are given a set of software to build out your technology, but you don't have as much flexibility. The design is already chosen for you. The color palette may also be chosen for you. Even the arrangement of those colors might be chosen for you. And you don't have the ability to be able to go in and make modifications to it. So, at the end of the day, you can still finish up and you'll have a decent painting, but you just don't have the flexibility to kind of make it your own. So how does Google use open source software? So first and foremost, we use Linux. There's tens of thousands of Googlers employed all around the world. And every one of those Googlers runs, well, a very large number of them, let's say, run either Linux or a Unix derivative, right? Unix had its sort of roots in open source. And all of us pretty much use that. There's utilities installed on our laptops and our workstations that are all open source, like sed and awk. These are utilities that engineers use every day, all open source, right? It enables us to do our jobs. But not only do we run Linux on our laptops and workstations, but we also run it in our data centers. So every service that you use at Google is powered underneath that by Linux. Another way that we use open source is our development environment. We use popular open source programming languages like Python or Go. A lot of the things that we do to get our job done on a day-to-day basis, right? We're working on source code, we're making modifications to that. We use open source integrated development environments, IDEs. We use open source text editors for modifying source code. We use open source version control to record changes that we make to the system and have that sort of history of changes that we've made. Compilers that we use to compile the software, all of that is open source as well. But open source has a lot of its roots, and the ability to be able to develop open source software is based on open standards, right? So these are standard organizations that have gotten together and defined in the open how a certain thing should work, the characteristics of it. And then a lot of times they'll create reference implementations based on those standards. So if you think about the presentation that you're watching today, whether you're here locally or you're watching it remote over YouTube, there are a lot of standards that are involved. The original content of this, this is done in Google Apps, in Slides software. All of that data actually lives someplace in a Google data center, right? And it's being served out over the network. The network is defined by open standards. You have protocols like TCP, IP, and DNS and HTTP in play. All of that has been defined as open standards. Even the content on the slides, the images that you see, the content of the slides itself, that's being displayed via HTML, CSS, JavaScript. Again, all things developed off of open standards. Even the text on the screen, right, are character encodings for Unicode or ASCII. Again, open standards. Even just displaying this stuff uses HDMI, DVI, VGA, or something like that. Also, video encoding over the internet, right? H.264. Again, all open standards. So Google clearly benefits from open source software. Like I said before, everything that we've done is built on top of open source software, and we really wouldn't exist in the way that you know us today without that foundation in open source and open standards. So clearly we're benefiting a lot, but does that benefit you at all? Well, you know, one of the key foundations of open source is collaborating with others and sharing those modifications back and forth. And Google does participate in that as well. So last year, Linux Foundation, well, every year they publish a report called Who Writes Linux. Last year in 2013, Google moved up into the top 10 contributors, corporate contributors to the Linux kernel. And you might think, okay, yeah, Linux kernel, Android runs Linux kernel, it's probably all Android development, right? Well, in an article published by Ars Technica, they interviewed Greg Crowe-Hartman, who is the Linux stable maintainer, Linux kernel stable maintainer. You know, and Greg was quick to point out that Google is really doing work all over the kernel. In fact, you heard, if you saw Joe, the previous session, Joe Bita mentioned that we contributed C groups. I think that was back in like 2007 and 2008. And that's sort of the underlying technology behind containers and some of the technology that you see out there in the open source world like Docker today. So not only are we contributing to, actively contributing to the development of the Linux kernel, Google also, through stipends and mentorship, has a Google Summer of Code project. And what that is we do pay stipends to students to contribute to open source projects. Google Summer of Code, I think, was started around 2005. And since that time, through that program, we've contributed over 50 million lines of code to over 400 open source projects. So those are examples, those are great examples of Google contributing back to existing projects. Some of you are probably already also aware that Google does initiate a lot of open source projects. So to name a few, obviously Android, everybody I'm sure has heard of that. Chromium is a foundation behind both Chrome web browser as well as Chrome OS. The Go programming language, the V8 JavaScript engine, which really is the thing that makes Node.js sort of under the hood, makes Node.js possible. So all of these are developed, were initiated by Google, open sourced from the beginning. They all have very active contributions, not only from Googlers, but also from other external corporations and even external developers that are interested in the technology and want to participate in it. So let's talk a little bit about Compute Engine also. So lots of announcements today with Compute Engine. And as we mentioned, because it's a Google service, it runs on top of open source software. So some of the open source software that we use to power Compute Engine, obviously it runs on top of Linux servers in our data centers. And we use KVM as our virtualization layer. We provide a public API, and that's defined by open standards, right? It's an HTTP REST API. So there's nothing sort of unique about that. There's nothing proprietary. It's completely open based off of standards. Even the images that you can launch, the virtual machines that you can spin up, the operating systems that we supply by default are Debian, CentOS, Red Hat, you saw, RHEL, and SUSE. FreeBSD, you can even spin up your own images as you probably heard in the previous presentation. So again, open source technology through and through. So now we're kind of ready to get into some of the work that we've done for open source projects that are out there that do support Compute Engine. And kind of the best way I think to probably start this off is just sort of let's use the hello world of Compute Engine. So what I have up here is 13 lines of Python code. And what this will do is create a single virtual machine in Compute Engine. And this uses the open source Python library. It's an Apache Software Foundation project called libcloud. And it's a multi-cloud library written in Python. So you can use this with other cloud providers as well. So recognizing that there might be users out there that would be using another provider that maybe would also want to try Compute Engine, we went through and we contributed code and documentation, sample scripts on how you, if you're already using libcloud or an application maybe that's even built on top of a libcloud, can go in and basically make some minor configuration changes for authentication. And by and large, it should probably just work. You may have to make some customizations there in terms of the machine size or the location. But otherwise, it's same concepts that you would get using libcloud with any other provider. But maybe Python's not your thing, right? So maybe you're a Ruby developer. Well, fortunately, there's another library out there that's very similar to libcloud in that it works with multiple providers. And here I've got a snippet of Ruby code, which does effectively the same thing. In fact, the code almost looks identical. This FOG is a open source library, all in Ruby. And again, you can use that with multiple cloud providers as well. And this is another example of where Google contributed code back over to the FOG open source community to make sure that any FOG developers or applications that are built using FOG can now also use Compute Engine. So, but there's this other language out there called Java that's very popular. And there happens to be another open source project very similar to both libcloud and FOG that allows you to work with multiple cloud providers. And so here I've got 12 lines of code. This one's a little bit different in the sense that this code snippet here uses, and this is a JCloud's sort of idiom, that they have templates that you define where you set the node attributes or the instance attributes that you want to create. And so here I'm just assuming that I'm using the default and that those are sane values. It's probably a single core machine type, and hopefully it's in a region that's going to be close by. But these are all attributes that I could modify and change, and then I can specify my exact environment that I want with JClouds. So again, as I had mentioned, Google had contributed to code. With the exception, I think, of JClouds, we've kind of poked at it a little bit and offered some help here and there, but by and large, this was done by the community itself. So I just showed you that you can use programmatically, right? You can create your own virtual machines and spin those up. And that's great, but now you want to put them to work, right? So the next thing that you would do once you have your instance up and running is you probably want to go ahead and put your own software on it or run a service on it. And the way that you would normally do that, I guess just sort of out of the box, is you'd probably SSH into that. And you'd, since they're all open source Linux distributions, you'd use your package manager to pull down your packages, deploy your application, and get it configured. And I think also you saw in the previous talk, if you saw that one, we talked a little bit about snowflakes, right? So you're going to spend a lot of time tuning and tweaking this, right, and getting it just right. But then the next time that you want to go and do that, you have to kind of remember, like, oh, what were all those packages I had to go, or how did I get around that one particular dependency? Oh, yeah, that's right, I had to compile that thing from source. So there's a lot of things, right, that you want to make and turn into sort of a repeatable process. There are a lot of open source configuration management tools out there that you can use. And all of these now, through code contributions by Google, support Compute Engine. So the two biggest ones that you probably have heard of, Puppet and Chef. But then there's also newer ones that are coming up, SaltStack and Ansible. And again, all of these support Compute Engine. So you know, tying back into the previous conversation about the, you know, getting away from snowflakes, right? All of these tools allow you to create a configuration that represents the desired state of your server or servers, your virtual machines in the cloud. It's like a declarative syntax. It just says, it doesn't tell really how a machine should get itself configured. You just say, here are the services I want, the packages I want, the users that are created, file permissions, anything that you can think of that you would normally do through just manual one-off commands, you can capture in a configuration file. Those configuration files can be versioned, so you can track changes to that stuff. If you make a mistake, you can roll it back. They're all strive to be idempotent, so you can rerun the same command over and over again and tune and tweak it and run the same command, and it'll only install things that have changed, or it's a great way to try and like tune and get your environment set up just the way you'd like. And as I mentioned, Google contributed a lot to the development of Compute Engine support into these. There's a lot of other open source packages out there, and here's some of the other popular ones that we've come across. In some cases, Google has contributed either directly to the project or through code or just through documentation. Like Docker, I think, for instance, one of our developer advocates put together a nice clean set of instructions. It's like 10 lines of code to get up and running with that. CoreOS has an image that you can put into your project, and you can run the CoreOS image right inside of Compute Engine. Vagrant is another tool that you can use to kind of quickly spin up a development environment, and that works with Compute Engine. And Packer is another project that allows you to sort of bundle up your image and get it customized the way you want, and then reuse that. So let's flip over to a demo. So we should have a terminal come up here in a second. And let me just cat out this file. So this is very similar to the little hello world example, right, in Python that I showed you before. The only couple of differences here to call out, obviously lines 5, 6, and 7 have my authentication credentials in it for my project. But the only, one of the other differences here is on line 11, I'm going to use a wrapping function that we added to libcloud, which allows you to create multiple virtual machines with a single method call. So rather than having to re-execute the single create node inside of a while loop, we sort of do all of that for you. And let's see what else. Oh, so I've got it hard-coded in there on line 14 that we want to create 100 virtual machines. And then on line 16, what we'll do is we'll print out, that'll return an array of created virtual machines. And then so on line 16, I'm going to print out sort of the length of that list, and hopefully that comes out to be 100. And then how long did that take? So let's just go ahead and run this. So let's call this, hello world times 100, I guess. So I'll flip over to the developer console here, and you can see this is the demo virtual machine that I was on when I executed that command just now. So we should start to see a couple instances spin up. Okay, so flipping over to the disks tab, our virtual machines now use persistent disks. That's your only option right now. There is no ephemeral disk or scratch disk. So what this has done is it's created the 100 persistent disks. Each is 10 gigs in size, and each has the Debian image loaded on them. And then we also have the 100 instances that are being created. And so each of those instances, it's matched. I should have pointed this out in the sample code, but I give it a name prefix of LC for libcloud, and then it just depends on an auto-incrementing integer for each instance it creates. And then that also matches the name of the persistent disk, and so then that's what it uses as its boot disk. One thing I'd like to point out, as you're getting up to speed with Compute Engine, and you want to learn our API, there's a couple things. So what I did here is I drilled down into just one of these instances, in this case LC001, and I'm scrolling down and I'm looking at some of the attributes on it. But down here at the bottom, we have a couple hyperlinks that you can click on, and this will show you the exact REST API that defines this instance. And so that's a great way to learn the API. And then there's also, Compute Engine provides a command line utility called gcutil, which is part of gcloud. And this gives you the exact SSH command that you can just cut and paste to SSH directly into that machine. So I wanted to call that out because that's a great way to get up and running with Compute Engine. Just kind of quickly drilling through some of this stuff, snapshots. You can, from a persistent disk, you can create a snapshot off of that. And snapshots are stored globally. So this is a great way for you to replicate data around. You can create your instance, customize it the way you want, and then take a snapshot of that persistent disk, and then bring up another persistent disk, let's say in Europe, and an instance based off of that, and you've just replicated your instance over there. So let's go back to the instance list. And if we scroll all the way down, hopefully we'll see down to 99. So let's find out how long did it take us to create a 100 virtual machines. So 100 in 1 minute and 27 seconds. And these, again, they're all Debian images. You can SSH into any one of these, and we had 100% success in less than 2 minutes. So if we can flip back to the slides, please. So what's next? So there's a lot of things that came out today, right? So as we've been working to contribute code back to the open source community for supporting Compute Engine, we're always iterating on things. We're always changing things. And it's a difficult job to kind of keep up with that. And it's a small group of us within Google that are kind of contributing some of our part-time work to this stuff. And in the spirit of open source, we'd love to collaborate with you. You can find me on GitHub, ERJonso. And if you have a project that is an open source project out there and you'd like us to see maybe kind of help you out either with some guidance or even some code or documentation, feel free to do an app mention on your project and kind of bring it to my attention. And if it's not something that I can personally take on, there's a lot of people that work at Google, and I might be able to find somebody that can help you. I'd also like to point out we have a GitHub organization called Google Cloud Platform, and there are a lot of great repositories set up there that are samples, applications, demos, that type of thing, across all of the Google Cloud Platform services. So I really encourage you to check that stuff out. And I'd like to thank you for your time. Sorry. Is there going to be any VNC support in the console? That's a good question. I don't know the answer to that. I would think with Windows coming up, we probably want to make sure that you have some capability of getting to it. But I don't know specifically. OK. I don't think there were other questions. OK.
All right, I think we'll get started. So I'm Mike Deline. I'm an engineer working on Google Cloud Platform, and I'd like to take a few minutes to talk about some of the things that makes our cloud stand apart. The common theme you're going to hear today is that we're built on Google. This means that being an engineer on this project is a fun job. To take to having a great global network that will go to the ends of the earth, will go even beyond the ends of the earth, put lasers down and fiber down with where the sharks are to ensure that we have that great global connectivity that so many of our products depend on. So number 9. Let's see if this will advance. Free, fast connections to Google. So when you build on Google's cloud platform, one of the great features you get is the rest of Google. Right, we give you high performance, low latency, high bandwidth, and no charge connection to other Google APIs. Other Google services like Ad Exchange, YouTube, Drive, Docs, Apps, the Maps API. This makes Google a great place to build real-time bidding, a great place to build video processing. Right? You can do your processing and upload immediately to YouTube. A great place to build productivity apps, interactive apps, collaborate and work with Docs and Drive. A great place to build geolocated services. All right, so there's a wide range of other Google properties and Google services that can make your cloud applications better. Number 8, Google Scale. So Google understands scale. And when you build on Google Cloud Platform, you get to take advantage of the technologies we've built that allow us to deliver services at scale. Not to brag, but what you might regard as a success disaster is likely something that we handle every day. As an example of this, we ran an experiment where we took, set up on the cloud platform a bunch of servers. We put a load balancer in front of those servers. And that load balancer is the same infrastructure that we use to deliver our other services, so it knows how to scale. We then fired up a bunch of clients. And we just had them start blasting at the server as hard as they could. They were delivering 1 million requests per second. So with no pre-warming, no warning, just turned on the load balancer and fired up the clients. Within 4 seconds, those clients were ramped up. They're firing their 1 million requests per second at the server, and the load balancer is handling it. Okay? After about a minute, there is a little bit of an adjustment as things rebalance. That all steadies out. Even during that time, you're getting very good throughput. That all steadies out, and by 2 minutes, things have gotten completely boring. Right? And the requests, 1 million requests per second just continue on. This entire experiment cost us less than $10. That was prior to the price drop, so it would cost even less today. Which means that this technology is something that really anyone can have. Now, not everyone needs to handle 1 million requests per second. In fact, that's fairly unusual to do. The way to think of this is as an insurance policy, at least for most applications. Right? You may not need 1 million requests per second, but you may not know exactly what you're going to need. And so what you can do is build on Google Cloud Platform and know that the infrastructure is capable of handling whatever you throw at it, whatever your customers throw at you. You've got an underlying infrastructure that knows how to scale. An example of this we saw last year at the Eurovision song competition. Our friends at Scalar worked with Eurovision. What they wanted, so Eurovision, Eurosong, if you're not familiar with it, is one of the most popular television events in the world. Basically, if you don't look at sporting events are very big, but then behind sporting events, this is really right up there. They see about 125 million viewers each year. It's a big event. They decided last year to start an app for a second screen experience. But they face this problem, right? How many users are they going to get from the app? How much load are they going to get from the app? Right, you've got 125 million viewers. Are you going to see 100,000 users, 1 million users, 10 million users? It's hard to know ahead of time. Right? You're launching a brand new feature, really hard to predict what's going to happen. So they took advantage of the flexibility of the cloud platform, the scalability of the cloud platform, to deal with the fact that they had uncertainty about what they were going to need to do. Because they're on this platform, they were able to deal with, for example, in one phase of the competition, they saw load spikes of about 5x what they were originally anticipating, and that wasn't really a problem. They could just scale up the extra capacity. It took a couple minutes, and then they're serving everything that they're able to handle that load. By the finals, they were dealing with 50,000 requests per second and serving those requests with a 99 percentile latency of under 35 milliseconds. Right, so really great performance, great scalability, and they're able to successfully deliver this new application. Let's go to number 7. Google's cloud is green. So this might matter to you because you're green too. And you'd like to have a cloud provider that thinks about these things. Nothing else that you don't have to worry about making your data center green. Let Google worry about these things. Let Google worry about being very efficient and finding resources of energy. Green is something that's very deep in our values, and it's something that we've worked on and invested heavily in over time. As an example of that, this upper right picture is from the Ivanpah solar thermal plant that just went online earlier this year in the Mojave Desert. Ivanpah is, if I remember right, a 392 megawatt generating plant. So that's enough green energy to power over 100,000 homes or dozens of 10 megawatt data centers. Another example here, this is one of the wind farms that we source some of our renewable energy from. And there's a bunch of these. You can go to our website to see more examples of that. It's just another data point. Google as a company has been carbon neutral since 2007. This is something that's deep in our values. We think it's very important. But, being green is all well and good. But at the end of the day, some people just have green eye shades. And my argument is that this should matter for the accountants as well. Right? That by putting these types of investments in place, we're able to lower our costs of energy. We're able to insulate ourselves from volatility in energy prices. We're able to insulate ourselves from potential increases in the cost of carbon over time. And so this is the type of thing that has allowed us to reduce our costs and pass those savings on to you, as you saw earlier today, as we dropped our prices. Let me give a concrete example of how the accountants should love a green cloud as much as we do. So what this graph shows is the power utilization effectiveness across Google's data centers, across our entire fleet. It shows that year by year, since 2008, the power utilization effectiveness is a measure of data center efficiency. What it measures is to deliver 1 watt of power to the compute infrastructure, how many watts do you need to actually put into the data center? Right. So in 2013, our power utilization effectiveness, our PUE, was 1.12 over the year. That meant that over 88% of the energy that went into a data center actually went to the compute, the storage, and the networks, the things that you actually care about. Less than 12% was spread across cooling, across electrical transformation, across electrical transmission losses, even across keeping the lights on in the data centers. All right, so this is a pretty remarkable achievement. If you look, for example, in 2012, that's the last year I've got data, the average across the industry, the PUE was about 1.8. So on average, in industries, and probably those of you that walk into a typical data center, the big crack units are running. This is not too surprising. On average, almost half of the electricity that goes into a data center goes to these other types of overheads. Google's able to drive that cost down through really long-term investments in building state-of-the-art data centers, has been able to drive that down to 1.12, where 88% or better of the energy is actually going to what you want. Number 6, supercharged disks. So physical disk drives really haven't changed much since the late 1950s when they were invented. You've got some spinning platters, you've got an arm that you move back and forth. They're getting bigger, they're not getting much faster. Moore's law is great for moving and storing electrons, but it doesn't really do much when you need to move a piece of metal to read your data. And as disks have gotten bigger, you get fewer IOs per gigabyte. Your data becomes trapped inside of these disks. PD, persistent disk, is the disk drive system, the block drive system that we provide as part of Compute Engine. Instead of relying directly on this kind of ancient technology on the left, it's built on Colossus and Spanner. Colossus and Spanner are two of the large-scale data storage systems that we've built inside of Google, right, for storing lots of data, spreading it across a bunch of disks, and reorganizing that data for more efficient access. As an example of what you get by moving from the old physical device to our new virtual device, if you take a 2 terabyte physical hard drive and compare it to a 2 terabyte persistent disk, both of them can get very good sequential read and write bandwidth. If you're not having to move the metal, you can do pretty well. But as soon as you start having to move metal to read your data, to do random reads and random writes, traditional disks really fall down. You can get dozens, maybe 75 read and write IOPS, whereas on PD, with this ability to reorganize the data for more efficient access, with this ability to parallelize the access across large numbers of underlying physical devices, you can do 8 to 32 times better. All right. Some other advantages of our PD device, virtualizing this old technology, first of all, you can move PD between machines easily. Right? So you don't have to pull out the disk and put it somewhere else. You send a command, you hook it up to another machine. You can actually simultaneously mount a PD device across multiple virtual machines. So in this example, we've got a web service, a bunch of clients are accessing it, we've got a load balancer that spreads the load across a bunch of Compute Engine front ends. They're all sharing the same back-end storage, right, of all the data that they're actually serving. This is nice because it saves you money. You only have to pay for the data once, to store the data once. And it also can simplify your administration. You do one update, and all your different servers can see that update. You don't have to keep a bunch of copies in sync. Another nice thing about PD is that there's no separate charge for IOs. This goes to the theme of trying to give you a simple model to think about pricing. Right? So we think this makes sense, that when you buy a physical disk drive, you get not just the platters, but you also get the arms. You don't have to buy the arms separately. We're going to do the same thing with PD. When you buy PD, when you rent PD, you get the IOs. There's not going to be a separate charge for actually using those arms. Right? This is both simpler for you, but it also makes it easier to predict your bills. Right? You don't have to try to figure out, OK, I've got a bunch of web servers. How many IOs per month are they going to do? So you can predict what your bill is going to be. Instead, when you buy the PD, you look at the size, tells you what the price is going to be, and you're done. Finally, just another nice property of PD, and there's a bunch of others, you can go read more about it, is that we get rid of some of the limitations of the underlying physical devices. So for example, if you've got a big database, you want to put 10 terabytes for your database onto a single volume, that's something that we can accommodate. No problem for us. Number 5, consistent performance. Multi-tenancy is hard. Right? When you build a shared infrastructure and you want lots of diverse applications to use that infrastructure, you have this challenge of making sure that one application doesn't interfere with another application. Google has lots of experience dealing with this problem. Right? We've been running multi-tenant data centers for a long time, and we've built up a reservoir of technologies that we use internally and now we can use in our cloud to help provide that type of isolation, to give you consistent performance. We've built cluster management systems and schedulers in Borg and Omega that help us provide this type of isolation. As was just mentioned in the earlier talk, We've been really some of the pioneers in containers and contributed some of those techniques back to the open source community for isolating different groups of Linux processes and giving them consistent performance. We've been pushing the boundaries of software-defined networking and taking advantage of that flexibility to improve the isolation in our clusters and across our clusters. As I mentioned a little bit ago, we've built internally a big collection of shared storage systems, Spanner and Dremel and Colossus. And those systems have been designed to allow different applications to take advantage of a shared service, but get the consistent performance that they need. And then finally, we've just built up over the time operational practice and tools. Right, we've got the tools to monitor what's going on, to react when we see something that's not right, and to fix those problems and improve our systems over time. And we've been doing that to get better and better consistency, both internally and now externally. We hear over and over from our customers that they value this type of consistency. This is one example of one of the quotes, but we hear this from a lot of customers all the time, and it's something we take pride in and think is a really important thing to be delivering. As an example of the types of things that we do to improve the consistency of our service, I just wanted to show this very recent example. Okay. What this graph on the right shows is what kind of performance do you get for the CoreMark benchmark as you spin up 2, 4, or 8 CPU virtual machines on the platform. In the left-hand side of each pair of these is what we've been delivering until recently. These are all, these are called violin graphs. This is a violin graph. And so the way to read this is you can look at one of these clusters of points. It says it's 4 CPUs. And the thickness at any given level is basically a histogram. The number of samples, the number of machines out of the benchmarks that we ran that delivered this level of performance. Okay. Ideally, what you'd see would be perfectly flat, thin lines, right, for each of the configurations. And you know, we're pretty good if you look at our kind of recent version of the system. So for example, if you look at the 4 CPU case, the vast majority of the VMs that we spun up had an expected level of performance. But there was a little bit of a tail, and every once in a while we got an outlier going one way or the other. This is probably not something you'd notice unless you were looking pretty carefully, running a lot of VMs. But it is something that we detected. One of our engineers noticed this and thought this is not OK. Right? We want to have consistent performance. This engineer spent several weeks, actually a couple of months, tracking down what was going on, did a bunch of statistical analysis, found out when did you get better than expected performance, when did you get worse than expected performance, tracked it down, found an issue in the scheduler, and was able to provide a better scheduler that gives us the performance shown on the right. Well, we're very nearly back to that ideal of a perfectly flat, thin line when we spin up these machines. That change has been rolling out to our clusters over the last couple of weeks and will continue to roll out over the coming weeks. And so if you've been happy with the consistency of performance that you've seen in the past, it should be getting even better in the future. Now, this may seem like a small thing, right? I mean, the vast majority of the time in the past, it was working just fine. Those tails didn't happen very often, and a lot of people probably wouldn't even notice them. But if you ever try to debug a weird performance anomaly in your system, right, you've got enough problems with your own code without that underlying system shifting underneath you. Or even if you're just trying to do something as simple as predict the number of virtual machines that you need to serve a given level of load, you really want to know what each of those machines is going to deliver. That's something that we value. We've learned how important this is. We've got some great engineers working to make that better and better over time. Number 4, security. So this picture was taken at one of our data centers a couple years ago. It was posted to Street View. It perhaps tipped our hand a little bit more than we intended about how far away we're willing to go, to improve our security. But suffice it to say, we take security very seriously. We physically protect our sites with fences, barriers, guards. We have strict access control. My badge will not get me into a data center. And we have video surveillance with both human monitoring and also programmatic monitoring, programs that actually analyze the video, detect anomalies, and raise alarms so people can have a look and figure out what more needs to be done. We do automatic encryption at rest across PD, Cloud Storage, and Cloud SQL. This is something that you don't have to configure anything. The data gets encrypted automatically. We provide secure communication with both physical security and encryption across our various networks. I have a growing list of certifications, kind of attesting to the sorts of things that we're doing. Here are some of these. But I think just broadly, the thing to understand is that, again, high security is something that Google as a whole depends on. It's part of our values. It's something that we work on all the time. We intend to lead and drive security for the industry. We depend on it for all of our other products. We provide it in cloud, and we take securing your data as seriously as we take securing our own. Number 3, 0 to 138. Okay. So this graph is, again, another violin graph, in this case showing the time that it takes to start up VMs that are part of various sizes of clusters. Right, so we start up clusters of 1, 10, 25, 50, 100 VMs. And then what the violin graph is showing is the histogram of how long it takes for each individual VM to get started. We run this trial a bunch of times to get a distribution. The histogram shows that. All right. So the first thing that you might notice is that spinning up a single VM is fast. Looks like the first ones are showing up. Typically, one will show up in 21 seconds. In all of our experiments, they showed up between 21, 22, and 23 seconds. Right, so the VMs come very quickly, and that's from the time that we say go until you can SSH into the VM. The second thing you're going to notice is that spinning up a bunch of VMs doesn't take much longer. So in the case where we kick off 100 VMs, spin them all up at once, again, we measure how long until individual VMs arrive. And in this example, some of the VMs are showing up as quickly as, looks like 18 seconds. All of them have arrived in all of our trials in 38 seconds. And so you can spin up a bunch of VMs, and it comes very quickly. What this lets you do is adjust to changing demands. Right? As the load on your system changes, the resources you're using to serve that load, you can quickly move up to match what you need to do. It was this type of agility that our friends at Scalar used to help Eurovision meet their demands for the Eurosong contest that I talked about earlier today. Per minute. So as some of you may know, we have a sister business that sells ads. And a big part of what they need to do to make that business work is microbilling. Right? And so once again, we've taken technology and institutional experience and applied it to our cloud to improve our platform. So in particular, we offer per minute billing with a 10-minute minimum for our compute engine instances. Now, this will both save you money, especially for very short running instances, but any time that you're running an instance and it doesn't take exactly an hour worth of work. So if your work takes a little more or a little less than a certain number of hours, you're going to save money with this per minute billing. What this graph shows is on the x-axis, the number of hours that a VM runs, on the y-axis, the price that you get, the cost that you pay to run that VM. And as you can see, being able to pay for just what you're using can actually result in some pretty significant savings. Again, this gives you more ability to, 1, deal with changes in demand, but also 2, take advantage of our scale. So for example, if you're doing an analysis of a big data set on Compute Engine, so you're spinning up a big Hadoop job, rather than run on 100 machines for an hour, run on 600 machines and get the same answer for the same price in 10 minutes. Finally, number 1, if per minute billing is, renting our infrastructure by the minute is cool, renting it by the second is even better. And that's effectively what you're doing when you use the BigQuery service. What BigQuery does is it spreads out analysis of your data across hundreds or thousands of machines without, of course, you having to manually shard it. We take care of all that. It allows you to use a familiar SQL-like query interface to this data across these massive data sets. This graph shows, this actually comes from the Dremel paper that we published a couple years ago to describe a lot of the core techniques inside of BigQuery, inside of Dremel at that time. And what it shows was that they were able to do an analysis of a trillion-row table, doing a top K query across that trillion-row table. And by spreading out the analysis of this trillion-row table across thousands of nodes, they're able to get their answers in under a minute. Now, of course, we didn't stop working on Dremel when we published the paper. we've continued to work on this system and giving you new features like the continuous queries that were described earlier today, so that you upload data, you can keep streaming uploads continuously, and as soon as the data hits BigQuery, you can issue your request, and now your queries are going to return answers reflecting that most recent data. So we developed these technologies as part of Dremel. Internally, it's a great tool, and we're really happy that now with BigQuery, you have access to this technology as well. So thanks for letting me talk about some of the things that make the platform special. We've been able to bring you some neat things so far, things from sharks to scale, consistency to security, from green to the rest of Google. And I'm really excited to be an engineer on this project because I feel like we're really just getting started. Thank you.
I just need offer ours. That's exactly.
Whatever they want.
Yep.
Totally
Anything
happy.
but music.
You go like that to the microphone.
I was.
had that screen up.
have an open mic.
I know, I don't want the music taping to have to pick up a lot of, like,
Then what I'll do
it's
is
really soft. Okay, you know what I mean though? I don't want to risk it press down. And just so you know, I'm gonna want to have a full post-mortem on this.
Presenter? Yes. And you're online okay?
Yeah, I've just been testing.
Are you going to hardwire in?
Mm-hmm.
Okay. All right, sweet. Thanks.
My name is Dennis Huo, and I'll be talking about the work that we've been doing to make sure that big data open source software runs smoothly and effectively on Google Cloud Platform. Now, I want to begin with the big questions underlying all of this, which are what exactly it means to run big data open source software on Google's cloud, and secondly, why that matters to you. Now, imagine you have an awesome idea for a web application. Maybe you've been talking about it for some time over lunch, and you decide to go for it. You code it up over a weekend, and you hit the launch button. Well, as it turns out, the rest of the world thinks you're onto something. So, somebody posts an article to Reddit, a Slashdot article appears, and before you know it, you have 1 million new users overnight. So what happens? Well, all too often, the story ends right there. Your server melts, and your users quickly lose interest in your service unavailable site. But let's hit the undo button. Suppose you went with Google App Engine, and your app scaled seamlessly just like you intended. So now you have 1 million happy new users. So what's the next step? Well, as it turns out, life likes to throw curveballs at you. So you see bots and spammers show up, flooding your forums with junk and driving your users away. Now, when you only had like 10 users, it was pretty easy to just eyeball the logs and ban a couple IP addresses and be done with it, right? But somehow, as it turns out, eyeballs just don't scale to 1 million users. And your computer now refuses to load the terabytes of log files that you now have. So you might find yourself reinventing the wheel. You might write a quick program just to process those logs automatically, try to catch these spammers. Maybe you'll find you need to run on multiple machines, so you'll write a controller program to automate this, right? So what began with a day's worth of work quickly ends up with you just discovering a week's worth of work. And a week later, you're a month behind, and in the meantime, your website has become a lost cause. Well, let's hit the undo button again. What if you didn't have to reinvent the wheel? What if, with just the click of a button, you had all the tools you need to solve your spam problem before lunch, and you could spend the rest of the day building the next killer app, building the next feature for the next 10 million users? What if you really could scale from a garage size to Google data center sized overnight? As it turns out, that's exactly what running open source big data software on Google's cloud is all about. Now, just to get into some of the mechanics here of actually running on Google's cloud, there are two big pieces to this puzzle. On the one hand, we have making the most of Google's infrastructure offerings. Now, traditionally, if you've invested heavily upfront in a lot of hardware, you'll end up with all these machines of a certain size, a fixed shape, and all too commonly, you'll find yourself wasting endless time and money building the software to try to fit this mold, trying to fit them into this fixed shape. In cloud, we turn this upside down. So you should write your software however it feels natural, write your software for your application logic, and then get the resources that match your use case perfectly. Perhaps the most egregious example of a fixed shape would be when you buy hardware, the time dimension is extremely rigid. You end up with this contiguous block of time for your on-premise hardware that is unbroken between the time you buy it and the time you're ready to throw it away. Well, in cloud, why not just get multiple disposable clusters instead, right? If you need to get some data analytics done today, why not run multiple clusters? Each analyst gets their own cluster to use by themselves and get your workload done now instead of having to wait in line. The second piece of the puzzle is making the most of Google's platform rather than necessarily just having to duct tape a bunch of little components together. And this is where we've been doing work to make sure that you have all the tools and libraries necessary to make it one seamless experience. We want you to be able to use your open source tools as well as higher value Google services like BigQuery and mix and match and have them interoperate seamlessly on the same data. And just to give an idea of what this looks like at a very high level view, let's go to the demo machine. So I'll explain a little more about what's happening here under the hood, but just to see what it looks like, I'm going to go ahead and deploy an 88-core cluster that's fully loaded with all the greatest data analytics open source software there is, and see how many. Sorry, I should actually type a command. Yeah, let's do that. And we'll see what happens a little bit later. So let's go back to the slides now. So, you might have noticed Hadoop was at in the title of the last slide, and we really are talking about all big data open source software here. But just to give a little bit of Hadoop, a little bit of Hadoop context, Hadoop has played a crucial role at being one of the very first open source implementations of the MapReduce paradigm, and one of the first such widely adopted software frameworks, which ultimately provided this fault tolerance and the machinery necessary to provide a really low barrier entry to starting to make use of large distributed clusters of commodity hardware. And this is really what enabled big data to really go mainstream and help it mature to what it is today. More recently, we see Hadoop serving in a crucial capacity as a point of convergence. So what I mean by this is not quite sitting down to write RFCs, but what we have is some organic community consensus-driven convergence onto certain behaviors and certain interfaces that came out of Hadoop. And one specific example of this is the Hadoop distributed file system, where we see that as data and analytics grows, as the ecosystem grows with a diverse set of tools, all of these tools are able to promise interoperability with your data simply by virtue of implementing the Hadoop distributed file system. And that brings us to one product that we have today available and available for you to use now, which is the Google Cloud Storage connector for Hadoop. This is built on top of the aforementioned standardization by implementing the Hadoop file system interface. So what this allows is for you to install this connector onto your Hadoop clusters and to replace at least a portion or all of your data access needs using Google Cloud Storage instead of Hadoop HDFS. We provide tools for automatically installing and configuring this such that you can either run in a hybrid mode so that naturally you can take your time migrating what data makes sense to put on Google Cloud Storage together with HDFS, or for new batch workloads, it might make sense just to run without any HDFS altogether. And we have screenshots, but let's go to the demo machine. So live is always better. So let's go ahead and we have a Hadoop cluster open here with the GCS connector installed. So what we'll see here is, let's just create a file. Let's echo here. We'll just say hi to cloud and create hello.txt. So we can see, this file has been created on my local laptop, and we can go over here to Google Cloud Console and, nope, not a new folder. We want to upload this hello file through our familiar GUI interface. And as we can see, so this is the cloud portion. Everything worked just as we intended. And now what we can do is we find that we have the Hadoop file system shell is available in this Hadoop cluster, and we can just cat out that exact same file. I think I mistyped something here. And we see that we can access that same file the same way we would through the Hadoop file system shell, as we would through the GCS GUI, as we would through the GCS command line tool, gsutil. So let's return to the slides. So to summarize what we've seen, we have two axes of interoperability here. On the one hand, we have cloud interoperability, where we have the same access and the same behavior from all different cloud services. Importantly, this also means the same access for other Google Cloud services like BigQuery, which can interoperate by sharing GCS as the common data storage. The second axis is Hadoop interoperability, as we talked about, where we can unlock a really broad range of open source tools just by virtue of implementing this standard Hadoop file system interface. And that includes making GCS work with Pig, Hive, Spark, Shark, and numerous other open source technologies. What this ultimately means for you is a significant reduction in operational overhead, because now your data is not tied to any single location in terms of some set of disks, nor is it tied to any particular technological stack. So if you're tired of MapReduce and you want to try something new, your data is still there. You can start processing it in a new framework. Now, when the question arises of whether something like GCS can really be a feasible replacement for HDFS, performance often comes up. And I think there's really two real aspects to this question. First is the question of whether the networking technology is really progressing in the right direction, such that doing this would be feasible. And secondly, there's this question of relinquishing a little bit of that fine-grained control that you might otherwise have with HDFS, like little things like rack locality or replication policies. And I'm reminded of the first time I actually had an opportunity to write a lot of assembly code. I remember I was really excited going into it because it was this opportunity to try out all the clever hacks I always wanted to make it run fast. And it turns out, after the novelty wore off, it was actually fairly painful writing all this assembly code. But I do remember, after so many hours of muttering at the screen, getting it to finally work the way I wanted and getting a huge success. It was like 20% speed up. I later found out, sadly, that if only I had flipped the -03 flag on GCC, the original program already would have run twice as fast. Now, what I learned, aside from the fact that maybe I'm not the assembly guru I had hoped I was I learned to trust the compiler. I learned to trust the decades of experience, of expertise from compiler experts that have gone into it. Whenever Java happens to be the right tool, I feel rest assured knowing that my memory management is actually in pretty good hands. And when I use Google Cloud Storage, I know I'm taking advantage of an incredible amount of research and development that has gone into Google's storage technologies over the years. And Google Cloud Storage still might not be the right tool for every use case. But what's important is simply having the option to take a step back, let somebody else handle all the dirty, grungy work, because that's ultimately how you can let magic happen while you focus on building the features and products that you actually care about. Now that said, earlier this year, the technology consulting company Accenture actually released a study of the performance characteristics and total cost of ownership trade-off between on-premise deployments of Hadoop as compared to Hadoop on Google Cloud. And I'd encourage anybody interested to read the whole paper. It's quite in-depth with a lot of different dimensions of analysis. But what we have here is at least one sample out of that paper showing a realistic real-world workload where we have the red bars here showing a mixed data flow model where we use the GCS connector for the input and output of the initial and final stages of the MapReduce, still using HDFS as an intermediate store, as compared to the blue bars, which are just using local disk HDFS. And we see that we actually had a pretty encouraging speed up using the GCS-based, the GCS connector-based data flow model. The green line here at the top is the benchmark value of the bare metal Hadoop deployments from a total cost of ownership analysis. And we can see that across all dimensions, the cloud deployments outperformed. So lower values are better here. So I'm happy to announce that we've also been working on two other connectors, two other Hadoop connectors for connecting to Google Cloud Services. We hope that the data store connector will help you bring data analytics through open source tools to operate on the same data that you use in your web serving or that you generate. And we hope that the BigQuery connector will help aid the seamless interoperability between whether you started out just using BigQuery and want to use open source tools, or if you started out with open source tools and want to start using BigQuery, you should be able to go either way seamlessly. Both of these we hope to make available publicly in early April. Along with all these connectors, we also have a thin helper tool called BDutil, which helps deploy and install all this Hadoop software with a thin extensibility mechanism for customizing your software and mixing in more open source tools. And that brings us to what we'll demo here using BDutil of Shark on Google Cloud Platform. Now, Shark is a prime example of how all this open source technology works together and works well with Google's cloud. Shark is ultimately, is basically Hive on Spark, where Hive is SQL on Hadoop. So the Hive engine will translate SQL over unstructured data into MapReduces that run in Hadoop, whereas Spark is an entirely different data processing model than MapReduce. But here we have Shark implementing total compatibility with Hive queries, but instead of using MapReduces under the hood, it will use Spark. And we'll see how this plugs into Google Cloud Platform in two ways. First, by reading your external data from GCS so that your data can persist independently of persisting your compute cluster. And secondly, by plugging into Cloud SQL so that you can have multiple different clusters all plugged into Cloud SQL as your metadata store and reading from that. So we'll go to the demo machine now. And we see that, first let's launch a cluster. Let's see, BDutil. We ran something similar to this already, but just to elaborate a little bit, what we have here is an extension that I've created here that's just for installing Shark on Cloud SQL. And all it does is here are some shell scripts that actually install Shark. We'll provide some cluster-specific configuration, and we just kick it off. If we take a look at our cluster-specific configuration here, we see that we just have some basic settings like number of workers, a prefix for the cluster name that all our instances will have, which project to use, and so on. Since we were lucky enough to kick off a cluster a few moments ago in this presentation, we can go ahead and just use that as our other cluster. Take a look inside. So, we'll run as Hadoop. And let's go ahead and boot up a Shark command line, a Hive command line, and maybe another Hive command line on the second cluster. Clear all these out here. So we can see we don't have any tables yet. Now, we can go ahead. I happen to have a data set here of, let's see, a natality birth data set for the year 1970 through today. And it happens to be an Avro format. So this is just some files sitting in GCS. And what we'll do is we'll create an external table which is pointed at that. So now that that has been created, we see that it appears in both Shark and in Hive on the same cluster, and in Hive on the other cluster. So you can see, this is demo 2 down here and demo 1 up here. And sure enough, we can also select top 10 from it from any of these 3 shells. So suppose we want to find out if there are any trends in the number of underweight births as a fraction of the total number of births over the years. So here's a query that we have prepared here, and we'll just plug it into Shark. Now, while that kicks off, suppose we also have another set of data. Here's a common use case. Suppose we have a bunch of files in JSON format. So, people often use JSON format as an initial data format, but it's usually good to get a binary format like Avro. So we can go ahead and create this JSON table in our second cluster. And then what we'll do is, let's see. We'll use Hive as our data conversion engine here, simply by creating a second table in Avro format, and then just saying select star out of our JSON table and writing it into our Avro table instead. We'll do that in our second cluster. And now we can take a look at the web UIs here. So here I have a web UI open of the built-in Spark GUI. And we can see that we see all the commands that we just ran. We ran select, and it looks like it's already finished, the Shark query that we kicked off a little while ago. And if we go into our second cluster, demo 2, and open the Hadoop console, we can see that Hive has gone ahead and translated that second query, that JSON creation query, into a MapReduce. So now we have MapReduce running on this, some data that's in GCS, right next to Shark running against Spark on other data that was also in GCS. And we can see that, oh, sure enough, we've got the results. We see that over the 80s, the percentage of underweight births went down a little bit, and then seemed to go up as we came out of less prosperous years, apparently. So some very interesting data. And with that, I'd like to go back to the slides, and I'd like to invite Ashish Tusu up to this stage, CEO of Qbol, to talk a little bit about our new partnership.
No, I'm fine. Great. Yeah, I thought that, but I'll, great. Thank you.
With GCS was very Hadoop friendly for us. Things like better speeds in the metadata operations, things like better characteristics around eventual consistency and so on and so forth really made it much easier for us to provide the service on the Google Cloud platform. And at the same time, speed efficiencies, for example, launching VMs is 2 to 4 times faster on this platform. Which is very important for us as a service provider, because in the Qbol model, the clusters are brought up on demand. So you run a job, the clusters are brought up. While you're running the job, the clusters are expanded or shrunk, depending upon the usage, and then they're taken away. And so the boot up time is very, very important for us. So all these things really, were very good for us to provide a good, compelling, performant, and a cost-effective service Hadoop as a service on top of the Google platform, Google Cloud Platform. So we have been working very closely with the Google Cloud Platform team to really bring other pieces of integration into Kubol as well. First of all, we are using, so in the cloud, the model is really the persistent store is the object store and not HDFS. Kubol takes full advantage of that and the GCS connector to really work closely with GCS and make sure that the processing of that data is completely seamless as far as Hadoop is concerned. The other big thing is the BigQuery is a strong, fast, interactive, big data solution on Google, which works really well. And Kubol also incorporates that as part of the platform in two ways. We have mechanisms through which you can use Hadoop on one side, process data, and push it out to BigQuery for further consumption. And we also have mechanisms wherein you can actually run your Hive queries on BigQuery data, where we treat that as a data store as well. Both of these enable things like putting more tools and more options in the hands of the analysts and the developers to really take advantage of when they're building their analysis or building their data pipelines or exploring data sets on various different data stores as well. So those are the two close pieces of integrations that we have enabled on the Kubol platform on Google Cloud Platform. And we are very excited to announce that while this platform has been an invited beta for some time, we are going to open it up on 7th of April for anyone to come and use Kubol running on launching clusters, Hadoop clusters, or doing self-management of Hadoop clusters on Google Cloud Platform. So that's a big announcement. Please definitely go out and go check it out and use the service and give us any feedback that there is. With that, that's all I had to say, and thanks for the opportunity to talk here. Done?
Welcome, everyone. It's great to have you here at the end of the day. Thank you for sticking around. We've seen some pretty exciting announcements today. I want to welcome back to the stage Urs Hölzle, who's the, as you already know, is the Senior VP in charge of technical infrastructure at Google, responsible for building all the data centers. And I also want to welcome Jeff Dean on stage. Many of you know Jeff, and if you don't, you probably should. He's a senior Google fellow and has had his hands really in every piece of major infrastructure at Google, and he's built many of the systems that you know and have heard about and have inspired many open source projects such as MapReduce, Bigtable Spanner. He's worked on web search, the ad serving system, basically all the important bits at Google. So, Urs, if I can start with you, maybe ask you a couple of questions that are sort of on top of the developers' minds today. We've heard a lot about the commitment to cloud and everything that Google's putting behind the Google Cloud Platform. Can you maybe tell us a little bit why cloud is important to Google, why cloud is important to you?
Sure. So it's really two things coming together. One is that you know, we always like to think about the long term, and if you think about it in a 10-year time frame, there isn't really any chance that 10 years from now, the public cloud isn't a major, major part sort of the world, right? Today, kind of everyone talks about it, but the reality is that you know, all who are using cloud are part of sort of the vast minority of developers and IT folks who actually are doing it. Yeah. But if you think 10 years out, there's just no question that a reasonable fraction of the world's server-side cycles are going to be in the public cloud. And that's going to be an interesting business for us, for others too. Yeah. And so if you look at just the numbers, it's easily bigger than the advertising business is for us, right? So that's kind of the business opportunity side. And then the second part is really the technical opportunity. We've been living as Google in the cloud for 15 years, basically, right? For 13 of these 15 years, our cloud was just for our own use. But we've learned a lot, and many of the things we learned apply kind of directly to sort of the public cloud. And you know, you mentioned Jeff, right? I mean, we came up with MapReduce, and that's now turned into sort of a common thing that everyone uses. It's just that we had the problems earlier, and that's why we kind of came across the early. So there's a big opportunity for us to actually take that technical leadership and really turn it into product leadership on the external side, just not just on the internal one.
Okay. So yesterday there was an article in Wired magazine where you were quite prominently featured, and in that article there was a memo that was described that you wrote to folks in your organization, to the technical infrastructure team, but also to the rest of Google, and you set a call to change in direction in motion. Can you maybe talk about what you wrote and what was the reason for sending this memo?
Sure. Yeah, that's my engineers get to write code, and managers get to write memos. So we compete on equal footing.
How many lines of memos have you done this year?
That's right. My memos are very concise, and I write them in Emacs. So I write them in Google Docs, of course. But so we're really going through a change. So we started about 2 years ago to redo our internal infrastructure, because in the 15 years that we've been doing it, we learned a lot. And we went through a big push to simplify things. Right? We accumulated a lot of stuff because we tried a lot of things, and some of them worked and some of them didn't. And now we think we actually know pretty well how to do that. And we're using this infrastructure to power cloud, and we want those two to be the same. And previously, so the last 2 years, was really the preparation for that, laying the groundwork. And now that platform compute engine is actually live, no longer beta, now it's time to really move many more of our infrastructure systems onto the external platform. So the New World memo that I wrote was really about taking this here and making this the #1 priority for everyone, and have really the majority of the organization work on the external product rather than the internal one. And one of the reasons we can do that is because our internal one is actually in pretty good shape. So, not working just, quite as much on it is not going to hurt anyone. Right? And so this year we're really spending the majority of our effort in externalizing the many things that we haven't externalized yet, because the platform now is ready. And so now adding people will actually make things go faster rather than slower.
So it's a pretty significant shift.
Yeah, definitely.
Hence the memo.
Yeah, yes.
So App Engine, in less than 2 weeks' time, turns 6. So Google's been working on the cloud platform for quite some time. But it seems that not only seems that there's actual accelerated launches that have been happening in the last 12 months, and of course with today's event. Was delivering and creating the Google Cloud Platform always the plan for you from day one, or is this something that has evolved over time?
So I think the dichotomy between infrastructure as a service and platform as a service is really a kind of a false dichotomy. It's really much more of a grayscale, and you saw that today. We kind of want to make it a grayscale where you can be all the way over here, where we make all the choices for you, and your life is really, really easy, or over here where you can make all the choices, and your life is really, really flexible, but maybe you have to do a little bit more work. And there aren't just these 2 points, but there's basically anything in between. And so I think what we realized was that even though people were extremely successful on App Engine, you heard Snapchat today, but there's many other examples. People really love App Engine because they can walk away from an application after they deployed it. And really, the way we say it, your only maintenance action for years is to renew your credit card. Right? That's really all you have to do. And there's incredible value in that. But even the biggest users of App Engine said, hey, look, I have this other piece on here. And it's not realistic to rewrite it, or I don't want to rewrite it, or it's actually great as it is, and I need to be able to just run it. Right? And for that, you need VMs so they can wrap them around. And our goal really is to say, look, pick the parts that you like most, right? Implement the components the way you sort of see fit, and then fit things together into a low effort, high performance, easy to maintain sort of system. And so it's really not an either or. And I think, so that's that. And we set out certainly with a vision of having something that's very high level, very easy to use, and very sort of low touch once you're done, very productive. And actually, if you asked me to bet, I would say 10 years from now, that is going to be the main way of how you actually use the cloud. Because if you can fit into that pattern, it's so useful, right? I mean, it's so low cost because you don't have to touch anything that's really a big win. But you got to cover the entire spectrum, and there's a lot between now and 10 years from now that's going to change. So this is an iffy bet even for me to make.
Okay. So when you run and manage the world's largest data centers, and you're hosting millions of applications and that application data, security has to be just at the top of your mind. And why should developers trust their data to the cloud?
So I think there's two answers. One is because we're probably going to do a better job than you would do yourself, because security is hard, and there's always all kinds of ways to screw up. And we have a great team. The second one is that there used to be this conception that IT needs security, right? That's where your standards are high, and consumers, they will deal with something that's insecure. But that's not really true, right? With consumers having moved much more of their personal data in the cloud, they set the very high standards. They have very high expectations. And so for us, as a consumer cloud provider, a security incident would be extremely expensive. And so we're actually spending hundreds of people, right, on security, a very, very good security team, to really try and make that extremely unlikely. And even on the consumer side, you have security features like one-time passwords that are ahead of many enterprise products today. Or our HTTPS for years now has used elliptic curve cryptography, which makes it much, much more secure against intruders, even if you get the master key at some point. You still cannot decrypt recorded sessions. So we've worked really hard on that, and I think if you look at that as a developer, do you want to take advantage of that, or do you want to try your own luck? I think you're going to be better off at doing it this way. And then in the cloud, we have the extra advantage that if you wish, you can go encrypt your data with your own key, where not even we have access to it. So you get the infrastructure that's already very secure against sort of the common mistakes. And then on top of that, you have your own extra layer of security under control. And so that's really a pretty good place versus hosting yourself is really, I think, a bad proposition.
So you could get the best of both worlds that way.
Exactly, right? You can layer on top, you bring your own security, but you really benefit from having, from all the work that we've already done. And in the long term, like people ask about, oh, what about security in the cloud, compliance in the cloud? That's just as much of the success as technical features, right? So if the cloud really 10 years from now is a major factor sort of in everything IT, then very clearly it needs to be the best security place and the best compliance place, just as it is the best technical place and the best economical place, right? These things need to come together. You can't really, leave them out. So almost by definition, right, our security will be very good because it has to be.
Yeah. Okay. So I'd like to move in a little bit to sort of innovation at scale. And Jeff, since we have you here, you've been involved in all the large-scale distributed systems at Google. And I wonder if you could sort of share some of the challenges you've sort of witnessed and had to deal with and program around that really only happen at that very large scale. So things that you wouldn't see if you have an aisle of servers in a data center, but something you see when you have data centers full of computers, warehouse-scale machines, many data centers across the world, 15 years of sort of running software on there.
Battle scars.
Yeah, tell us your battle, show us your battle scars.
I think there's a lot of lessons we've learned over time. And from the very early days of Google, we had hardware that was kind of very consumer-oriented hardware. It didn't have a lot of sort of reliability features built into the hardware that you might like ECC memory or even parity for our earliest machines. And so if you sort a terabyte of memory, a terabyte of data with a machine's not parity, it ends up mostly sorted. And you sort it again, it's mostly sorted some other way. So I think, from those early days, to work around that, we built sort of a software checksumming library that is sort of in constant use in all pieces of our infrastructure, just to make things more robust to that kind of very low-level hardware error. Now, modern machines have ECC errors, but sometimes switch buffers don't necessarily have ECC, and so you can get corruption even in network transit, and so these kinds of things are really good for protecting against that. And then I think when you're pushing the boundaries of scale, like you're running systems that are thousands or perhaps 10,000 machines, you see failure modes that are really rare but are very perplexing and annoying that you wouldn't necessarily see if you're running a 100-machine system. So a good example is if a whole rack switch goes bad, that's a pretty rare event, but all of a sudden you lose 40 machines or 80 machines off your network. But even more nasty than that is like a switch that kind of is working. So it drops half the packets coming through it. And all of a sudden,
in one direction.
Yeah, or only in one direction. Right. And that's actually tricky because things like health checking and so on that are designed to see if something's alive, actually work. Like it is alive, it's just incredibly slow and you can't actually communicate effectively with the machine. So, these are the kinds of problems that you see running at scale. And one of the things that has happened is you recognize these sorts of problems and then you build infrastructure to sort of, in software, deal with these kinds of failures automatically. And so, some of the things that we've built into MapReduce are designed to be robust to not just a particular kind of failure, but lots of kinds of failures, even ones we can't imagine right now because the software techniques are just effective at dealing with when things aren't working right, no matter exactly how they aren't working right.
Yeah, okay. So Urs, you co-authored a book, it's called Data Center as a Computer, An Introduction to the Design of Warehouse-Scale Machines. And in there you talk about this sort of software tolerance. you know, if we get to the point where we can design some of our own hardware and build better switches, tell us why we can't just build better hardware so Jeff doesn't have to work so hard.
We can, and we do, but Jeff still has to work hard. No, the problem is that really scale kind of in the end gets you, even if you try to avoid it, because even if you had an incredibly good piece of hardware, there's no manufacturer in the world that can make 100,000 of them and have them work 3 years without things failing. And so once you accept that you will have failure really as part of every day, then whether something fails, you know, 3 times more often or not is actually not your problem. The problem is that there's failures that you have to recognize and isolate and sort of automatically deal with. And so I think we came to peace with that, you know, a long time ago, because you really realize, okay, even if I could do it better by a factor of 10, and I don't see any vendor who does it better by a factor of 10, but even if I did it, basically my software effort is still the same, because failures would still happen. And to some extent, actually more frequent failures are the ones that you handle really well, because those are the really well-tested kind of things. So to some extent, there is really not an advantage of making them more rare. And so generally, we pick the right point. So today, we do have ECC memory, because you know, memory errors actually are, you know, at today's lithography are even more common than they used to be. So you absolutely want to have it. But still, do we actually have memory errors that even ECC, 2-bit ECC correction does not detect? And the answer is yes. Right? At scale, you're going to see that. And you know, I haven't done the computation recently, but I'm sure we see it at least every week, probably every day, just based on the amount of RAM that we do have.
And the solar flares. Actually.
Exactly, right? alpha particles, and so on and so on. And so you have to go deal with it, right? And have enough resilience so that you can actually still move on.
So being on the way I sort of read this and summarize it is, so being on the cloud platform sort of insulates me from solar flares.
Among other things.
Among other things.
Hopefully, yes. Yeah. Yes, hopefully, yes. And we really hope that we can expose some of these things that we learned as tools that make it easier for all of you to build applications and not actually have to understand how to deal with failure, because as long as you follow these simple rules, you will be fine, right? That's kind of the ideal situation. Today, we have realized that in App Engine and on the VM side, to a smaller extent, we've realized it with the VM migration, where we're able to move you away from something that we see coming, and you don't know this even happened, but we can do a lot more in that area.
Okay. So Jeff, when you were building the sort of the first iterations of these distributed systems 14 and a half years ago, did you realize when you were sort of trying to make the engineering trade-offs and dealing with failures, providing availability for the systems and consistency, did you realize at the time that that was essentially those 3 components, the CAP theorem, consistency, availability, and partitioning, that were really underlying the engineering decisions?
I mean, I think...
So, just to interrupt, I think it's called Brewer's theorem. At least that's how I like to call it.
Really? I always call it the CAP theorem.
No, it's Brewer's theorem.
Sure?
I think I know this
I think it's too much about cats, I think.
No, CAP.
I think I know this one.
All right.
Can I join you?
Yeah. Everyone, please welcome Eric Brewer.
What a surprise.
Dr. See you again.
Eric, thank you for joining us. So you noticed that we had a 3-person couch, so obviously we needed a third guest.
Saw that coming.
If you don't know Eric, he devised the CAP theorem or Brewer's theorem. We'll let him answer that question in a moment. He's a professor at UC Berkeley of computer science, pioneer really in building large-scale systems, built the first really useful cluster for web infrastructure. And can you tell us, do you prefer CAP theorem or Brewer's theorem?
Actually, I prefer CAP theorem because it sounds bad coming from me to call Brewer's theorem.
Okay.
So you can call it whatever you like, but I'm always going to call it CAP theorem.
I'll call it Brewer's theorem.
That's all right. I don't mind.
Can you maybe tell us a little bit about CAP theorem, I think sometimes it's explained sort of incorrectly as a 2 out of 3 choice.
Well, I think in 2000, or really when I first thought of it, was about 1998, it was a 2 out of 3 choice in the sense that we were in an era where everyone wanted ACID properties and wanted us to build literally cross-national systems that had both availability and consistency. And I realized we weren't able to do it, but also that we were regularly choosing availability over consistency. And, but people didn't accept that that was the choice that I had to make. So they were actually very reticent to say that's an okay choice. And so the CAP theorem in some sense was to give everyone, myself included, permission to choose availability, right? And now that's what happened. People like Jeff chose availability for Bigtable, and many others have as well. And I think it's because the internet's the first time we had a kind of 24/7 service, except maybe the phone system, which isn't really a data system, it's a communication system, where you actually had both data and availability that you wanted to get. And so we actually started making some difficult choices, which we still make, actually.
Okay. So you've, in addition to CAP, you've also looked at sort of the origins of SQL and NoSQL databases. And on the cloud platform, you can get a managed SQL service, a managed NoSQL service, but you can also sort of run your own. If you do VMs, you can spin up Cassandra and have your own flavor of a large NoSQL system. How should developers sort of think about those trade-offs and how do they select one over the other?
I actually try not to choose, even though I've just told you that you have to choose. You only have to choose if you are going to have partitions, and only during the small amount of time where you have partitions, right? The rest of the time you can actually mix them much more gracefully. And I would say we've already built systems, and certainly talked about some like Spanner that Jeff worked on, where you can set it in a more of a consistent setting or more of an availability setting, and you can make those choices on a relatively fine grain. If you know you want partitions, like you're doing mobile phones or disconnected operation, and you really are going to have truly concurrent operations on both sides of a partition, then you really have to plan around that and think about your merging. Otherwise, I think you can be a bit more graceful about it. At least kind of that's the modern answer, I would say. Okay.
So you can have sort of all 3 legs of the stool, but just not all at the same time all the time.
You have to play with them a bit more gracefully.
Okay. So Jeff, if you've been building sort of many generations of these storage systems, and there's maybe you can talk about sort of the problems you were working on when you developed a Bigtable and MapReduce. What were sort of the fundamental Bigtable or sort of big data problems that?
So MapReduce sort of originated when my colleague Sanjay Gamawat and I were actually working on rewriting the core indexing system for web search at Google. And the pipeline at that time goes from a bunch of raw pages on disk that our crawler has collected, sitting in a bunch of files. And you have a bunch of stages that are trying to sort of transform it and do things like find duplicates and choose which one of the duplicates you want to choose because it has a prettier URL, compute PageRank, decide which pages we're going to put in the index, what language they're all in. So there's all these little phases that conceptually are doing pretty simple things. But the code had gotten really complicated because in each of those phases, we'd kind of rolled our own parallelism for that phase. We say, well, this one runs pretty fast, so we need to use a couple hundred machines. This one's slow, so 1,000 machines would be better. And each one of them had its own checkpointing mechanism and recovery mechanism for that to deal with failures, because when you're running on that many machines, you have failures. And so what got lost in there was actually the fact that all these operations were relatively simple and straightforward, and they were obscured by all this sort of nasty support code. And so Sanjay and I kind of started squinting at each of the phases and looking for abstractions that we felt could represent all the simple computations we were trying to do in a way that we could then hide all the complexity of dealing with failures and automatically parallelizing across an appropriate number of machines and dealing with slow machines in a library. And so MapReduce is kind of what we came up with. We have both have backgrounds in looking at different kinds of programming languages, and the functional programming language paradigm is a pretty useful one. And so MapReduce kind of builds at least loosely on that. And so we realized that all the phases in the indexing system could be represented in this abstraction. And then we could work hard on making that one library perform really well. So that's kind of the origin of MapReduce.
Okay.
And the origin of Bigtable is kind of similar in that we wanted to have an incrementally updating system for all of our indexing systems. So we wanted to have a row of data for every page we know about, and then have different columns that are being asynchronously updated. So the crawler would go off and fetch contents and then write the actual current contents into one of the cells. And then there'd be other asynchronous processes updating things like what language we think that page is. All the different phases we used to run in the pipeline would now run kind of asynchronously. And then we'd always have the current state of this page by just looking at that row.
Okay.
And we needed to scale that out to a very large number of machines to deal with all the pages that we wanted to represent. So.
Okay. And then how did that lead then to Spanner? What subsequent problems were you solving that Bigtable didn't address?
So the first version of Bigtable essentially ran within one cluster, within a single data center. And then over time, we added some support for sort of eventual consistency to have more interactive services where you wanted to keep a bunch of geographically distributed versions of the data in sync. But that was kind of somewhat unsatisfying because you actually want all of the things that you mentioned. You want consistency and availability. And it's actually kind of a pain for developers to deal with having 12 Bigtable replicas of their data scattered around the world. And so what Spanner solves that Bigtable didn't really do is the problem of geographic distribution of data across wide areas potentially. And also some flexibility in allowing users to say, well, this particular data, I want to keep 2 copies in Europe and 3 in the US, and I don't really care where I keep them. That's just roughly where I want them. Okay. And that gives the underlying system freedom to move data around in response to changing patterns of demand and load and disk availability in our European data centers. And also, Spanner allows users of the system to select the appropriate consistency trade-offs. For some operations, you want a strongly consistent view, and you may pay for it in availability. Other ones, if I'm marking an email message read or something, it's probably fine to have an inconsistent view of that data. What's the worst that can happen? And so I think allowing users to pick that trade-off appropriately for the different pieces of their application is one important thing Spanner allows you to do.
Okay. So Eric, you joined Google about 2.5 years ago.
Yes.
And you're currently on sabbatical from UC Berkeley. And you've had a chance to look at innovation sort of in the academic setting, the commercial setting, and you've seen it sort of firsthand inside of Google. How would you compare the way innovation happens? Is the pace different? What does it feel like to be inside of Google, and how does it compare?
Well, when I started in this area, which is almost 20 years ago, we had a cluster of 4 machines. You could put it on a desk, and that was actually enough to make progress on cluster computing. Right? You could actually solve problems that were new with 4 machines. And now we're at the state where you really need many, 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 many more machines than that. And so I kind of feel like Google's the place to be to have the problems that I want to solve. Right? They just aren't anywhere else because of the scale and because really of the goals. It's an ambitious place to be. And I think I get a lot of challenge out of that and great enjoyment.
And do you think, is the pace different of innovation? Is it faster at Google?
Yeah, well, I mean, it's faster in several dimensions. It's faster because you have vastly more people. It's also faster, I think, because there is an urgency, right? There's not much urgency to cloud computing in 1995. I remember we went from 10 machines to 100. That was a big deal, right? Like, woo, 100 machines.
Factor of 10.
Yeah, it was a factor of 10, and the things broke, and we had to fix stuff. And so, but it's definitely not the breadth of stuff going on, and also, I think, not really the same ambition. The time is more ambitious now, and that's great for everybody.
So it's harder problems and just bigger scale, really, that
absolutely
that drives this.
And actually, Fred, if I can, having been in academia myself, I think one of the big differences really that today I think academia struggles with is that you may have the ideas, but you don't have a good way to test them, right? And not just because you lack the infrastructure, but you also need real-world applications to actually
That's right.
test
You need users and data.
your thesis, right?
Yeah.
Whether it really works, right? And one of the great things at Google is that we're in a pretty good place already because we've been working on it for 10 years, so the standard is relatively high. We have great people and we have great problems to solve, and together that really kind of gets an acceleration sort of factor. And my favorite quote actually from the last half year or so, for those of you, just a short digression into networking, Van Jacobson, if you know TCP, you know Van Jacobson. So he's at Google. He joined us, last spring or so, and I talked to him in the summer, and he said, I didn't expect that, but in the last 4 months, I've gotten done more than I have in the past 5 years. And I said, why? And the answer was, I can actually test an idea, right? And I can test it very quickly. And then the next day, I know I was wrong, but I have a better idea. And so I can actually, and before, this took me years, right, to get to that point. And that's really, I think, one of the big opportunities I have. And that's why I said before, 10 years from now, really, we're not going to live in the same world, right? Things will profoundly change because we can discover along the way the things that we do right and the things that we do wrong, and then think of better ways or more innovative ways to do them wrong, right? And then, but over time, right, we get them less and less wrong.
Yeah. So talking about sort of that pace of innovation in the future, I see, Jeff, you wore your Google Brain shirt. So I wanted to
cerebellum is folded, though.
I wanted to ask about that. You wrote a blog post in I think it was 2012, and you described what I'll just call a very large cat detector. But there's a lot more behind it. I wonder if you could talk a little bit about the project, what you did in 2012, and then maybe we can talk a little bit about what's happened since then and what the benefits to other Google products have been.
Sure. So the last couple of years I've been working on, I switched gears a little and have started to look into very large scale machine learning systems, and in particular systems for training very large neural nets and then using them for a variety of problems. This project started because Andrew Ng is a Stanford faculty member with expertise in this sort of field of machine learning, and was spending a couple days a week at Google, and he and I bumped into each other in a kitchen, and he said, oh yeah, I'm thinking of like figuring out how to use neural nets for things, and I'm like, oh, that sounds like fun. I'd actually done an undergrad thesis on parallel training of neural nets a very long time ago, actually. So, he kind of said that at small scales, these kinds of approaches were showing pretty promising results in perceptual tasks, things like computer vision and speech recognition. And so I said, wow, that sounds like if we just made them bigger, they'd get even better. And so he and I and a few other people started to form a little project around this of how are we able, can we build systems that allow us to train very large neural networks to accomplish interesting things. And so one of the first experiments we did was to do what's called unsupervised learning, where you don't have sort of the desired output of the model. You just have a bunch of raw data, and you want the model to kind of capture regularities and interesting patterns that it observes. So the experiment we did was we took 10 million YouTube videos, one of the benefits of having lots of data lying around. And we took one frame from each one of them, so it's kind of a random sampling of video frames. And we put it through a model where we essentially just tried to learn representations that were good at reconstructing what the individual images were. And so the training was done on 16,000 cores, and that's one of the benefits of having these large-scale cloud platforms, is that we can do those experiments and get results more quickly. So getting back to Van's point of being able to get results on your experiment to figure out what the next thing is that you want to do, being able to run that on 16,000 cores instead of 1,000 is not necessarily as efficient as doing it on 1,000 in terms of actual dollars, but it lets us get our results more quickly, and so we're more effective. So anyway, we trained this model in a completely unsupervised manner, and then we looked around at what the highest layers in this model, so it's like a deep 10-layer neural net, and at the lowest layer, the neurons learn to be responsive to very primitive things like edges at different orientations. And then as you go up, the neurons get a little more complicated, so they'll learn like corners or things like that. As you get a little farther up, you'll get like pieces of chair legs or things like that. And so we looked at the top layer, at the very top of this model. There's 60,000 neurons. And then we had a test data set that was, it's YouTube. So we said, well, there's got to be cats. So we took a test data set that was half cats and half not. And we knew those. And we looked around for a neuron that was most sensitive to whether or not the image contained a cat. And if you can just skip ahead. So we looked, and we found a neuron that was actually pretty responsive. So these were the images that caused that particular neuron to get the most excited. And you see that they're mostly cats. There's one Starbucks mug there, but mostly cats. And I don't know, if you can see this is actually the representation of the optimal stimulus, the thing that would cause that neuron to get the most excited. And that's actually a cat. It's pretty cool. We call it average cat. So by just training on a lot of data, this model has essentially invented the concept of a cat without ever being told what a cat is. And that's, I think, a pretty fundamental thing. We looked around at other neurons and found ones that were receptive to faces and backs of people and sort of concepts you would expect these models to represent from just looking at a whole bunch of images.
I think we have another slide. Let's look at this next one here.
Yeah. So then we shifted gears a bit and realized that although this unsupervised learning was incredibly cool, there's actually more applied uses you can make if you have a large supervised data set. So you have a bunch of images and you have a bunch of labels. So an image of a cheetah and the label is cheetah, and a garbage truck, garbage truck. If you can directly train on that objective where you want to give it an image and then have it tell you what it is, supervised training is actually pretty effective. And so again, once we've done a little bit of supervised training, we then looked at what are the optimal stimuli for a few of the neurons at the top layer of this model. And you see that some of them are pretty good at succinctly finding things that we would, as humans, know what they are, like yellow flowers or wine bottles or balsamic vinegar or pizza at the bottom. And some are kind of a little more abstract. They aren't a single sort of succinct category, but they're things like very textured, spotty objects. So I think that's kind of an indication of what's going on in these models, and it's interesting.
Okay. So 16,000 cores, probably 1,000 machines or so.
Yep.
How many, to detect a cat, so how many cores would we need to represent the brain of a cat?
Well, I think those kinds of comparisons are hard because we I think, have a pretty good handle on how to do training for sort of categorization tasks. But the brain of a cat actually is much more complex and has a lot of sort of mechanisms in it that we don't understand quite as well from a machine learning standpoint, how to do sort of feedback and control. But from a perceptual viewpoint, I think we're getting a handle on how to train interesting systems to do perceptual tasks pretty well.
Okay.
We actually have a fair number of those perceptual tasks at Google. Some of them are very general things like this general object recognition, and some are more fine-grained. So the Street View team, if you can click to the next thing, wanted to be able to find text in arbitrary street scenes. And so with a little bit of labeled data, we had some people draw bounding boxes around text in some scenes. You can actually see that this model does a pretty good job of finding text in these scenes, which is kind of the precursor to then doing OCR of the world. Maybe I have one more example there. It's just another street scene. But it's a pretty challenging problem because you see like there's all kinds of things like logos and different font sizes, different fonts, different colors. But this model is actually able to do this very effectively and is doing it from raw pixels. So you just feed in raw images and it is able to sort of give you this nice heat map of where text might be. And we have other models that find street signs or other kinds of interesting things in these data sets.
And have there been benefits to other Google projects from Google Brain? Like you mentioned voice recognition, is that being used?
Yeah, so we've been working with a whole sort of a growing array of different teams. We've had some very initial close collaborations with different teams. So the speech team was definitely one of the early clients we worked closely with to use our distributed training system for problems they had. In particular, they wanted to build and train very effective acoustic models for speech recognition. So that's kind of the first part of speech recognition where you go from a quarter second of raw waveforms of speech to predicting what is kind of the sound being uttered in the middle 10 milliseconds. Is it a ba or a f or a s, that kind of thing. And then you kind of stitch it together with a language model to actually figure out what the utterance is. And so working with them, we were able to train a pretty big acoustic model that was actually much more effective than the previous kind of model they were using for this. And the word error rate for English recognition dropped by 30%.
Wow.
Which is sort of a really huge drop. Like this is kind of unheard of.
Drop.
Yeah. And 30% drop goes from like not quite usable to actually quite usable for a variety of tasks. And we're continuing to push on making the models bigger and better. And then a whole bunch of other teams kind of came to us after they saw that success on speech and on some of the image tasks. And now we have about 30 or 40 teams within Google applying these models to all kinds of different problems.
Okay. So the neural networks that you're sort of working with, the basic form thereof, they've been around since the 80s. Why is it that we're making progress now?
So I think a few things. One is, as you say, the basic ideas have been around for about 20 years. 20 years ago, there wasn't enough computational power to train very large and, in particular, very deep networks. So people were playing around with neural nets that had maybe 2 or 3 layers of abstraction in them, and on fairly small data sets. So I think the big difference is we now have enough computational power and big enough data sets to really train very large models and have enough computational power that we can do that in a reasonable amount of time. We have kind of what we call a patience threshold of 4 or 5 days we're willing to wait for a model to train completely from scratch, and maybe a day if we're like really experimenting quickly. And so the reason we use lots and lots of machines is because we want to train the biggest model we possibly can in that patience threshold.
Okay.
And if we're able to train a bigger model because we can parallelize things better or use more machines, that's just gravy, because we can then train more effective models on larger data sets and so on.
Okay. So I'd like to sort of step it back into the data center world. And so we've just talked about this neural network with 16,000 cores. That, in sort of Google scale, is probably a small scale system. When we talk to lower level storage systems, and they're much larger, how does your technical infrastructure team sort of deliver the network so that all these machines can talk together, both globally and sort of within the data center?
Yeah, it's definitely an interesting problem, and one of the nice things is that it's kind of like having a child, right? Doesn't come with a manual, but fortunately they don't actually, like, they grow up slowly, and so you have some time to catch up with their demands, and that's kind of been us with networking or compute or storage. If we had the problem from sort of day one, then we would have been pretty overwhelmed. And so networking is actually something that's become very important in the last 10 or so years, and we've started to do a lot of work because we got to the place where, just like with compute or with software systems, we couldn't buy what we needed. There wasn't really a vendor. So it wasn't a question of, should we build or buy because which one is cheaper, but really there is nothing out there that you can buy, right? So you have to actually build it. And one of the biggest sort of leaps we made recently is to convert our actually, let me back up 1 second. So we started building networks, obviously, right? Both inside the cluster and between all the data centers. And so we've been owning, dark fiber and lighting our own optics, et cetera, for a long time, because at scale, you kind of need to do that, both for capacity and price reasons. But one of the biggest steps that we made recently was to convert much of our external backbone, so this is the backbone that connects the different data centers together, to run not on traditional networking protocols like BGP and OSPF and LSPs and all these things, but MPLS, but on OpenFlow, which is actually kind of very cluster-ish kind of idea of how to control networking, where basically takes the same idea from cluster computing, where you say, gee, the individual node shouldn't really make decisions. Let's have a manager, like the nobes are dumb. They basically they're just a pool of nodes, and we tell them what to do, rather than them trying to communicate and figure out what to do. So in networking, once you have a certain scale, you actually want the elements, the routers, the switches, to be relatively dumb, because they don't really understand what's going on sort of worldwide. And OpenFlow, or software-defined networking in general, really brings that world much closer to the software world, right? So now we have a global network that we can control much better and at a much higher level, sort of more at the application level, if you want, rather than sort of at the network level. So we can worry about, hey, here's 2 Gmail cells that are talking to each other, and not about here's port 1, 2, 3, 4, and some QoS class and some IP ranges and things that are just brittle, right? And so that has helped us a lot in really pushing the envelope in terms of how fast we can grow and how well we can control it. And one of the biggest advantages, and that's really what we've seen, I think since the 90s on the cluster side, is that once you move something to be sort of more software controlled, you can simulate it. And simulation means you can do better testing. So one of the big reasons why we're actually able to switch our global backbone from traditional to a completely new stack in about 15 months was that really we couldn't do that testing it on the real hardware in the real world, right? That would be pretty risky. But we were able to build our global network sort of in software as an emulation, and so we could play through all kinds of disaster scenarios. What happens if this thing goes down? What if this thing goes partially down, right? What if you'll lose this line, right? Does the software react correctly, et cetera? And so if you can do the software testing, really the whole integration, unit and integration testing, then you have much higher confidence that when you actually try it out, it will really work, right? And if it doesn't work, you can explain it in a much better way. And once you've figured it out, you can add it to regression test suite, and it won't happen again, right? You won't break it again with a new software release. So in networking, I would say that really in the last 10 years has probably been the biggest change, that now networks are becoming much more cloud-friendly, if you want, or cluster-friendly, because we can start to program just like we could program the nodes in the data center or the storage elements. And you can take the big picture, sort of how do you want to orchestrate things, and sort of automatically translate it down into what the network elements need to do. And your operator doesn't need to do that anymore. And that really is a huge change. And we're still discovering new opportunities of how that really sort of percolates through the entire stack. And you say, oh, over here, like I used to do it this way, but now there isn't really a reason to do it this way, because now I can do it the easy way, because the network now actually understands what I want to do.
Okay, so we've heard a lot of sort of innovation and research. Jeff, I wonder if you could talk about sort of Google's philosophy between research and engineering. How does Google make the trade-offs between the two? How do you decide which team you work on?
Yeah, I mean, I think one of the things that I really like about Google is that we have this very continuous, not hard boundary between research and engineering. So I'm in engineering, but I work on kind of longer term problems sometimes and work on shorter term things some of the time. And really, you're not a researcher or an engineer. You're working on problems that fall on different parts of this continuum. And the same person might move back and forth on this as they work on some very long term thing and then gradually get it closer to being ready to deploy to real users or whatever. Then you become a little bit more of an engineering hat. I think that's a really valuable thing. So on our team, we have a bunch of people who are a little bit more on the research end of the spectrum, a bunch of people who are a little bit more on the engineering end of the spectrum, and collectively we can do things with kind of complementary skill sets. So there's a bunch of people with a lot of machine learning expertise on the current team I'm working on, and a bunch of people with kind of large-scale distributed systems things. And collectively, we're doing things that none of us could do individually because we just don't have the whole set of skills in one person. And I think that's really fun because you learn a lot about that. You learn about how what are the trade-offs in doing machine learning algorithms at scale. And I think that's a really valuable thing to keep working on interesting problems and learning a lot as you.
Okay. And we've done that very deliberately, actually, because, and you see that today in cloud, but you saw that in search 10 years ago. When you have a problem that is so early stage, basically, and you can see the ramp that really is going to change by orders of magnitude. You can't sort of incrementally engineer the product to a better state. I mean, yes, you do that, of course you have to, but at the same time, you really have to fundamentally rethink things all the time in order to have a chance of actually keeping up and hopefully, even, getting ahead versus the problem. And so research versus engineering, it's almost, not sensible to ask the question, right? Like, how are they different? They're really kind of different facets of the same thing. And if you don't really tightly couple that, you're going to have research that is no longer grounded in reality, or you're going to have people who are too much grounded in reality, are just making today's problem better rather than recognizing that tomorrow's problem is actually very, very different and requires something new that is a departure from what has served you well in the past, right? And so we're trying to really blend that all the time and give people some freedom to do crazy things, because what looks crazy today might actually look obvious tomorrow, and so you have to kind of balance that.
Actually, a good example that came up today, which is the demo that was given this morning about doing live migration of a video player, is a demo I gave internally about a year ago. And that idea was in academia, I think, in 2003. But to get it right in Google, it took a while, and to actually convince people with something we want to bet on it. This is how we're going to run our clusters. That actually takes internal consensus and solving the whole problem, which you don't solve in academia, right? That's a big problem. It has to work for all the cases, and then you actually then get people to take that actually to product, which is now seen.
Okay. So you talked about building systems. When you built the Inktomi search engine, you of course sort of had to get your own gear and get your own cage in a data center, even shared one next to Google.
We were neighbors, yes.
Oh yeah, I visited that cage.
They sent heat my way.
Yeah, yours look much cleaner than ours.
But for the record, modern Google clusters look more like Inktomi clusters.
It's true, it's true. We no longer bungee cord our racks to the pipes.
That's more than 10 years ago.
Yes.
Yes. Would you, if you were doing it over again today, would you build Inktomi on the Google Cloud Platform?
Yes, I think that part's the easy part of the question, right? Which is, any startup shouldn't be investing in their own infrastructure, right? It's not the core competence, right? It's not fundamental to what you want to do. I think the harder question, which I think you can uniquely answer now, is when Inktomi got to a size where it could afford to build its own data center and have its own machines, should it or should it not? That's the harder question. And before today, the answer would have been Inktomi should have, because there would be significant cost savings to do so. But if Google's willing to provide virtual hardware on the same Moore's Law cost curve as the real hardware, then there's no reason to switch. And that's actually comforting, because it's a big pain to switch. So that's new, actually, new today.
So, Jeff, maybe not quite a final question, but what problems are you working on today? Is it still Google Brain? Is it an extension thereof? What are sort of the future problems that you're trying to solve now?
Right, I mean, I think one of the things that these neural nets are able to do is they're able to take very raw forms of data and then automatically build interesting high-level abstractions of that data and give you things that you can learn from that data automatically. And so unlike a lot of other machine learning techniques where you kind of hand engineer features you think are predictive of something you ultimately care about, these systems can build that sort of automatic combination of interesting features and discover what is actually interesting in your data automatically. So I think that probably is a very, how can we sort of package that up and make that easier to use has been a question we've been wrestling with within our group as more teams within Google try to use this for their own problems.
Okay.
We're making some progress on that, I think.
Eric, what problems are you trying to solve right now for Google?
That's the funny thing is, I can't talk about it. Right? In general, I've been here 2.5 years, and Urs mentioned before that we kind of, about 2 years ago, started making transitions to what we want to build, a kind of joint infrastructure for internal use and external use. And that's kind of what I've been working on for those 2 years. You can kind of see glimpses of it, but frankly, the best is still to come.
Okay. Urs, maybe Final thoughts for today?
Sure. I think Eric is trying to say we're solving problems that you don't know you had. No, but actually, I think Eric's pointing to something that's pretty profound. I mean, if we, like clearly where we are today is very cool. And if you had asked me 10 years ago, you know, like could we ever get to this kind of scale and have it work this way and it actually being available to really, you know, everyone, sort of at this scale, I would have said, no, that's probably unlikely, right? And so to some extent, really, it's incredibly cool where we are, right? It's amazing when I look at you know, a picture like this, the fact that, you know, we can stamp these out and they work as well and they're cost effective. And I mean, it's really, you know, I'm sometimes surprised myself, right? But in the grand scheme of things, I think we shouldn't kid ourselves about having solved the problem. We haven't solved the problem at all, right? In fact, we're kind of, you know, 2% in or so. And so I think the most amazing part to me is that I'm really confident that if we look back 10 or even 5 years from now to where we are today, and the things that we're proud of, right? Whether that's recognizing cats or handling petabytes or something like that, we're going to really be kind of embarrassed because it's so lame, right? And 5 years or 10 years from now, it will really be obvious how lame it was, even though it seems amazing today. Because we're so early in the cycle, and we're just having, you know, literally in the last 5 years, the different elements come together, right? Having data, you know, like actually solving the whole availability, partitioning, consistency, like in Spanner, for example, is a much better solution than we had earlier. You know, MapReduce, we're not actually using MapReduce anymore for new code, right? We have a new thing that's called Flume, and actually is an even more elegant way of expressing these things. But just in the last 5 years, we've had sort of the hardware and software pieces come together that actually are a good starting point where you can go off into a Google Brain within a pretty short amount of time. But if you take that ability and then really the innovation that happens everywhere sort of based on that, I think we'll really see an acceleration or an accelerated pace of discovery and innovation over the next 5-10 years, right? And so we all underestimate how fast that really will be. And we kind of, you know, realize that, okay, 5 years ago we didn't have, you know, smartphones basically or whatever. But, you know, 5 years from now, the smartphones, they're kind of just going to be, you know, faster and cheaper than they are today. No, they're not, right? They're actually going to be profoundly different as 5 years ago, you know, what was it, the T-Mobile G1 was, you know, compared to the Nexus 5, right? These are not the same thing. And so the same thing is going to be true for cloud. So, you know, when we sit here 5 years from now or 10 years from now, I think we'll have some pained smile if you show us videos of this conversation today or of our keynote this morning and say, yeah, you know, I guess given the time this was sort of cool, but today really, you know, that's what you were proud of. So to me, that's actually the most exciting part about all of this, right? We really are just at the beginning. Only 1% of the world is in the cloud. I think only 1% of the cloud's problems are solved, really. But I think 5-10 years from now, we're going to be well into the double digit on both of these sides, and it's going to be a very exciting time, you know, for me as a computer scientist, and I think for everyone sort of as a developer, to be part of this, right? This could easily be the time where, you know, decades from now, you tell your grandchildren or whatever, yeah, I remember, you know, this was a time when we went from sort of Stone Age to pretty modern in computing, in really software systems, and I was there, right? And now I realize how important that was. So I hope that 5 years from now you all agree with me on that, but I really think we're at the beginning of something pretty big and something that I'm, you know, more excited about than I've been in a long time.
Great, thank you for that.
Okay, yes, we get up. And we go.
Yes, we're done.
All right. Do we have an announcement? You're welcome.